Okay, sorry. So the meeting will be will be recorded, and it started now. So the first part is gone, but I will not start again. So the just showing you the structure. We have the IEA, the International Energy Agency, that has a lot of technology collaboration programs. So IEA wind is one, and there are then PV and all sorts of other energy sources. And within IEA wind, we have different tasks, and we are, as I showed, the task 51. And within our task, we have 3 work packages. And the work packages are really the chain of models that we need for the energy system. We have the meteorology, and we have the conversion to power, and then we have the end use. And but what we realized when we started phase 1 was that our subtasks in the work packages that we called then work streams, they span over often over 2 or 3 work packages, and that's why we called them work streams. And we work across all as it fits, and where we have people that are interested in participating. And today we are at one of our last public events, the Extreme Power System events, where we had a workshop in Austria last year, and this year is a follow-up on the international level. So the main results and learnings from the first phase is we had 4 public workshops. This is the 4th. We have brought the recommended practice as an open access book published with Elsevier. We have developed some open source code for evaluation and are in the process of publishing a platform for forecast evaluation and uncertainty quantification. You will hear about that tomorrow more, and we have about 25 publications already in those years and more to come. And one of the key targets also in our work is the liaison with the IEC, where we now have started to work on the first standard for our community for renewable energy forecast evaluation. And but what our learnings are from the first phase is really that collaboration is key. Collaboration across disciplines, across boundaries, across countries and continents. The more we collaborate, the better we become, and the less everybody has to invent the wheel anew. And with that, yeah, then a last short thing for those of you who do not know me, and also my colleague Caroline Draxl, together with Gregor Pante from DTU. He's coming later today. He apologized that he was somehow had a conflict and cannot be here right now, but he's our operating agent, and Caroline and I are task managers. Caroline is from EPRI. She will give some presentations later on, and I'm WEPROG in Germany and Denmark. And we are trying to coordinate the task together with our work package leaders, and you will hear more about that tomorrow in our task meeting. So let's get started with our workshop. And to explain quickly the way we have set up the workshop is that we want to get engaged with you. It's supposed to be a workshop, so it's not about only listening, it's about working together. And that's why we have made we have taken in Slido, and I would like to encourage you now to scan the code or go on a browser with slido.com and type in DWD 2025. and then you have to give the passcode extremes. And when you are inside the Slido, you will see the first question: what was your motivation to join us here today at the German Weather Service? And with that, I want to just get a feeling and hear your interest and motivation. And then we change to, yes.
No.
Here.
Sorry, yeah.
Okay.
No, so to speak.
We can see it here on the screen, but we cannot see it on the.
Oh, there it is. There it was. This is your slide deck. Did we share this?
Can we?
Is it maybe on the Firefox?
Yeah.
We just need to share.
Yeah.
Yeah, we can see it here on the screen, on our screen, but the screen is somehow
And
much.
we thought we shared the screen, the full screen. Then close sharing the screen and
This is oh, sorry, this is the Slido.
Es musste es wieder starten.
Maybe you have to move it one.
So.
Sorry. I'll move it. Oh,
we stop it here.
there we go. And now we go to the internet.
Okay,
Yeah.
here we go. These are the hiccups at the beginning, so bear with us. Yes.
So das ist wirklich interessant.
Yeah, so that is nice to see that the networking, and I take this as collaboration, is the one that, and knowledge sharing, that this is something that has brought you here. And that is really nice to see. So I'll give you, can we see? I'll give you another seconds while I introduce our first keynote speaker or introduction. In our introduction session, Renate Hagedorn, the Vice President of the German Weather Service, has agreed to tell us a little bit about what is ongoing at DWD. And many of you know Renate. I know her from her time at ECMWF, and then when she came back to DWD, she has been starting the large energy projects here in Germany, but also on an international level. And I think, Renate, you are one of the people that have really done a lot for the energy meteorology community, and have helped the collaboration between energy and meteorology. And I'm extremely delighted that you agreed to give a short introduction, and please welcome Renate.
Corinna, for the nice introduction, which makes me really blushing, I would say, because actually I don't have so many welcome words, but I was asked actually to say a few words here. Probably, I guess, to demonstrate the importance of the topic for DWD, and of course, I'm very happy to do this. But looking around, I can see indeed a couple of familiar faces, even faces from my ECMWF times, George, where I met him with the really first project in the context of renewable energy, and also you, Corinna. And so I think some of you already know that DWD really, for us, it's a very, very important topic, and we put a lot of importance onto it. And I mean, it was demonstrated really that we engaged in a lot of projects. I mean, I can say a few words, but I guess Vanessa will talk a little bit more in detail about our journey in the topic of renewable energies. But really, it was for me, this first project called Eveline was really kind of the trigger point or starting point here at DWD to really engage very much in this topic. And I'm kind of proud to say that we really managed in this journey now to implement a real dedicated so-called energy program. It's not easy to scramble, let's say, 5 people who really can work permanently on this topic. And I mean, Vanessa was also very, very important in this project. She's now leading this new energy program, and I can say it's in very, very good hands. So therefore, I mean, one thing I actually wanted to mention, we had yesterday a management board meeting, and we have a new head of IT, and he's here for 6 weeks, and he was looking around, so what's working well at DWD and where is maybe some room for improvement. And he was a little bit concerned about ITsec and cybersecurity, and how whether we are well established here in this context. And so he said, because he recognized that it's very important for DWD that we have really very secure, reliable services. And I can only agree with this, because this is one topic that I think the TSOs, DSOs are really very happy to work together with us as a reliable source of information. So I very much supported him and said, yes, it's a very good topic if you focus also on that area. So you have here given a very nice interactive introduction, and I think I have read a little bit here in the agenda. You have a very dense agenda, and so therefore I don't want to take too much of your time, and just wish you a very, very good meeting with lots of discussions and interactive and exchange of ideas, not only here in this room, maybe also during coffee breaks in the evening, maybe with a little beer or so. And I think, as you said, closing the gap and really talking to each other is very important. And actually, it was even one of the main reasons that I changed from ECMWF to come to DWD, because they said, if you want to work together with the users, you have to go to the Met services, and this is exactly what is happening, and I'm very happy. And so without further ado, I wish you a very good, fruitful meeting. Unfortunately, I have to leave more or less directly now, because at 9:30 I have the next meeting. I might try to come over for a couple of exchange and talks during the next couple of days. But for now, very good meeting. Thank you very much.
So thanks very much, Renate.
Great. Technical things. Here, if you're looking for the restrooms, I mean, this could be important. Just if you go outside here, this conference to the left, and then the next 2 doors are women and men. So the restrooms.
It's right beside the desk where you got the
badges
badge.
and also, probably all of them registered. And you, if you're a foreigner and you want to have access to the LAN network here, wireless LAN, then you also can get a key guest account and the password for it there. You have to sign up for it. I guess probably you also already got this, but in case you didn't, also just outside of the desk. And yeah, you see the coffee break will be here. Lunch break will have, there's a room over there, yellow room with the yellow door. There will be the lunch, and then we'll have to eat it over there and here, because around noon there is also a meeting in the in the green room over there, so we shouldn't talk too loud outside. That's, I just want to say. And in case of emergency, the closest emergency exit is over there. You know. Yeah, I think these are the important technical. Yes. And yeah.
Yeah, sorry.
Of
course, this was very important, and also Helmut, who has been helping a lot and making this happen here. All the physical stuff here at DWD. And then I also have to say to all of those that are not talking German, why we always talk about DWD when it is the German Weather Service. It's because it's Deutsche Wetterdienst, and as a German, you know it as DWD, and you can't do any other than say it like that. So I want to just announce that so everybody is on the same page. And with that, I want to also ask Vanessa and Frank on the stage. Vanessa has been, as Renate said, also one of the initiators and part of the Irene project, where I think together with the Americans that had the WFIP program, WFIP 1 and 2, and I can't remember if I don't get it, the wind, what was the longer name? I remember.
Wind forecasting.
Wind forecasting improvement project. These two projects were the first of its kind, where we actually looked into measurements from energy sources like wind turbines and solar. At the time it was wind that was predominant, whether we can actually use measurements in the weather in the weather models to get more information at the levels where that are important for wind energy. And it was a success, I think, and it was a disaster at the same time. A lot of things were discovered, and there was really there was a momentum, and everybody said we just have to get the data into the right quality, and then we can head off and improve the weather models. And that was 15 years ago, and we are still trying to close that gap. And I think that can be kind of frustrating, but it also has to be a motivation that we have to keep on trying, because we are now at a stage at that time, and now I have some Umbrian people here, it was wind power was noise on the system, and it's no longer that. And because it's no longer noise on the system, everything changes again. And it's like we start anew. And so therefore I hand over the word now to Vanessa. She is now Deputy Head of Meteorological Product Development and Distribution System Division. And that's a long title. And I think
As a large group as well.
the most important thing to remember about Vanessa is that she's very dedicated in energy meteorology and is trying to close the gap also inside the weather service to the energy, so that we can come together and she's one of the people that have made it possible that we can actually be here. So Vanessa, and then I'll also say a few words about Frank, because you will be changing maybe a little bit around, and Frank is head of the Department of Hydrometeorology and is dealing a lot with the climatology aspects of the energy systems. So we have the whole spectra here, and now I hand over the word to Vanessa.
Thank you, Corinna. And Frank is also very dedicated in this area, so this is not only the focus on me. I'm very thankful to be here and to present something, from the strategy or the strategic point of view to actual applications. What we at the DWD, and many actually say DVD, this is a very nice, a different kind of name for us, but it's a DWD, exactly. And I'm trying to give a little overview, as Renate also announced, to probably should do this, what we do at DWD, and to then focus more on, and the second part, Frank will focus more on a subject that is very important for this workshop. He will present analysis about Dunkelflaute, which is a German word that has entered the international, the international language. And let's start. I do this. How? So I think there have been activities about energy transition and being, towards the aim of greenhouse gas neutrality. But I think this event has actually triggered a lot, at least in Germany, in order to get into this renewable energy sector and to have a significant transition from towards the renewable energy sector and the gross electricity production I've brought here, that evolved over the last 15 years, so that we actually are at around 60% of the gross electricity production that has been accounted in 2024. Our goal for 2030 is 65%. This is also in line with the European Commission Green Deal, and I think we are on a very important and successful path. But that needs support from us, from our community, bringing meteorology and the energy system together. Renate already said a lot about our interdisciplinary research projects. The first one, called Eveline, was actually a very large project. We had several different smaller ones over the last more than 10 years. And these were very important for us because we had the chance to establish these partnerships and the collaboration between the weather or the meteorology and the power forecasts, the end users, which are manifold. And so we managed to establish partnerships from operational and academic research organizations with the transmission system operators and private companies to understand what is needed from us as the National Weather Service, which kind of data, which kind of services. And this was very, very important and dynamic time. I'm very happy to be been part of it. We also established interagency cooperations that focus particularly on the planning and monitoring of this energy transition. And within these research projects, we established this annual user forum, which brought together the entire community, and which is still working. So we do meet annually at DWD. And I think this is a very, very important meeting apart from today, to interact and to be in an exchange about the needs and the possibilities. Renate already said a little bit about the impact of these research projects on DWD, on the permanent activities. So we started focusing more on those variables, wind forecasts, radiation forecasts in model development and output. So we looked closer at the boundary layer physics, developed nowcasting, included more data in our data assimilation cycle, and worked on stochastic physics. So there has been a lot of activities around these research projects that also improved our forecast products and the models themselves. We also introduced new verification scores. We still are looking for those data, in particular in this boundary layer. And yeah, please come to us if you have those data. I won't be stopping saying that. And it has been included in strategic decisions on the level Renate is actually. So the main people deciding on things the DWD is doing. They are aware of this important topic, and we're trying to navigate the activities at DWD towards those goals. And I think in 2017, the DWG Act has actually changed and has been adjusted towards the support of the infrastructure, in particular for the energy supply. So we are by law asked to support the grid operators, for example, in order to meteorologically safeguard the infrastructure. And based on this, we had like Rückenwind. So we had more arguments to implement a sustainable energy program. Renate and Corinna also mentioned it already. So we're trying to, or the concept of this energy program is to have long-term development due to permanent staff that has time and resources to meet these the needs of the energy sector, and it's complemented by interdisciplinary research projects, and most of all based on partnerships I've been talking about already. Our grid operators as the key customers because of our act, of our DWD Act, but the energy service providers and the entire communities also forming the goals of this energy program. Also the ministries and governmental agencies for the planning and monitoring, and we're supported by by the what is called Ministry of Transport. So this is our actually where the money comes from. Okay, we are working with a lot of data at DWD. There's a treasure box to my mind. We try to develop in a way that the energy sector can use it, and we work with observation data, with NWP and artificial intelligence based forecast models, which I will be showing briefly. We provide time critical forecasts in various temporal and spatial resolutions. We also include estimations for forecast uncertainty, which is a very important topic for myself. I'm very dedicated to bring these forecast uncertainty information into applications, and we calculate reanalysis as a database for many different applications. We have climate models for seasonal and decadal predictions, and it's all available on our open data platform in order to foster innovation and make new product developments with our data at least possible. I won't go into detail. This is an overview about our ICANN model chain at DWD. I think the slides will be shared afterwards so that you can dig deeper into our actual system. There are many different setups in terms of temporal and spatial resolution and the forecast horizon, with different number of or amount of members for the EPS systems. And we have an icon art model, which includes the prognostic forecast of mineral dust. And we are actually working on an artificial intelligence based forecast model, which is called AICON. This is a very new development with a graph neural network model as a base for the model integration of the forecast. It's based on a reanalysis called ICON Dream. And we are actually evaluating this system at the moment. We are trying to understand the processes behind this completely new approach to model weather the weather forecasts. And we plan to publish the data in the first quarter of 2026 on the open data platform as well. That's our plan. For the climate data sets we are using, Frank will be talking about it in more detail. We use satellite data and WP models in order to get climatologies and do statistics for specialized applications. And the entire resort climate and environment, they look at monitoring and analysis for climatological trends, also for the energy sector, but Frank will be go into detail more. Just briefly, where we see ourselves as part of the energy value chain. So we support the process and the value chain by our meteorological data, the forecast data, and we focus on reliable forecast for critical weather situations, which is actually topic of this workshop, talking about extremes, and our collaboration with the public agencies for the planning and monitoring process with many different very high value data sets. During those research projects, we were working closely together with stakeholders to identify critical weather situations. And this is not only extremes in terms of very strong wind or things like that, but also we were focusing on weather situations that are coming with large forecast errors, which then makes it difficult to implement in applications. That's just for the overview. And our energy program we were talking about earlier, the people focus on the co-design of products and data sets in terms of optimization of model physics, data assimilation of planetary boundary data, analysis of climatological aspects for grid planning, for example, development of ultra-rapid data sets, so highly available or short or rapidly available data sets for nowcasting purposes, and the development of probabilistic warning products. So these are the main subjects we defined for the first phase of this energy program, which can be changed according to changing requirements. So about this workshop today or these days, I was thinking about the definition of weather extremes. What is it? So it's, first of all, from the meteorological point of view, the weather situations that threaten the energy infrastructure. And Gregor Pante, a very good colleague of mine, he will present more our activities in this session defining extremes this afternoon. Very strong winds, for example, freezing precipitation, and we are identifying more weather situations that fall into this category. Weather situations that challenge the security of the supply. This is, for example, the Dunkelflaute or the Hellbrise, so the opposite of a Dunkelflaute. And Frank will be talking about this. And according to our research projects, Evelyn and Grid Kaspar in particular, I think, forecasts for the energy during energy systems, so wind forecasts, radiations forecasts that might be associated with extremely large forecast errors might be an extreme as well, because it is then coming to extremes because of a forecast error in the metrology. And this is something I think all of you know, how difficult it is to deal with these forecast errors. And I think there are more interdisciplinary activities wanted and needed to implement necessary information that is helping to deal with these forecast errors. And now I'm handing over to Frank in order to dig deeper into the Dunkelflaute and the climatological aspects. Thank you.
Yeah, okay. When I first read the title of this event, I thought the typical thing when you talk about extremes in climatology in general, is having a high value of a specific parameter. But we have seen last year, at the end of last year, there was a strong discussion in the German media on having low values of wind. And you are probably aware of that this kind of extreme is also of interest for the community here. So there's this German word, Dunkelflaute, which I have now also seen several times in the scientific English literature. So it's actually a situation where you have low wind and low solar energy production. And it came up in Germany because we have an increasing amount of wind and solar in the energy system. So in the last year, it was around 60% of the electricity production. And therefore, there are also these groups who are not in support of renewable energy system, and they brought this word into the public discussion. But we received a lot of questions on that. Currently, our partners, the grid system operators, tell us that they don't have a real problem with that because they have sufficient reserve capacity in Germany to handle these episodes. But anyhow, there has been a public discussion, and that was caused specifically by events that we have seen in November and December 2024. So I will give you first a plot on the electricity generation in November 2024, and you see here is the 6th of November, where we had almost no production from wind, and only, as it is the winter, only also a very low amount of solar energy here. That was the case in November, and that was also once again the case in December at the beginning, and then also around Christmas here. So discussion started, and that brought a number of additional new questions to us, not only on the weather time scale, but also. I'll continue to talk. Just sorry. So I mean, that was a very extreme event here, and we also made an analysis indicating that it was the strongest event. So if we just assume the same energy system for the last 10 years, it was the most extreme case. So therefore, discussion started on, do we see an increase in the frequency of such events or in the strength of such events, for example, because of climate change? And then that brought us into the situation that the public press and also our partners were interested in having such long-term analysis. Vanessa already mentioned that we have a number of data sets here. Here you also have some of the links. These data sets are produced within DWD, but they are not restricted to Germany. So you can use them for applications on, let's say, as you see here on the African continent. This is based on the METEOSAT data, but it's a data set covering several decades. And we also have different reanalysis products. So for this analysis, we use the ERA5 data from ECMWF, but we also have the products that are produced based on the models of DWD. And for example, this COSMORIA 6 model, you see the domain here. This already has been used in several studies on the energy system. So We have written some reports on this study, but those are in German. But if you're interested, you can find them or can provide the links to these things. We also have an annual report looking back at the production, so the parameters of the last year, so wind and solar. To see the mouse here, okay, doesn't matter. Okay, so the typical situation in Germany is that you have a seasonal cycle of solar and wind. So highest solar production is of course in summer, but so the wind is complementary to that. But still we have to check whether we have, what about these phases of low production with wind in winter anyhow. So this is a long-term trend, but here, this is a situation like it's a few days in November. So you see that over Germany, you have a negative anomaly, so low amount of wind on the left. So so this is a specific day, the 6th, the most extreme day here. But what you typically see, you will see also this for the other episodes, that when you have the negative anomaly over Germany, you have positive anomalies over other parts of Europe. So this is a typical structure that we see because there is a typical weather pattern behind that. And that was also the starting point of the analysis here. So there was an approach using the so-called Großwetterlagen. It's a fixed term in, well, for describing weather patterns here. So this has been defined some decades ago. Here you see the reference to the paper. And so these are 29 classes of weather patterns. And then we had a master's thesis, actually, the author is here, Jacqueline. So where already a while ago, we tried to understand if there's a correlation between these weather patterns and the energy production. So here you see all the classifications, and blue is the amount of wind speed that the wind energy that you can expect. And the critical one that we are going to look at is the so-called high over Central Europe, hoch über Mitteleuropa in German. And this is typically what we already knew from these previous studies where we would expect a low production. And this weather pattern was also responsible in November and also here in December. So here you see how this classification is typically applied. So we know for each day in the year what weather pattern we had. And we can do this back for some decades based on the ERA 5 data set. So at the end, we can make an analysis if we see an increase in this weather pattern or if we see a longer duration of that, because those information would be needed if you want to, well, design for example, the reserve capacity or the storage systems. So this is a starting point for just counting the number of events. And here, you see the time series starting in 1950, just based on that one specific pattern. This is only focusing on the winter half year, so it's October to March. So you see the very high numbers here in the last winter, but you also see that the year before you had none of them. And in general, we have the typical variability that we have always when we deal with weather, but we see no trend here. So that was one of the important conclusions, that we could inform the public that there is no increasing risk of having more and more of these situations. So this is just a number of days, but also we had a look at the duration. So this is just the longest duration of those events that where this pattern occurred in a direct sequence of days. So again, we don't see that the duration is increasing here. We could say there's even a small decrease in the trend line, but it's not statistically significant. So this was also in the German press, and we still get requests on that. So this is an example of how we are using these long-term climate data sets for, well, understanding this kind of extremes. And yeah, I will draw first conclusions from that part. So I already said this. So the an increase in frequency or duration is not observed, but this meteorological information also suggests that it could be of interest to discuss exchange of energy in a cooperation in Europe. But I'm also aware that this is just our meteorological point of view. Of course, designing an energy system is of course a number of challenges here. And we just last week, we had the so-called Extreme Weather Congress. I should, hier sind die Leute, die noch eingelassen werden wollen, soll ich das machen? So there are more people liking to join. But so last week we had a discussion with colleagues working at the so-called Universität der Bundeswehr, so interested in security in Europe. And of course, having these cables from northern Scandinavia to Germany is also a security issues nowadays. And therefore, so there you see that we don't only discuss this with partners directly from the energy sector, but there is more political issues on top of that at the moment. Okay. And this is a summary of the whole talk. So Vanessa, maybe we get some questions on everything here. So you have seen that the renewable energy sector is a key customer of DWD. So for weather information, but also for our long-term climate data sets and analyses. So yeah, we are open for questions.
Thanks a lot. For this very interesting presentation. I would like to move the questions to the end, but while Martin is, our next speaker is preparing himself and Helmut is changing the presentation, I would like to take one or two questions if there are any. There is one here, yes?
Yes, thanks for the talk. And what I'm a bit interested in is we are users of the icon data and we download them from open data, DVD, which is it's tremendous to have access to this model output. What is a bit a challenge to us in using it for energy applications is that they are in the crypt2 format and our access pattern is mostly time series based. So we are interested in time series for a single location. So we have to download a lot of crypt2 files. It's a huge amount of data transfer. And so I'm interested in whether you have it on your radar to provide them in a more cloud native format, I would say, like a SAR store or something that is more readily chunked for different applications where it's easier to query, for example, for time series.
Yeah, I can say yes. And actually, as we speak, there's a colleague of mine developing an API for at least a subset of the NWP data set in order to start with a minimal viable product, actually. This work is done within a large project or program, another program at DWD called Digital Transformation, and it's focusing on the on data lakes, develop data lakes, and to have modern distribution systems and APIs for the end user. So we do develop it, and we hope that we can provide at least one model, the icon RUC, the rapid update cycle, also at the beginning of 2026. So it will be a first playground, and to interconnect and to use this kind of data provision. But be a bit patient.
Thank you for your presentation. I have a question. Maybe it's a bit too early to answer, but do you think that AI will have the potential to improve extremes compared to all the other panel of models?
I think we should talk to the yeah.
I'm neither an expert on AI, but I would say one problem with AI is that actually it it focuses on the average weather. So it could have more problems with the extremes than the regular numerical weather prediction model. So that's yeah. I don't know yet. It has to be investigated, but yeah.
And I think these evaluation exercises we do for the next few months at least, or yeah, continue to do so. But it's actually very, very important for us to understand the data set before we publish it. And this is one part of the research questions we actually try to address in the next few months.
So I'll get you to the stage afterwards again, because this is actually a good question to start a really an interesting discussion. But I would now like to introduce Martin Stensdal from Energinet, our second keynote speaker. I think everybody knows Energinet. I know it also as ELTRA back in time. They have also been helping companies like ours to get into forecasting, and but Energinet has always been ahead of things, and that's of course also because Denmark is in a very favorable position in the world. If you're a small country with large countries surrounding you, your playground is bigger and nicer because you can push your problems easier away and to your big brothers. But we do need these organizations, those that maybe have it a bit easier than others, because they push the boundaries, and that's why I'm extremely delighted to have you here, Martin, today. You are working with balancing and you're working with forecasting tools. So this is exactly the kind of knowledge that we're looking forward to hear a little bit about. So the floor is yours.
Thank you very much for the very nice introduction. And actually, I think it's a very fitting introduction, most of it, that we are a small country. And Energinet, the TSO, has had some luck with implementing a high level of renewables in the electricity sector in Denmark already. Last year, we were above 80% of renewable energy in our electricity sector. We are aiming at and expecting to be 100% in 2030. So well before the EU requirements. Really quickly, my name is Martin. I work with balancing. I'm here with my colleague Mads in the back on the left-hand side. I'm from a more market perspective, working with how do we ensure the right level of balancing, the right level of security in our grid, where Mads is one of our experts in the forecasting division, so actually developing and doing these in-house forecasts. So my idea here today is to take it a bit, higher level than these very narrow forecast views, and really give you a view on how do we use them and how do we expect to benefit from better extreme weather forecasts. So just give you a perspective of how it's used in grid operation in Denmark. Really quickly, Energinet and Denmark, small country. We have a peak demand of around 6,000 megawatts, maybe 7. And one of our special characteristics are that we're very well interconnected. So we have a lot of big brothers that can help us when we're in trouble. This also lets us develop. We have the west coast over here, the North Sea, with a very high wind potential, which we've already developed a bit, and there are a lot in the pipeline to expand on the wind sector. Coming along with that, the last couple of years, we've seen a large increase in solar PV, which means that we've reached this very high level of renewable penetration and all the problems that arrive with it. Luckily for Energinet, we have a very progressive, I'd say, leadership that allows us to push the boundaries of how these security calculations, how do we maintain a proper what do you call it? Level of security of supply. So I want to go through some of the forecast-based methodologies that we use to give you an insight on how we still need to implement extreme weather, extreme events, and some of our thoughts on how these already play a tricky role in what we do. Yeah. So the 3 points I want to go through today. There are, of course, a bunch of other ways we use forecasting in Energinet, but one of our new ways of using forecast is the dynamic reserve dimensioning. So historically, we've had a static reserve dimensioning where we procure an insurance in reserves, same amount every day, every hour. Now we've moved on to dynamic reserve procurement, where we every day forecast what is the probability of needing a larger or smaller amount of these reserves. Of course, it comes down to the Benjamins, everything, like we have to procure this level of security at the most cost-efficient way. And this is our idea of doing that. Secondly, I want to talk about security calculations. These are done every day after the market clears, even before, taking into account all these grid operation incidents that may have happened. We may have a big power line out for maintenance. So doing these security calculations ensures that the way we expect the grid to be in the hour of operation is actually feasible. Lastly, proactive balancing. This has been the philosophy of Energinet for many years now. But the way we do it is we try to forecast close to real time what is the imbalance going to be, half an hour, 15 minutes. And in that way, we can procure our balancing reserves, the energy activations, cheaper. We can activate more efficiently and hopefully socioeconomically optimize these balancing challenges that we may see. Yeah, so moving on to dynamic dimensioning. Just to give you a quick idea of how it works. In the graph down here, you see the yellow line, which is a historical way we've done dimensioning in Denmark. It's calculated on like a year's worth of data, and that sets a probabilistic level of security for the Danish grid. But as you see, the pink line is the actual need in those hours. And of course, just because you exceed at some points doesn't mean the entire grid is going to fall together, but it does increase the risk of this happening. So what we've done with dynamic dimensioning is we take a bunch of inputs into like our own model that evaluates, is there a greater need in the up and the down direction, both of them, which is then the blue line. Which means that at a lot of hours, we can procure less than the static methodology and still achieve the same level of security of supply. This was implemented at the start of 2024 and has been a success. We have saved, looking at the money again, we've saved a bunch of payments for unnecessary reserves. Of course, you still see at some points the pink line will exceed the blue, but most of those, the blue is actually higher than the static methodology, meaning we've actually achieved a higher security of supply going to dynamic. And not to get too specific on how this is done, because I'm not the expert on that part, but it's honestly a relatively simple Bayesian model that gathers these different grid scenarios in clusters, and then we take a certain level of security on those, like what were the highest need in those hours. And this was what we implemented in the beginning. We did this forecast D-1, so the day before in the early morning. But of course, as everybody knows, as you get closer to the hour of operation, you'll have a clearer picture of what's going to happen. So we just started, implemented secondary auctions So after the market has run, if there are any capacity and our forecast now tells us there's a greater need, then we'll procure some more. The final idea of this methodology is that it's a continuous market that we really upscale, downscale as we receive new data for our forecasts. But getting back to extreme events, how does extreme events really impact this forecast? It does in the way that we receive, we have it in our historical data. We have this simple Bayesian model where historical data really sets our level of security. But as, at least from our perspective, these extreme events, the first thing that comes to mind for Denmark is these storm shutdowns. We have not seen any of these in a severe case yet. We've seen some indications that it's happening, but it's been we haven't seen a lot of this, which of course impacts our methodology, because then if it's built on historical data, we won't see this level of insecurity. Also, right now, the forecasts are made some time before, maybe day before, where we see that forecasting these extreme events accurately that much time before is difficult. And again, trying to optimize socioeconomic, procuring a lot of reserves for these periods of time where low certainty extreme events will happen is not deemed feasible at Energinet. So really the big question about dynamic dimensioning is this the right place to include extreme events? It's still being discussed inside Energinet, and it's one of those nuts that's hard to crack, whether this is, if extreme events should be considered in our reserve dimension. Yeah, but my thought was to put that in your heads and just to have the thought about how we view these extreme events in our reserve dimension. Moving on to the security calculations. I've just quickly brought this one because I think it's one of the more interesting ones when it comes to extreme events. Maybe you saw it on one of the first slides, that this is done more or less continuously with new updated information, mostly about the grid. Over here you see like a schematic of the west part of Denmark grid. It's not really important what it says, but this is like the transmission high voltage lines. Then we get from each of these nodes, we get an expected production, consumption, and some other information that lets the control room calculate if operation will be within some security parameters. These are heavy simulations that are run in, it's called Power Factory, trying to simulate the entire Danish grid if operation will be secure. So of course, simulating all possible outcomes is not feasible, as that requires too much simulation power. So getting higher quality updates on weather dependent technologies will really both ensure that we do the right simulations, and it will save us resources in these security calculations. Yeah, that's what I said here. That in this case, getting a higher accuracy will definitely be of big use for Energinet and the control room. Also here, we don't have this same floor that dynamic dimensioning has, that it's being used from a long time before the operational hour. So I see a definite use of better, more accurate extreme event forecasts here. And lastly, I want to go through proactive balancing. So this is also one of the new, well, at least we have introduced, this is called MFR are energy activation market, where we have went from a manual activation from our control room staff to an automated activation that is being controlled entirely by an algorithm and forecast needs. And as you can see down here on the right hand side, the blue line is the expected activation that you want to cover, and the green line is the actual activation of these reserves. So most of the time we hit the imbalance quite well, but of course it can be expected that if a extreme event, storm shutdown, or yeah, you could expect solar eclipse. It's not really that hard to estimate, but let's just play with the thought that it wasn't. Would change these blue lines very quickly, very rapidly, and put our activation way out of line. So what we see here is the need for accurate estimations at the very short term, very near real time. And secondly, the inputs to this forecast are, of course, changes in weather, demand levels. All of these we make in-house. But one of the most significant ones are the balance plans from the balance responsible parties, so the owners of all the production plants in the grid. They send us their expected production. And one thing we see as a developing need is that when these balance responsible parties get their forecast data from the same manufacturer of weather data, we see that this harmonization of weather-dependent production, the forecasts, really can create an extreme event without there being one. We have seen an example a few years back where wind front was supposed to hit Denmark, and these plans from the balance responsible parties all said, yeah, the production will ramp up very quickly within a certain hour, but it didn't happen. And it led us to the biggest imbalance that Denmark has seen during an hour across many balance responsible parties, leading us to investigate that almost all of them used the same producer of weather data forecasts, leading to the same error in forecasts. So I really see that this harmonization of using the same forecast as a challenge in the grid in the future. Yeah. We just to give how we do it, we use at least 3 different forecasts, and then have some internal check that if all of them say the same, it might be true, but we used to really mean the forecast from these 3 forecasts. So to wrap up on these just these 3 things that we use forecasts to at Energinet, by closing some of these gaps, I believe that we'll have a more reliable, efficient, and cheaper operation of the grid, which of course will benefit everybody that are using the electricity grid. So if we can get knowledge of extreme events in better quality at a long forecast horizon, we'll be able to do this risk assessment more accurately, which will lead to a lower reserve procurement cost. Knowledge about time and place, also near real time, will let the operators handle these situations more effectively, leaving more room for other events. And then if we can tackle this harmonization of forecasting of the providers, then we can ensure that this doesn't become another weak link in the green transition. That's all I brought. So thank you for your attention. I look forward to more talks later on.
Yeah, thank you, Martin. That
Thank you.
was very interesting. Is there a question, a quick question here?
Yeah.
Yes, thank you very much. Thanks a lot for the talk. Me myself, I'm working with seasonal forecasting for a renewables company. I was thinking, do you consider at all or not really a forecast on the seasonal scale, like 2 months in advance or a month in advance, or you do not consider this as you don't, maybe you don't need it?
We do consider this. These are made for some of our long-term forecasts, mainly for energy adequacy. So if we will be able to supply the demand that will be there. We also try to forecast the demand in longer timescales, but to my knowledge, these forecasts are still quite based on historical data. So what have we seen the last couple of years? We already have quite some substantial data, but yeah, that's the way we do it right now. Thank you. Yeah. Yeah, go ahead.
Question based on your automatically activation of MFRR. So if you're using forecast data and the balancing groups are also using forecast data, how can you be sure that you know that if there will be an imbalance in 50 minutes when the balancing groups should also know that they use the same forecasting?
Yeah, good question. That's again back to the philosophy of Energinet in balancing. We believe in that a centralized activation of balancing energy is more efficient than sub-optimizing at the BRP level. So what we do is that we allow for imbalances at the BRP, and if they can forecast them themselves, they send that data to us. We will have an imbalance, so that's fine, as long as you also offer the flexibility for the MFRR market, the AFRR market, for us to handle it at a centralized manner where we can, socioeconomically optimal handle these imbalances.
Thank you.
Very quick, Alex, because there are a number of questions that, but I would like to have them at the end. But if you make it very quick, we'll take it.
Yeah, sure.
Just a question on the 10 and 90% quantiles. Did you determine them by a means of optimization, or is it dictated by law?
Yeah, it's a historical value. We've used that for a long time. I think it's defined in it's called SOGL, the System Operations Guideline made by the NSOE. So it's a value defined for us to use. Yeah.
Okay. Thank you very much, Martin. And we'll get to the question. Because we have a third keynote speaker, Detlef Siebert from SEtrade, and talking about small and large. Detlef is founder and CEO of SEtrade, and he's coming from a large and has started a small, and that is now growing. And I think why I invited Detlef is because he's always coming with some visionary thoughts that are thought-provoking and that are changing our ways of looking into the market, and the optimization of the market is always something that almost in every discussion comes up. And I think this is something that we want to have here, thought-provoking and provocative, because this is what brings up good ideas and brings us further and pushes these boundaries. So Detlef, I'm very happy that you're here today, and the floor is yours.
Yeah, thank you very much, Corinna, for the introduction, where I really was a little surprised to be here and to speak to you. But I take this opportunity to get a little bit more from the energy forecast itself to the euros, because I'm a trader. And I started being an energy trader really 25 years ago here in the surrounding in Frankfurt, because there's the headquarter of the DB Energy. So the energy producing or trading company, a subsidiary of the Deutsche Bahn. And I got, as a young engineer, the possibility to have the project to bring the balancing group management into this system. So it was quite new, 25 years ago. So I had and I'm not allowed to make the proof at the plants of the DB Energy. So I had to, let's say, acquire first German industry clients to bring it into the balancing group of the Deutsche Bahn, to have that proof. And when it was working, then we shifted it over to the plant from the DB Energy. And so then we terminated 22,000 energy delivery contracts and bring it then to the main portfolio of the DB Energy. And as it was then into the portfolio, we need to have, let's say, the energy source. And then in the same time, the energy trading market was founded in 2000. And so as an engineer, I was the first, let's say, being part of the first, let's say, lesson where I get an energy trader. So this is the reason why I do not have an economically background, so I'm an engineer, but I'm working as a trader a very long time. And this is the reason why I want to introduce myself a little, because now I'm very happy to bring my knowledge of the last 25 years into the current situation of the energy market, which is really a pity a little. And so it fits very much to the weather extremes we are talking about. And I was very happy to see that you, Frank, talked to us with the Dunkelflaute extremes in November last year. But in my point of view, a very much more dramatic situation we had at the 3rd of June. Because it was a situation last year, it was a banking holiday weekend, and as most of the traders are working in the day-ahead market, so the day-ahead auction market, they stopped in their trading at Wednesday, the week before. And on Monday, we had the situation that we had a weather extreme in the southern of Germany because of heavy rain. And we have a flooding situation on Monday morning. And then we've seen that the order books in the continuous intraday market was totally sold out. I've never seen this in the last 25 years. And so we had weather price peak, energy price peaks up to 10,000 euro per megawatt hour, which is the defined borderline. Otherwise, it's getting higher, each higher. And the same was to the balancing prices, which really ended at 15,000 euro per megawatt hours. And this was just only event of 2 hours between 8 o'clock and 10 o'clock in the morning. But it costs millions in the energy industry, in the energy trading markets. And this is the reason why I want to get you a flavor of my everyday business and what is maybe the requirement out of my daily business to yours. So Corinna introduced me as a founder of the new company. Yes, I was part of very big companies, but when I became 50, I decided to make something more what I really, let's say, what's really an impression from myself. And this is the integration of the energy into the real business to set the energy transition to a success story. Because all the companies I worked for before, they do not really get pressure out of it. Because it's just only a technical thing to integrate something as we heard it in the past, but really to make it as an economical success story. I can't see really the pressure in the market out of it. Because at the end, we have to fulfill the situation and the gap that the energy production do not fit to the energy demand. And this is the most important thing we have to find solutions for. And this is the reason why I thought it was a good possibility to integrate AI solutions to fill this gap, which is not in the business yet. And this is what we are doing here. This is a small, let's say, graph of that, how we are working. So in the middle is our trading platform, which is AI-based. So it's a trading AI-based algo trader, which is, let's say, trading a couple of 10,000 deals a day. It's really heavy trading in the middle, but to get a couple of 10,000 orders a day, you have to have an intermediate, because a real plant like an energy consuming industry company or a charging station or battery packs or CHP plants or wind or solar farms or hydrogen electrolyzers do not itself, they are not creating orders for the stock market. So we need to have an intermediate to fulfill this. And this is something what we are explaining as a digital twin. And these digital twins is this what we are doing, what is the heart of our company, that we, and I found very talented, let's say, developers, IT developers, who are able to transform physical plants into an AI-based digital model, that they are in the 24/7 manner are able to trade or to fulfill this need for the algo trading in the middle to create these orders. So, which is very easy to understand when the market prices are get negative. And I know I have several of megawatt hours as a free capacity of batteries. I know to have the situation, how much capacity do I have as an aggregated manner for all the batteries which are, let's say, all over Germany. And then I can pack together it to one order. And then I'm able to buy or to purchase this order with a negative price. And then I have to deaggregate it as, let's say, as an piece by piece, let's say, order definition, how much megawatts then the battery has to load when I bought the energy. And this is what we are having here in between the digital twin and the real plant in the field is, let's say, a real-time interface talking to each other every day, every time. And this is in a 24 hours real-time manner that we always have the situation by getting the real data from the plant and setting it out, the forecast in the future, how to drive these plants. And this is how we are working. And there we can integrate now, let's say, the energy forecast, the weather forecast, the price forecast, and with the free capacities of these flexible market components, we are able then to optimize the energy costs for the clients. And this is what we are doing. At the end, we need to have better energy prices for production plants, better energy prices for industries, better energy prices for the bankability of the investments. This is at the end, the most important things. And we try to support these and to integrate your weather forecasts and our price forecast with, let's say, a well-done digital twin to optimize the real plants in the field. And this is just a little joke by asking the most important AI or the most, let's say, well-known AI, ChatGPT, what he is thinking about how a digital twin can look like. then this is the picture out of it. So it's just only something like this. But I pasted another slide in. This is this heat map of the energy prices in the day ahead auction last year, and this is what we are talking about weather forecast and the price out of it, and how to deal with. So whenever in the heat map the prices are red, we have then a very high beneficial possibility to sell energy, and whenever the period of the field is blue, it's better to purchase the energy. So, and we have to make this possible, and we try to have then always the best solution for the clients. On the one hand, the producing clients, to bring them from the blue level to the red level, and opposite for consuming companies. And this is what it's meant like flexibility. But end users are not flexible. Not at all. Nobody of us is flexible in energy use, because every day we wake up at the same time, we're cooking our coffee at the same time, we're using the energy. And mostly now it's dark outside, so the price is high, but we are not changing our way of using energy. And industries are not doing this. Private householders are not doing this. And this is the pity of the market. So, and it is the same absolutely clear understanding as it was in the past. The consuming company or the consuming part who is able to consume the energy as the production is in the same way gets the lowest price of energy costs. This is the reason why steel plant operating or aluminium plant operators acted in a way of band load or base load consumption. They got in the past the best price because they are worked like the production of a nuclear power plant. But they shut down. Lignite coal-fired power plants shut it down. So now we want to have integrated 80% of renewables up to 2030, but the logic is the same. The one who is able to consume the energy as the production power plant is producing it will get the best price. So the question is how to get flexible, how to get the clients flexible. And the answer is the flexibility as in with storage facilities at the end. But meanwhile, it's also a transition period, because these flexible components, the storage facilities are much too low in the energy business now at the moment. And this is the reason why we have both. We have these weather extremes and we have these price extremes. And which is the pity, because this is the reason why the industry are leaving Europe at the moment. And we have to stop this situation, and we try to have, or we have to have solutions out of it. And this is something what we have to discuss here also. Okay, so two pictures which are completely common, and everybody knows how a PV plant is looking like and how a wind farm is looking like at the moment. But this is the problem. The efficiency of these kind of plants, because there were in the last 20 years built it in the energy EEG law in Germany for the subsidies by law to integrate renewable energy in the market. But the problem out of it is that the producing companies are working like produce and forget. They do not have in mind who is my client, who wants to get my energy, and who is able to pay for it. And when is he able to pay for it? So we are creating an industry, and it's the only industry who don't care about the product. Nobody is caring about who is my client, is he willing to pay for it? And when do he consumes my product? And the energy business is totally logic for the whole of industry who's producing any kind of product. In the energy, this is not a problem. Nobody cares about it. And this is the pity at the moment. And this is the reason why now when we achieved 60% of the share of the energy production is now renewable, happy days, of course. But now we have the problem that the production in this is in the same time is that high that we see more and more and more negative market prices at the moment. And this is what I, of course, want to explain once again, and you are well known of these graphs, but I decided to bring it once again because the colleagues from Agora Energiewende and the Agora Meta is very good for the visibility of the problem in my point of view. So this is a reason I decided to show you this graph because I want to shift over then to a real plant in the next slide. But this is the situation from the last 2 weeks in June this year, when we had much more integrated renewables than 60% in the energy. You see it here in the downside, the green field is the production of renewables, and the gray ones were then for conventional power plants. But above, the very important thing is the red line, which is very small, but the red line is the demand, of course. And all the others shows the real production. And whenever the gray peak is above the red line, then the production is higher than demand. And whenever this is happening, then the prices are down. And the black line here is the market price at the day ahead 1 hour auction for these days, for these 2 weeks in November, in June this year. And I put the line where the price is, you get energy for low. So for €0 per megawatt hours, I put it in the very fat green line. You can see every day, nearly, instead of 1 day here, and this was where here I don't know, it was the 27th of June, where the production was really a little bit low because obviously we had a rain day at this day. But every day, the other days, we had negative market prices in the field, which is good for the industries, of course, when they are able to use it. But a pity for producing companies, of course. And this is what I want to show you what happened with a new plant which was installed in late November 2024, which is our client. And this was in the same period of time, the production of this plant, because it is under the act of the solar peak. So in German, Solarspitzengesetz, which means from the very first of negative market price hour, they get no subsidy anymore for the energy production, which means as an energy trader, we have to shut them down. So whenever you see here in these periods, this is in the morning until the prices get negative, we allow them to produce and then we shut them down. Until the evening time, when the prices get a little above €0 per megawatt hour, then we shut them on again. But you see, as let's say the amount of energy which is then they are able to produce is really only just a little. And then in addition to this are the purple fields we've seen here. These are the events of redispatch. So this is another event where the plants get shut down from the DSOs at the in the field outside. So and whenever the prices are not negative, it's very likely that the grids are at the top, so they have to shut down these for redispatch reasons. So at the end, you can see the plant is not producing, let's say, maybe like 20 to 30% of the expected volume. The plant is really operating, and luckily, in the purple fields, they get their subsidies again. But if they are not in a redispatch event, they get nothing, really nothing. And what does this mean is at the end, well, now, sorry, but a little statistics that you get a flavor in which direction the market is going. I show you the events from January to mid of or end of September, as we have now. In the last 5 years, how much negative price events we've seen in the market. And you see, okay, there was in 2021, I start here, we had events like 139 from January to end of September. Then we've seen 22, this was the event of Ukraine crisis, as we have this shutdown of the nuclear to the natural gas transportation. So the prices were quite high. This is the reason why we can, let's say, terminate this graph. But in the year's event of 2023, 4 and 5, we've seen we have exploding events of negative prices in the market. And now we have events in 25, and the year is not over, that we see 525 hours where the price is negative. We say, okay, we have seen more than 6,000 hours this year. These 500 hours is not that a big event, but we've seen 2,162 sunshine hours. And out of these 2,000 sunshine hours, we have 510 negative price hours in these periods of time. And as you remember what I've seen here, these hours where they shut down is not the hours where the production is low. So it's always when the production is very high of these amounts. So it means that in 25% of the year, when the sun is shining, the plants will be shut down. But at the end, it's not only 25% lower energy production. At the end, it is more than 40% energy lower production, because it was always the shutdown in the peak times. And this is the real pity at the end, because this is, I want to extend a little, because this is only the statistics for the day ahead auction. As you may know, that we have several spot markets outside. There's the auction price, where the whole market is fitting together to bring one market price for each hour. And there's another one, this is the continuous market, where you can have directly orders in between two counterparties. And there, the negative price events in this year was even more than 600 hours in this year. So it's increasing the problem in the continuous market. And this is really a fit or a requirement from my speech or from my keynote this morning, that we have the expectation of the math and the feed-in forecast industry or providers, that we get more information about the price situation. How much impact do the weather extremes and the weather forecast and feed-in differences will impact the price solution and the price developments. I show you two examples of the September this year. It's just only picked out two days, and this is not, let's say, a very special day. You see here the price information. The blue line is the day ahead 1 hour auction. Sidestep, which is now the history, because now today is the first day where we do not have the 1 hour day ahead auction anymore in Europe. So the first day we have the quarter hourly day ahead auction, because yesterday it was the last remaining 1 hour auction. So it's just only a sidestep, because it's now a new area we are stepping in today. This is a historical thing where we had these 1 hour day ahead auction. And you see in the first example, we've seen that the intraday prices were always below the day ahead price. As a trader, you've seen ahead to sold out every energy production in the day ahead market, and opposite for all the consuming companies, we had to purchase the energy in the intraday. When I do it well, when I get the information out of it. And the better the forecast is, the better is the beneficial situation out of it. And the opposite is here. The other day, we've seen much higher intraday prices as the day ahead price forecast. And this is something where the information from the feed-in companies where we are buying the forecast is much too low. And it's absolutely necessary that we get the information, because we are running into a big problem, because all these new plants under this Solar Peak Act, as I said, we will see a dramatic bankruptcy wave in the very near future. And this is really a tragedy for the whole energy business, because we will then see leaving the trust of investors, trust of people who are willing to invest in windmills and in PV plants anymore. And of course, those who are not willing to see the energy transition succeeding will be happy out of it. And we can have, let's say, help to get a better beneficial energy, let's say, trading by better forecasting, by using more and more the energy prices out of it. And this is one of the most important things we have to keep in mind, that there's, at the end, the weather is like the weather is. And then we get the forecasting for the generation out of it, of course. But at the end, we have to see in the causal chain of this logic, what impact do it have on the price? And when it's better to go for the traders into which market, for the consumption or the production sides, in the auction field day ahead, or in the intraday market in the continuous side. And this is very important. And this is what I hope that we will a little bit get out of this workshop today or in the next 3 days. Don't stop thinking about megawatt. Thinking more about the impact on the market price in euro per megawatt hours. And this is what really is the most important thing to secure and to save the energy transition at the moment. And therefore we need, of course, much more, let's say, information. Because in Germany, of course, we have the big problem of the gusts in the wind industry and the ramps for wind and solar things. We have to have much more better forecast. And when we've seen these ramp alerts, we just only don't have the impact on the megawatt. So we need to have information in what does it mean in the energy price in euro per megawatt hour with the delta megawatt in delta time. So because all these gusts we've seen every day shifting by hours in the latest or in the front, because we know day ahead there will be a gust next day, but when exactly we do not know. And this is the reason why we have to always sell and buy back the positions by shifting these gusts every day. And so we have sometimes we have to trade this single gust 3 or 4 times. And in the end, it's going 50% into balancing energy. And this is, let's say, where the whole industry is losing money and money. And this is something we can, let's say, you can help us to get better feed-in prognosis, better ramp alerts, and of course, to learn what does it impact into the energy price. And this is, let's say, my call to action to you as in this workshop to discuss about this and find solutions for us to have a better trading and a beneficial production at the end, the bankability of the plants for the investors. Thank you very much.
Thanks a lot, Detlef. Just stay here for a moment.
Okay.
We also we start with some questions. You have had one, so we take a new one first till you get inside.
So you're telling you have a lot of problems with these forecast errors and wind gusts and so on. My question is, do you have an in-house meteorologist to look at the forecasts? Because in my experience, all these wind and solar forecasts are seriously flawed in certain weather situations, and it can easily be recognized by someone with some experience in the field, and it could really help in trading.
Yes, of course, we do. We do have.
A little bit closer to the mic.
Okay, sorry. Yeah. Yes, of course, we do have this experience in-house, and we try to find the best solution, but it's not the best. And the more information we get, and the more, and especially for the DWD as a big organization, getting the most and the best information regarding the grid situations and so on and so forth, get the best solution out of it, or the best results out of it, in my point of view, because we are very small trading company, and we are not able to, let's say, install this own capacity. And every trading company is, let's say, forced to do this. But the question is this beneficial? Make this sense? Or do we get, let's say, more and more data to help our lives, let's say, to support our lives more easily? Because at the end, everybody will gain out of it. We'll get the better information out of it.
Thanks for the presentation. Actually, the situation you described is very important, and it marks a kind of change of paradigm in renewable powers forecasting. And we discuss a lot also in France with RT and other actors this question of negative prices. And maybe it becomes more important even than extremes, because extremes, what we define as extremes, have a small probability in time, but what you showed appears every day, actually, and it's a very different situation. And what happens is, what I would like to point out, that if we have this wind PV plant, what we observe is what you showed as time series. I mean, the plant has to stop many times. Don't forget that the power forecasting models are regression models that are based on the historic time series. So the quality of the forecast will really degrade when we try to train the models using this kind of time series. And it's not only this, because today we have seen also that there are other external factors that impact forecasting, like, for example, regulation imposes to have systems for detection of birds. And we have a case in France where one wind farm was, in 1 year, there were 10,000 stops of wind turbines. So this adds to this kind of situations. So we are in an area, I mean, in a time for renewable forecasting where actually it's more important to forecast the contextual information, rather than the real process that drives the phenomenon actually.
Yeah.
And a question, okay, you said that many companies are going to go bankrupt, but we're not, I mean, how many PV plants have to go bankrupt that we don't have this exceeds of power? So probably when they go bankrupt, so there will be a point where the negative price will disappear, no?
Oh, yes, this is the solution. Yeah, thank you very much. No, yes. Luckily, we've seen not yet the bankruptcies, but they are coming up because I have the discussion every day because banks calling me, clients are calling me that they are getting in big trouble because they can't pay for the salaries for the banks anymore because the energy production is too low. And this is what always or only new plants which are installed last year are let's say are targeting, because the Energiespitzengesetz, so the Energy Peak Act is active since 2023. So now we've seen that the plants are installed, and this is the first summer they get out of it. And even after the first summer, they get in big trouble. And we are seeing that a lot of big plants and the new plants are coming up are not having 2 megawatts. They have 20, 40, 50 megawatts in production. So they increase the problems of redispatch. And of course, the installed, let's say, investments over there are that high that we will see this situation coming up very soon next year. This is what I'm seeing at the moment. And this is really a pity. And this will be, let's say, really a political discussion coming up, and where we can find to have solutions first, to help them secure, to help them survive. And I try to push this and force this with my small company. But of course, you all are part of this business, to find better solutions for the forecast, to get when and where is the better market price to secure this, and to show that even we find solutions for this really very, very dangerous problem at the moment.
This can show that the market design is not appropriate for.
That's correct. I also wanted to say that it's the market design, and in Germany especially, I think it is the missing rollout of smart meters, because what we see in Denmark, for example, where there is probably now 80 to 90% of the population is in dynamic pricing, and people do change.
Yes.
Become flexible.
But yeah.
So there is a change happening. It's not from day 1 to 2, but there is, and I think that's why we have to come together in this interdisciplinary forum to discuss these things, because better forecasts do not help a wrong market structure.
And then the strength and the strong, how the DSOs are really stopping the events when PV plant operators are willing to let's say invest additionally to the PV plant in the battery, and they get stopped by the DSO. It's really a pity as well. So they want to get more flexibilized. They want to do their things. But the interdisciplinary things and the interdisciplinary mindset is not that there. And we've seen this situation. And I just wanted to talk about this.
Yes, that's great. So there was one more question.
So I think what you just mentioned was a good layup for my question, at least. So thanks for the presentation. We see a lot of the same problems in Denmark, at least with the solar park shutting down 80% of the days that are actually sunlight, if there's any windows. But But what you mentioned this about the flexibility of the consumers, where in Denmark we see this quite a lot, at least in the past 2 years, because the electricity prices has been very volatile. They can be very low negative prices in the middle of the day in the summer, and then they can go extremely high during the winter. I had a colleague that said if you were charging her electrical vehicle during the day, it would be maybe 10 euros, and if it was at the most expensive time, it was 100 euros. So because of these volatile prices and the huge boom there's been in electrical vehicles in Denmark, we see people actually started to become flexible and adjust to the prices. So I'm not sure if there was actually a question in here because we probably answered it based on the market situation.
Yeah.
Thank you for your inspiring presentation. My question is about importing, exporting energy into the neighbor countries and to which extent that could be a solution. And you are dealing with in your current position. Thanks.
Yeah. So to answer the last question first, now we are not trading the across the border lines, but import and exports are very important. As the colleague from Denmark is saying, this is one of the most important things across the Europe, that we help us each other, that we see that we have the interconnectors and that we are not alone with the problem. But this is not the main solution, because of course we can export, let's say, all the produced energy to the Alps, into the pump storage facilities over there, or to Scandinavia, to the pump storage facilities, but it's not enough. We need to have the flexibility here, and every client has to think about the flexibility. As you said, yeah, the price, let's say, volatility has to be a driver of, let's say, getting the demand more flexible, to find solutions for it. And this is something we can, let's say, have the solution for our own, at home, in our company we're working in, and for the area we are working in, the Stadtwerke area, and so on and so forth. This is what we have to make first. And this is what we try to do, yeah, to get solutions in the regional areas, and then at the end we can export it to the next region, and then at the end of this chain is then the import and export. But to find solutions in the field, for every industrial client have to find to integrate batteries in their production processes, to have, let's say, shifting their production a little, or finding more flexibility in the energy demand in their cases. And this is what we try to achieve with the company, because it's a smaller one. But then, of course, it's getting wider at the end by making this homework in the decentralized manner. Then the import and export problems getting lower, of course.
Okay, so thank you very much, Detlef.
Okay.
And now the clock, we had 5 minutes for our networking break, and I have at least 5 more questions on my notes. We have to keep the questions and write it down and discuss it in the break, or otherwise we're running very much out of a time schedule. But I think it was a very interesting keynote session. Thank you very much for the keynote speakers. And my suggestion is that everybody is fetching some coffee or water or whatever you like, and then we come back in directly to our place and start the next session, and just take the coffee break while we listen to the next talk, because then we can discuss some of these questions along the way. And I'm sure that a lot of the questions that already have come up, they will come up again, and we will be seeing here, right? Yeah. So thank you very much again for the keynote speakers, and then let's all grab a coffee and some water, and then we'll
Just we'll have a break in the recording, and now we continue. So, yeah, take a seat. We'll come now to the session defining extremes. We already had some also notes on what can be extremes. Especially, I think it's important here, being at the Weather Service, to point out that extremes, not only weather extremes, which price extremes are another one, which is for the market in the end very important. And so the next speaker is Caroline Draxl. What Corinna already said, she's a co-lead of the IEA Wind Task, and she's working for EPRI, Electrical Power Research Institute in the US, and developing a tool, especially to risk assessment. And yeah,
thank you, Helmut, for the introduction, and thank you all for being here. I would also like to acknowledge some of my EPRI colleagues who have contributed to this slide deck with their slides, and also who have contributed with their research to what I'm going to talk about today. All right. There we go. So today I would like to introduce EPRI and explain why we're interested in researching extremes. I then want to characterize meteorological and power system extremes from our point of view, and we've heard a lot about this already. I would like to also summarize a little bit of that, and then go into the definition of extremes, and at the end, introduce EPRI's risk screening tools. So a little bit about EPRI. Our mission is to advance safe, reliable, affordable, and clean energy for society through global collaboration, science and technology innovation, and applied research. So we are a research institution. We are a global institution. A lot of offices are in the US, as Helmut introduced, but there's EPRI Europe. We also have offices in the Gulf region, in Japan, and we are operating out of Mexico and Canada and other countries as well. The research at EPRI spans the entire electric industry. So that's the nuclear sector, the generation sector, also power delivery and utilization. And the strategic research areas are low carbon resources, end use and economy-wide carbon reduction, electric system reliability and resilience, electric system flexibility, and market transformation policy and regulatory education. And so you can see, topics like low carbon resources or carbon reduction and electric system resilience, all these are topics for which it's important to be interested in extreme events and do research on extreme events. So explaining this a little bit further, as EPRI is reimagining the future energy system, what topics surface in the next 10 to 15 years? So that's decarbonization. So EPRI is focused on accelerating economy-wide low carbon solutions. And the other topic is resilience. So we are focusing on mitigating climate impacts and cyber and physical risks. And then when we look out to the next 15 to 30 years, there'll still be decarbonization. So we want to focus on a net zero clean energy system. And there's also still resilience, where we focus on future-proofing energy system design basis. And we also focus on transformation. So we want to drive the affordability of a clean and resilient energy system through digital transformation and power system modernization. So we want to make energy more clean, affordable, and reliable. And that's not only what we should be doing at EPRI, we as a society should all do this. And as we do this, we need to look at extreme events. Okay, so I'm now going to characterize meteorological and power system extremes and then go into the definition of extremes. So when we talk about meteorological extreme events, I really also want to call them climatological extremes, because when we look at extremes, we need to look at the large or long time span, and we also need to look into the future. So usually meteorological extreme events are derived from climate data or model simulations or observations. The meteorological extremes are usually defined relative to climatology, like I said, something like a 30-year period. They are also probabilistic in nature and often characterized by return periods, and they may exhibit long-term changes due to climate change. You can characterize extremes for one variable, or they can be caused by a variety of extreme events. For example, if you think about a hurricane, then we deal with precipitation, extreme winds, and also storm surge, for example. Or when we talk about winter storms, we deal with extreme precipitation and cold temperatures at the same time. We can classify meteorological extreme events into acute events or chronic hazards. For example, acute being something that happens in a short time period, for example, flooding. Or we can talk about chronic hazards, something like as the climate is warming, then the transmission system, for example, might see reduced performances. Or we can look at multiple low wind winters in a row that can stress a high renewable power system. At this point, I also want to talk a little bit about the difference between extremes, variability, and volatility. If you think about a distribution, then extremes can be the tail ends of the distributions, and variability being the whole distribution that includes the tail events, and volatility being just the randomness in the chronology of the events. And meteorological events can be location specific. When we look at power system extremes, then those so climatological extremes can provide insight into the power system extremes, and often they may overlap with, but they can also differ from the extreme operating conditions we're seeing. And it is likely that we need additional information from asset managers, engineers, or system operators to understand what may be considered extreme operating conditions for power system assets or components. So when we think about extreme events, we always need to look at the impacts from the weather on to the assets or the power system. We can define performance thresholds relative to operating characteristics of the assets or the system. For example, we can say, okay, if the temperature is above a certain threshold, then we likely experience extreme power system events. Then again, the power system extremes can be location specific. They can also be asset specific. And what is considered extreme might change through the adoption of new technology or operating methods, and also with climate change. And also, power system extremes might actually not have anything to do with the weather sometimes. So they can be caused by equipment failure, malfunctions, supply shortages, human errors, or man-made attacks. And in any case, the goal is to ensure that the power system assets can maintain adequate operations or ensure rapid recovery. And if that's not the case, we are dealing with an extreme event. So I have here a table where I want to contrast these and look at specific types of extreme and see how they differ depending on if it's a climatological extreme or a power system extreme. So the first row is climatological, and then second power system. So when we look at temperature and we say, okay, a climatological extreme could be the historical 99th percentile of the summer daily high. And if we look at power system extremes for temperatures, that might be like the distribution transformers are at risk of failure if subjected to a few days of very hot temperature, for example. Then when we look at precipitation extreme, in the meteorological sense, it's like the 100-year rainfall or the 30 millimeters in a day or something like this. And for power system extremes, it's, for example, sensitive electronics can fail if submerged in floods. And then the severity of the flood impact depends on the elevation or waterproofing of the equipment. So it could be that if an equipment is waterproofed and there's flooding, it might not actually harm the asset. So we have to look at the impact that the extremes have on the assets. For wind, for example, if we look at climatological extremes, those are hurricanes, thunderstorms, derechos or gusts. And if we look at power system extremes, winds or extreme wind gusts can damage power lines, and they in turn can cause wildfires. And that actually is something that happened in my neighborhood. And then turbines, for example, can be unable to operate if the wind speed is above cutout wind speed. And I also want to say that changes in extreme events are likely to be more impactful than changes in average conditions. So this is also a plug for saying that we need to look at climate change when we talk about extreme events. So on this side here, I want to talk about the definition of extremes, and that extreme events can be defined along multiple characteristics. And those are the 3 dimensions that are commonly used. So we can define extremes by the magnitude or intensity of the event, by their duration, how long they last, and by the frequency, how often they occur. But there's other ones that we can use, for example, regionality. Extreme events might vary spatially. They might have some seasonality to them. They might change within a year. There's also compound hazards we can consider, like if one event leads to another or they occur simultaneously, like for example, you have hot temperatures over a long time period, and that leads to drought. And if there's rainfall after, this creates more severe flooding, for example. Or we can look at consequence. Extreme event consequences can include demand, load of the system, or societal factors like health, for example. And the question of what qualifies as an appropriate extreme event is one of the design choice. So then we can use these attributes that can become criteria. And the choice of the approach that we should take when we define extremes should reflect the specific purpose and the context of the categorization. And I have an example now. I want to show you why it matters how we define extremes. And I'll go back to the Dunkelflaute events or dark doldrums. So we did a study and wanted to find the worst year of Dunkelflaute events. And so here on the y-axis, there's different definitions of extremes that we used. I'm not going to go into detail here, just letting you know there's a different definitions that we used. And here's the time axis. And we wanted to find the worst year. And that worst year is indicated by a red square. And you can see that depending on how we defined it, we found different years that are the worst. So how extreme an event is depends on how you define it. And I'm really looking forward to our Dunkelflaute session and see how various groups define their extreme events. Okay, and with this, I'll move on to EPRI's risk screening tool. And to illustrate that tool, I want to start out with an example of a challenge that someone might have. For example, they might ask themselves, how do we evaluate which event poses the highest risk to the power system? And so we looked into this. This is the state of Texas, and we considered 4 1-in-50-year extreme heat events in Texas. And we looked at them depending on criteria around duration and spatial extent. So in map A, we looked at the 10-day statewide average temperatures. In B, at the 10-day average temperatures of a single city. In C, 3-day statewide average temperatures, and in D, the 3-day average temperatures of a single city. And so you can see that, again, selecting extremes is not as straightforward. These maps differ, and so depending on how we define that 1-in-50-year extreme heat event gives us different answers. And so, And so we need information beyond the weather itself to find out about these extreme events. So for example, we could ask which assets are present in the system when these events occur. Might they suffer performance impacts from high temperatures? Or what is the state of other weather variables beyond temperature? Is the wind blowing? Is it cloudy? Is it humid? Or we can say, okay, how sensitive are electricity demands to these weather conditions in space and in time? And this is what also the risk tool can help with. So it can combine weather, asset vulnerability, and demand information to screen for periods of concern. So it can take weather information or climate data or also past weather data and pass it through models of asset vulnerabilities to identify high stress grid conditions. And those high stress grid conditions can be, for example, high load conditions and the high likelihood of generator unavailability. And we've often actually found that looking at load is really important also to define the extremes. And we've heard also prices, but not in there yet. Also, in terms of climate data, risk can identify key time periods or conditions for more detailed downstream modeling that someone might want to do. Then the tool can look at asset vulnerability. And the goal there is to define asset vulnerability matrices and derating factors as a function of weather variables. So if we take onshore wind, for example, we can have thresholds in there or like functions in there that can say, okay, if the temperature is below freezing and there is precipitation, then this could lead to a derating of 90% due to blade icing, for example. Or we can say if the wind speed is greater than 25 meters per second, the derating is 100%. And that's due to a cutoff winds. And then risk also looks at electricity demand. So the electricity demand estimates, they incorporate the local weather sensitivity, future technology adoption, energy efficiency improvements, and temporal correlations. So again, we have the climate data or the weather data that can be input into asset vulnerability functions, and then we add load projections, and then we can identify high stress operating periods. So I wanted to show this graph here. This is output from the risk tool. So we have time on the x-axis and available supply in megawatt watt on the y-axis, and the colors indicate the generation method. So the gray down there is the nuclear generation. Then we have the brown colors, that's coal and gas generation. We have a little bit of yellow, that's solar, and we have wind in green, and just a tiny bit of battery. I don't know if you can see the little purple dots there. And then overlaid is the load curve, that's the black line. And we can see that there's periods where our generation doesn't meet the need. And in risk, and this is actually, I should say, for the 2035 case study, so that's using climate data. And so with risk, you could go in and say, okay, you can screen for changing risks and put in, for example, new system build-outs or additions of adaptation measures. You could use different climate data inputs and see if that changes. You could use adjusted asset vulnerability functions, or you could put in new load assumptions. And here's an example of how that might look like. This, you've already seen this graph. And if we then look, for example, at another year, 2050, we have similar but still different makeup of the available supply of the generation. And if we change the methods that I put down here, for example, we play around with new system build-outs or additions of adaptation measures, we might get a different load curve here, and then we can say, okay, we have a different gap. Yeah, which is, we can look at extreme events that way. And so with awareness of system risk and the potential to invest in hardening options, we can then be more resilient. And here's another graph that I wanted to show you. This is for past data for 1989, for example. This is also for Texas. And down on the bottom, you have time again, and you have, in this case, the generation capacity outages on the y-axis. So this plot shows you why certain outages happened. And the colors indicate the why, like which weather situations caused the outages. So we have the green, for example, that was low wind. The blues are no sun. Then we have the red is low temperatures, or the purple extreme cold. And this was an extreme cold event back then. And it was a 3-day cold snap. So in this case, there was 50% of outages. And then if we contrast this with another year, 1983, we had a 5-day cold snap, so longer. But because the makeup of the energy system was different, the weather had a different impact on the different generation methods. And so the outage was actually lower, even though the cold snap was longer. And so the point being here that we need to, so it matters how the whole system is responding to the weather. And we need to look at that. And risk can help with that. And that concludes this talk. So these are my key takeaways. The identification of extreme events is important when planning for a resilient power system. Risk can help you with that. And Risk is actually an open source tool, and it's available on GitHub here.
So,
just wait a second, because, yeah.
Yeah, and I have a slight question to look at. I'm curious to see in terms of ranking. So I was wondering if you can rank the following extreme event attributes in importance when you think about a wildfire event. So which ones would you think are the most important ones? And it's really interesting to see that certain different people choose different definitions for extremes that are important. And if you use different ones, you might get different answers. And then I have the same question. Oh, I'll wait a little bit, there's some more people.
The QR code is also there. Both over here, if you scan it.
Yeah, I think we can do the next, but I think I can also do it too. Yeah, so if we take a different event, how would you rank that then? In this case, it's like a high wind speed event.
Okay.
Yeah, this is interesting. In this case, consequence moved up to the top now, yeah, went down, but different criteria, depending on different events and depending on probably what's going on in your head is how important it is for your own application. So it really depends on the application.
That's interesting.
So then thank you. Other questions? Okay. Yeah. Your future.
In your future risk assessments, do you take into account how much solar or wind storage may increase in the future, and thus perhaps could mitigate the risks?
Yeah, and you can change that in the risk tool if you want. Yeah, the different makeups and I mean it's always you don't know, right? I mean what it will be, so you have to use assumptions.
Actually, one question comes to my mind: is this tool now specific for the US, or is it, can you use it worldwide?
No, you can use it for different power systems. You can yeah.
I mean, do you have the data for the US only, or so?
The users can put in their own data. Like for example, the weather data, you can use your own data set that you come with. It doesn't have to be a certain data set.
Thank you for the talk. Does the tool include storage and transmission in some way, or is it basically residual load analysis?
I believe so. I'm not the expert on this tool, but I can get you the answer and ask a subject matter expert. And maybe Juan Carlos, if you're still online, I have a colleague online. If you know the answer to this, you can put it in the chat.
Okay,
I have one question here from the chat that was that we maybe can take here. How important are solar eclipses? Mentioned already twice, intuitively they would seem to be predictable and transient, not so critical. And maybe some of the others want to answer that.
Yeah, this question actually came in during the keynotes talks. So
but it's in a way, it's again what you said. I think there is, it depends. It depends. A solar eclipse in itself is predictable, but if it comes at a bad time, it can still lead to an extreme event. I don't know whether some of the other speakers want to comment on that.
On a cloudy day, it's probably not very, it's not a big impact. Whereas on a sunny day, it's totally different.
Exactly. This is one side, but the astronomical conditions are very well predicted, and it's actually from, I don't know, from pretty soon implemented in our IPRI model. And it depends on the weather situations on the day. If the key is high, then and the event is more extreme. You said already. So it is both. It is implementation of the astronomical conditions. That's probably one first step in the NWP models, and then it's the forecast capacities of the model. Yeah.
So then we'll continue to our next speaker, which is Christian Gams from MeteoSwiss, Switzerland, talking about weather regimes as a proxy for extremes in the power systems. Also again, weather regimes, which Frank Kaspar was already mentioning shortly, already now we'll hear more details.
Shall I let?
Oh, I'll do this. Yes, you don't think. Yeah. And if you want, maybe point up hinstellen, vielleicht.
Ja.
Ich weiß nicht, ist das dann der Option ist.
Okay. Is this good with the microphone?
Yes.
Yeah. Okay. Good morning, everybody. It's a pleasure to be here. So what I want to talk about is coming back to the topic of Dunkelflaute, but also solar power gap. So this is basically a result which is at a transition from academic research from my previous employment at KIT and now bringing that more into application at MeteoSwiss and elsewhere. So I want to acknowledge my co-authors, Dominique Bühler, who is now also at MeteoSwiss, and Fabian Mockert, still at KIT. But first, just where I'm from, I'm now at MeteoSwiss. MeteoSwiss is basically the national meteorological and climatological service of Switzerland, like DWD, but way smaller. We are just 10% of the size of DWD. And in the past, there were already several more decentralized applications for the energy sector. So I just emphasize few of the activities we're currently already doing. But at the moment, we are also trying to foster a bit more tailored products to the energy sector in order to support the Swiss energy transition. But what we're doing so far is an energy bulletin, which was mainly through the gas crisis a few years ago. So we are doing regular updates on the weather conditions in a seasonal outlook mainly, but seamlessly thought. And the key product here is heating demand days that we predict on the basically community levels. Another thing is feeding in meteorological information in the Swiss Office of Energy, also another federal agency, energy dashboard to monitor the weather situation, in particular in winter. But then our core business is providing the seamless weather and climate data. I'm from the climate division, so it's mainly the things for planning. We need the gridded information in complex terrain. And in particular, wind is a problem because we need maps like that on 100-meter scales for wind assessment in complex orography of the Alps. And this is not yet achieved by current model data sets. So here we are exploring new types of data sets. Likewise, here in collaboration with DWD and the CMSAF project, we are developing retrievers which are tailored to the alpine orography. And this already feeds in a service where we can inform the solar power potential at each rooftop and facade or walls of a building, which really fuels the energy transition. When it comes to the Swiss energy system, there's a speciality that in the electricity, we are already quite renewable with a high share of hydropower. So the bulk is hydro from lakes and river plants, but also pump storage, which already have been mentioned. And then there is a base load of nuclear still, but these are predicted to be turned off. And the increase in recent years, and this grows exponentially, is really in solar power. So there is literally no wind energy in Switzerland. This is more for the acceptance, which is not given. So the future energy system will become one which is driven by water power and solar power. And the current installment is even higher, so it already is 50% more, so about 9 gigawatts of installed panels, and this is planned. So this is basically where we want to get, but a more ambitious target would be having a huge fraction of installed solar capacity in Switzerland. But this then brings, of course, a different way of volatility in the system. And this already concerns the public now. So one thing is in the transition season, so in autumn and spring, when solar power is already still relevant, but also in winter, this peculiarity of the Swiss plateau region, which is basically the flatlands north of the Alps, it's often covered in these foggy conditions. So low stratus clouds, this is the Rhine Valley here shown, but the mountains are out of it. But many of the PV installments are at low land. So this needs to be predicted, low stratus in particular in transition seasons. And what happens if not? I mean, the other speakers were talking already about it. For us, we had a severe event in the solar prediction last April already. This was similar, a weekend issue. So typically they had day ahead forecasts, but which are deterministic and misrepresented the actual power production. So there was too little production on that day. Due to an uncertain weather situation, something which we could show with probabilistic forecasts like we do with our icon suite are easily to capture this uncertainty. So this is basically not the matter of having all the same forecasts, but simply the providers had too bad forecasts. And this also caused severe costs from an event which was lasting only a few hours. So 30 million francs, this was the cost of this, because the spot market prices also rose to 10,000 euro on that day. But what also concerns is not only the national production in terms of solar power, also what goes on beyond in the boundaries. We are interconnected, and these Dunkelflauten in November, December also were of concern in Switzerland. Because of the hydro storage. There was a lot of balancing from the pump storage, so they were at their capacity of what is transition possible towards Austria and Germany. And this also, it concerns also what's going on in terms of wind energy, even if we don't have wind energy. And this is the graph again from Agora. You for sure know that. So it's the power production in this 4 month period. And you see again the Dunkelflaute in November, but then also others that happened in December and January. And in between, you have these periods of high wind power production. And you see these are multi-day events. And that brings me now to the weather regimes. What I want to show in the course of this is that meteorologically, these Dunkelflauten are, as we have seen by Frank already and Jacqueline's work, by the high over Central Europe for Germany. But this is more the synoptic weather type perspective, so the daily variability, and on the multi-day time scale, so more weekly variability of the large scale conditions over regions like North Atlantic Europe, we have regimes. They are typically lasting at least 5 days, but often 10 days to 3 weeks. So it's more this slower frequency, atmospheric variability. And we see typically cyclonic regimes like the Icelandic low or North Atlantic oscillation positive. So it becomes meteorologically now a lot. But these regimes come along with windy, wet and mild conditions in winter, whereas blocked regimes, often that you have a high pressure system residing somewhere over Europe, bringing more calm conditions and are prone to these Dunkelflauten. So in this research now at KIT, we used a definition of 7 different type of regimes. I come back to a slide later. They are basically identified in a large scale field, so-called geopotential height, but I will not show that. And they are also characterized either by cyclonic or blocked regimes. In terms of the wind impact, this is now grouped here. So it shows these 3 cyclonic type regimes in terms of their modulation of wind speed at 100 meter in the European domain. So you have Iberia down here, Scandinavia up here. And red means more wind than on average in winter. And these cyclonic regimes have cyclones, low pressure systems somewhere over Europe. And then they generally affect either Western Europe or more the North Sea region, and again the North Sea region with above average wind speeds. And then the blocked regimes often come along with low wind speeds, in particular the Euro blocking. We call it Euro blocking, but this is the high over Central Europe of the Großwetterlagen of DWD. They come along with calm conditions, but in peripheral region, you see this above average, also what we saw in November, like in Scandinavia and Greece. In these conditions, we have above average production. And also Atlantic Ridge, if you look carefully in the Eastern Mediterranean, Italy, Greece, we have above average conditions when Western Europe suffers of a wind drought. Now it's interesting also to looking into trends. So this looks a bit on first glance maybe contradictory to what Frank said, but it's not. This is the year-round frequency, also dating back from 1950 of these regimes. What you see is there is a huge interannual variability in the regime occurrence. So it's colorful. The red shades are the cyclonic, wind-prone regimes in Central Europe. The yellow to green shades are have less wind. So, and when you glimpse the eyes, you might see you might think there's a certain trend in the greenish regimes, which is also, I mean, we also checked here, and there is a trend in the Scandinavian blocking, so blocking over Scandinavia, but mainly in summer and autumn. So it's not the winter Dunkelflaute. So, and we do not see statistically significant trends in the high over Europe neither here. But what you also see, if you look here, 2021, some of you in the sector might remember this was a very wind dry year, so there was a big lull. And if you carefully look, there was hardly any cyclonic regimes. In contrast, you had yellow, the Atlantic Ridge, and the Euro blocking. And I just checked the Copernicus State of the Climate report from 2021, which was discussing this wind drought in Europe. So this graph 2021 shows that in Germany, Denmark, United Kingdom and Ireland, we had a way below average wind speed country aggregated. Another year was also 2010. And you see they come along here, 2021 was a lot with Atlantic Ridge. And this also had above average in Greece, Italy, what I showed before. This regime was prevailing sometimes in that year, and it's consistent with this regime. So there is a link to this lower frequency variability on weekly scales to the wind power output country aggregated, and you can nicely show that here, inspired by Jan Wandel here. I think tomorrow he will also discuss this a bit. When you now look at these Dunkelflauten from last winter, again, you see that the first one, the severe one, happened during Euro blocking, the other one again during a Euro blocking with Atlantic Ridge. Then we also have so-called no regime days, so they might also happen in unusual situations. But it's also interesting, these high periods of high wind speed happened during this cyclonic regime. So here we had an orange regime and a violet regime. And again, in February, another Dunkelflaute with Euro blocking. But we looked into that a bit more systematically. So this was a study just similar and inspired by Frank and Jacqueline, but using these 7 regime definition, defined as a combined capacity factor in a high renewable system below a certain threshold. And when you apply this definition, we find most of the Dunkelflauten are actually Flauten, so doldrums, so they occur in winter when we anyway have little solar power. This is only for Germany here. And they mainly are linked to the light green Euro blocking, so consistent with Jacqueline's work with the high over Europe, but also in the blue regime, which is Greenland blocking, which is a blocking over Greenland, the NAO negative phase, and in autumn, sometimes the dark green or other regimes as well. So we see a certain systematic link to these regimes. And now it's the question, what is special about these regimes that feature a Dunkelflaute versus not every regime features a Dunkelflaute? So can we learn something in terms of also anticipating ahead these Dunkelflauten? And what Fabian found here is a significant difference in the duration of regime life cycles from those which feature a Dunkelflaute versus those which do not feature a Dunkelflaute. In particular, the Greenland blocking life cycle, where embedded we have at least 2-day lasting Dunkelflaute, on average lasts almost 20 days. So a very long Greenland blocking life cycle, whereas on the average duration is just slightly less than 2 weeks. So this gives an indication long-lasting regime life cycles are more prone to feature a Dunkelflaute. But we were also looking at the meteorological pattern because we found there is not only the high over Europe Dunkelflaute, this would be the typical pattern. So Germany residing in the center of the high pressure, but we also found that the other typical Dunkelflauten regimes, Germany is rather in the saddle point between pressure centers, either in an axis between high pressure from Iberia to Scandinavia or between low pressure in these. And then we also have low wind conditions. And this is important, what comes along with temperature, which drives demand. And there, the Greenland blocking is more relevant because we have cold conditions in winter during the Greenland blocking Dunkelflaute. So this is when also demand will be high due to heating. And Germany also has cold conditions. So this is something where we want to watch out for in a forecast. So now with this knowledge, you could think, looking into a forecast, seeing a Greenland blocking of long duration, we might see a cold Dunkelflaute. But also this is misleading because the regimes, they have a lot of inter-regime weather variability. This is shown here, the country average 2-meter temperature over Germany during regime days, not necessarily Dunkelflauten. And you see on average, Greenland blocking is cold, colder than usual, but it can be in some occasions also mild. It can be very cold. So you need to also have a handle on what is the weather character. Not every Greenland blocking is a cold one or a non-windy one. And that's another master student, Judith Gerichhausen, did that. She's now at Geosphere Austria in the forecasting section. And she looked at the characteristics of cold Greenland blocking events, warm Greenland blocking events, and here the contour. Well, you see the cold expands over Europe in the cold Greenland blocking, whereas it resides over Scandinavia, and Europe is rather mild in the mild Greenland blocking. And the characteristics of this high pressure differs. So here it's more has a co-characteristic of a ridge over the Atlantic, so the high pressure slightly shifted towards west, and we get this northerly flow into Europe. Whereas in the mild, we have a strong storm track, which is more characteristic of an co-occurring Atlantic trough with mild conditions into Europe. So this gives you a distinction and the means of forecasting for the experienced energy meteorologists. We can coin that also quantitatively in so-called regime indices. So there is for now, you just need to know there is a tool where informed you can already get whether it will be mild or cold in Germany. And we developed that catalog for each countries, each type of weather impact that you can imagine, wind, solar, temperature, precipitation, how the inter-regime variability can be basically characterized in terms of the regime characteristics. And just going into applications, this is now a subseasonal forecast for another cold Dunkelflauten event. First, I characterize the event below here. Its average temperatures in Germany. The event occurred in mid of December 2022. This is the capacity factor for wind. So this was the cold Dunkelflaute happening 2 weeks after initialization time of forecast I'm showing here, and way in the middle of a Greenland blocking. And this would be the forecast depiction of regimes. So the forecast started end of November, shows you a long-lasting Greenland blocking, which lasts almost the whole month of December. And there is a spread in that, but it's pretty high compared to other forecasts. And when you carefully look at the yellow curve, this comes along with this co-projection into the Atlantic ridge. So this is the indication that there is also the shift of the high pressure towards the west, and therefore colder conditions might prevail. And this thinking is important in subseasonal forecasting 2 to 3 weeks ahead, when we cannot predict surface weather very accurately. So it gives you a handle of how to deal with this inter-regime variability. So just almost the summary, what goes on. At MeteoSwiss, we are currently together with ECMWF implementing such regime forecasts. But we are much more interested in the climate monitoring, using these regimes for climate monitoring, knowing about solar power gaps, when do they happen and how often do they happen. So we do that in a master thesis. And then Fabian is exploring more the forecasting part. So on subseasonal timescales, there are other climate modes which are relevant. So he looks at that and does statistical ML-based forecasting of regime activity and can show a very much improvement of probabilistic regime forecasts with a neural network approach compared to the standard NWP output. Yeah, I think due to time, I skipped that. It's just an example of the climate monitoring application. I have a summary slide, and I don't know if you still want to do some Slido or, yeah. Then I quickly go to Slido. So there are 4 questions, and I leave the organizers how to manage that. Yeah. So is only one question active at a time?
Yeah.
Okay. So the first question would be: have you already heard of regimes? And if yes, in which context are you using regimes? So there's already a trend that regimes are used in forecasting, more looking beyond a week scale. But also in this application, understanding what's going on in the power system. Okay, should I go on to the next?
Yeah, I can do it.
Yeah, or do you do it? So regimes are not only, I mean, they are traditionally used in Europe, but there are now more regime definitions out. So there's in particular North America is now, in North America, they are using more and more regimes because these definitions have been established the last 5 years, but also there are East Asian regimes, South American regimes, so primarily for the extratropics. Yeah, but this reflects a bit that also the knowledge from academia that in Europe they are widely used and they are just coming up for North America and other regions. And it's interesting that many of you are using already regimes, so and then primarily for Europe. Are you taking care? Okay.
You can do too.
The next one? Yeah. So how often in your daily work are you using regimes? So is it just an one in a year exercise or yeah? Okay, a bit less than half hardly use regimes, but then it's interesting. There is still a fifth of the participants who use it every day. So these are probably energy meteorologists looking on more the subseasonal time scale. Okay, for time, I go to the last one. from which source are you getting regime information if you're using it? So that's probably only the 20% daily is relevant, or those who use it occasionally. But this is a word cloud, so you can just type like DWD, ECMWF provides it, private companies provide it. So that very popular is the Decider tool by UK Met Office, or you could type Decider, then people know what you mean. MetDesk as well. Okay, I think we stop here. We have 24, and this is roughly the thirds who used it. So thanks for participating.
Thank you very much. Yeah. And questions? Yeah, we'll start. Yeah,
Much for your presentation. I was wondering if, in addition to Dunkelflaute, beyond Dunkelflaute, you found any meaningful relation between the regimes and other types of extreme events, or you studied them? Thanks.
Yeah, so it has been shown some regimes are linked to a heavy precipitation events in some regions of Europe. So here we have what we've heard before, this dependency on the region, so where exactly it hits, but in particular the regimes, because they are so large in scale, they modulate in autumn basically the steering of atmospheric rivers, and in particular the Atlantic Trough is prone to atmospheric river landfall in Iberia, Portugal and Spain, but also the western coast in particular. Then in summer, we have heat waves linked to it. So, and also co-occurring heat waves, in particular, the Scandinavian blocking is linked to heat waves in Central Europe, but also, of course, in Scandinavia. And so this has been, there's a bulk of literature in the academic literature already out, which shows these links of how regimes modulate more these larger scale extremes and longer lasting extremes.
Thank you, Christian, for that presentation. And my question is then, how are we able to disentangle the weather regimes from a Dunkelflaute episode? I mean, when we see in the forecast that we are getting a Greenland blocking, into which extent can we say 100% sure that this will bring us weather Dunkelflaute? Is anybody doing this work to disentangle a regime in the Dunkelflaute?
No, the 100%, of course not. We are in a probabilistic world in sub-seasonal to seasonal forecasting. But the knowledge that Fabian and Judith got is basically a first pre-alert is if you see a very long-lasting Greenland blocking in the forecast, say 3 weeks or longer. So this is quite prone that sometime in between you get a Dunkelflaute. And the cold conditions you can monitor by looking on, is there kind of a similarity, and this is basically expressed by the index curve I showed into Atlantic Ridge, then it would be the cold flavor of Greenland blocking, or into the Atlantic Trough, then it would be the mild flavor. So these are the key take-homes of characteristics of a Greenland blocking that are more prone to the cold Dunkelflaute. And you can learn more about it with this catalog. If it also depends on the country you're looking at and the time of year you're looking at.
Yes, thank you so much for your presentation. I was wondering, do you have any opinion when these so-called Dunkelflaute events or blocking weather patterns appear more likely during the winter season? There exist some theses around that potentially the early winter period they appear more because of the weaker polar vortex, for example. So any comment on this one?
I mean, on bulk, the frequency is less in winter actually of blocked regimes. So I didn't show that, but in general, you expect on average more of the cyclonic regimes in winter than in summer, and in particular in summer the blocks. And for the seasonality, you mentioned it. This is the state of the current research basically. because there are all these teleconnection modes which affect in the end the large-scale regimes also over Europe. And there are newest research like teleconnections from the early Indian Ocean, how that affects the early occurrence of regimes, and in particular also Greenland blocking. So the 2022 case was debated whether it was linked to that teleconnection. That would be an early one. So there is a lot of research need actually to understand these teleconnections better because they affect these regimes. And the problem here is that we do not have the climatological record. So often these 40 to 50 years of reanalysis data feature too little of the events. Yeah, but this is at the cutting edge of research currently. Yeah.
Corinna, last.
I have a question that is both for you and Frank, if he's still here.
Jacqueline is representing him.
Yeah, because I think, I don't know whether this also has to do with some kind of changes that we don't understand yet, whether this is climate or climatology, or whether this is just an annual variation. But we can see, at least in wind power forecasts, that there is a trend that there is stronger winds in summer than there has been, let's say, over the last 5 years. There can be storms in the North Sea or over the British Isles that we have never seen before. Is this a climate trend, or is there a knowledge, is there a work ongoing to know whether this is just a change, a variation, or whether we can say there is a trend happening?
Well, the quick answer is we cannot say if there's a trend going on, but looking more into the detail, the time series I have shown, we checked all trends also seasonally, and the only emerging trend is more Scandi blocking in summer and autumn. All others are insignificant when you look on this long time series. So there is still a lot of fluctuation, but from these regimes, this Atlantic trough is some which happens year round. So it can happen in summer as well, and it brings summer winter storms, we say. And yeah, whether this is increasing or not is not clear.
Thank you very much, Christian. The next one speaker is Irene Schicker. She is from Geosphere Austria, formerly ZAMK, and she is also very active in the IEA task and with a lot of post-processing of forecast, also using a lot of ECMWF data. So now not like DWD, so it's also an interesting aspect. Yeah, and she will present us adverse weather and mass event detection from the meteorological perspective, a multi-scale physics-informed approach.
Yes, thank you for the introduction. So yes, another Met service. And this time, at least in Geosphere, we also include the geothermal renewable energy, because we have the geologists already on board since 2.5 years now. So we integrate all spheres, more or less. We also have space weather, so we also have them. But going back to the adverse weather and RES, and you will hear again a lot of definitions and see a lot of definitions, but I try to make it short. So yeah, and I want to acknowledge my 2 colleagues from the climate department, actually, because I'm in the weather department, they are in the climate department. And most of the work I'm showing here is done in the Energy Protect project we have at Geosphere. And that is actually looking into adverse weather events. So not only extreme weather, but also adverse weather, which might not be extreme to us, affecting the renewable energy infrastructure. But we also have projects looking into renewable energy generation. So that's also covered here. And what we aim to do in Energy Protect and also other projects is to use the same methods across the timescales. So for forecasting, but also looking into where do we have current hotspots in infrastructure hazards, where do we have them in the future, and also developing some sort of what-if scenarios, like what if we would have had another turbine type during this or that event there? Or what if the, let's say, power grid mast would not have been 20 years old, 30 years old, but would have been maybe a newer one in the sides. So that's basically our motivation. So we have this rapid and continuous integration of RES into the power grid. And similar to Switzerland, we have an exponential growth in solar power in Austria. Not so much for wind energy, but also wind energy grows a lot in Austria, and we have a lot of repowering already ongoing. We have a lot of geothermal going on now, not so much the pump storage, because there's still this similar to wind energy, not in my backyard discussion or not in my national park discussion. Yeah, and a lot of hydropower in general. But we also have this increased sensitivity of the power grid to adverse or extreme weather events, which also affect the infrastructure. And just thinking of Boris, more or less a year ago, that impacted a tiny bit of power generation, but a lot of infrastructure. So we have this risk in both types, and we have the inconsistent definitions and impact metrics on how we evaluate what and the impact of an event to the power generation, to the infrastructure, or the whole power system. And we thought, being meteorologists and climatologists, we try to look into both scales and try also to come up with definitions we can use in forecasting and climate estimations. We also want to develop, and that's still ongoing, a multi-scale machine learning method or framework, combining all the different adverse weather types we defined and we decided on that we can actually tackle in the projects with the human resources we have into a toolkit. And as we do also have the risk lab at Geosphere Austria, who look into all kind of hazards like mudslides as well, and the impact of mudslides or other hazards together with the fire brigades. We also have them on board for detecting and risk assessment of the current and future hotspots. So going to some definitions and some industry feedback we got a year ago at the Austrian IEA, the first Austrian IEA workshop, on what they define as extreme event. And that's a bit more on the power generation side, and unfortunately German, but extreme events mostly highlighted were storm, heat, heavy precipitation, a cold spell, hail, wind tramping, snow, ice, not so much Dunkelflaute, but still visible, and also not so much Hellsturm. But something that's popping up more and more is tropical nights. And that's more for the demand side. And this will be getting an issue. It is already a bit of an issue because we had a couple of tropical nights in Austria this year. Last year was even worse. And we don't have that much of air conditioning. And that's really nothing you can kind of mitigate right now. But there will be a lot of people install air conditioning already, and that's another demand, especially at night. Yeah, and then we also try to group this into 3 time columns. And from left to right, you have nowcasting, then you have the medium range, which is from week to, let's say, the extended range, a bit into the seasonal range, and then the long-term or decadal range. And we do see that something like cold spell is present through all the timescales. Storm damages is the lowest column, is present through all timescales. Heat is more an issue on the medium range to long term, and same for Dunkelflaute, heat wave, and summer wind drought, which we also have here already. And we do actually have a paper now, and I think it's hopefully in revision with Corinna together. So We evaluated all the results we got. And what we also heard, and that's also feedback we got during the last couple of months, is hailstorm, plus we have a nice sunny weekend, which is not too cold or not too hot. We have a lot of runoff, so think of a typical spring situation in Austria, where people are outside, either still going on ski tours or going mountaineering in the east of Austria, and you don't have a lot of consumption. So what do? You typically try to transmit everything you have in the east to the west, where we have the pump storage. But if we have runoff, and a lot of runoff, then the pump storage facilities are pretty early on full, and they just can't get rid of and can't empty the pump storage devices. And that's actually something that happened this year already a month earlier than the years before. So this sending it to Austria to the pump storage won't work very long in the future. And another event which is not mentioned are the combined air quality, so health, or Dunkelflaute in winter events, or also the Flaute events in summer, and the increased demand, either heating or cooling. And especially for winter, where we have these persistent winter inversions, where we have most of the wind energy in the east of Austria, typically then they are in a kind of Dunkelflaute event. And we also have the build-up of bad air quality. This adds another point on the production issue, but also depending on the type of air quality can impact the devices as well. So in a lot of projects, also there's, I'm not going through all, just showing the table. So we have a lot of projects also in the Destination Earth framework. And Destination Earth is on detecting extreme event or adverse events for the power system for wind and solar. And we have 2 parts defined there, plus a third one from DLR, which is wind power ramping and solar thunderstorm ramping and the power grid. And we had to come up actually with a definition from the meteorological side. How do we detect in the IFS or in the continuous digital twin of ECMWF, so the 4-kilometer one? How can we detect from the meteorological side that an event will be happening in the next up to 4 days, so that we can trigger a sub-kilometer model to forecast for that specific region? And we looked into what are the causal weather patterns, what are the parameters we have to use for our detection, and then some nodes and forecasting methods, detection methods. And that's for power production only. And that's a short list for infrastructure events. So we tried to do something similar for the infrastructure, what type of events, and we have again storm gustiness here. We have heavy precipitation and flooding. We have the temperature range, we have the excessive wind loads and gustiness. We have lightning, but lightning is not so easy, especially if you go to the climate scales. We have icing conditions, humidity, damp, and heat, and that's the power infrastructure. Plus, what we also still miss in that table is wet and or late snow and snow accretion. Plus the information then if you have next to the power lines a forest, which happened actually some years ago. We had late snow, late April in Vienna and the surrounding, and quite a lot of snow, like 20 centimeters, I think. And we had the power lines running through the forest. So the forest, a lot of the trees collapsed due to the snow loads and fell onto the power lines. And that's something we are implementing now with the Risk Lab people. And the 3 gray ones are the one we actively look into. The light yellow one is the one we are going to tackle if we have time. And the heat wave, cold spell, and thunderstorm is something we might tackle if we are still in the mood for it and have time. But for all of those, we have a set of definition how we can detect something in a weather forecast without having access to near real-time data or historical data from different power plants. We do have some, but not for all of Austria, and ideally we would have it for all of Austria. Yeah, this is just very briefly. We have a lot of data sets we used across the different projects. Just to give you a very brief, blue is historical data, orange is an analysis set, so it's not a reanalysis, it's an analysis. Green are the forecast models, purple are the destination Earth digital twin data sets, and then in orange we have the climate, light orange we have the climate models. So those data sets combined we are using into the, in our framework to define and detect something, plus a lot of metadata. Where do we have the power lines and the masts and the substations? The known PV sites, we don't know all of them because every PV site that, if you only have, let's say, 4 PV sites feeding into a substations, you're not allowed to get the data in Austria by law to secure privacy. So we only know what is in the OpenStreetMap and in the Global Energy Monitor. For the wind turbines, we're in the lucky position in Austria. Every turbine which has at least 100-meter hub height is in the aviation database, including the information of the turbine type, rotor diameter, refactoring, so everything is in there. And now I'm going through some detection stuff. And this is a ramping case. And I think we heard end of November 2024 already from Frank this morning. So there was also a case in Austria, and I'm going to show you the next one. And on the 21st, we had a down ramp within 3 hours from roughly 2.5 gigawatts to a bit more than 150 megawatts within the 3 hours. So we had quite a high drop, and then we had an up ramping again of up to more than 3 gigawatts within 3 hours. So that was quite a ramping case. And as you can see, there was another ramping case on the 22nd. This ramping event happened mostly in the eastern part of Austria between Vienna and Bratislava, where you have most of the wind energy sites located. And it was a storm event. And we also see that while we had the down ramping, the hydropower plants and the pump storage were producing again to match the demand, because that was really like when everyone got home from work around 5 p.m., turning on all the facilities at home, turning on the TV. So we needed the energy. And we all the same, that did not happen on the 22nd because the timing was different. We didn't need it at night. So this is a classical case where we try to use our ramping detection tool. And our methods are built on different types of methodologies. So we have the classical weather pattern classification, which is a bit different in Austria. It's not the Großwetterlagen definition, it's our more Austrian centralized one. And then we have a subjective one as well. So we have the automatic and the subjective one. We have this, then we used cluster and pattern detection, extreme indices and thresholds, and some really old-fashioned code from the 80s actually for climate models for detecting cut-off lows, because those are the events that mostly bring a lot of the heavy precipitation to Austria, the 5B patterns, and you can detect them very nicely with these old data sets. What we are also looking into is a multi-criteria ensemble approach to detect fast-running low-pressure systems, where we have this nice table of definitions we try to implement. We're still investigating and using old cases to verify that it's working. And we also plan to combine it with the NSOE data to have a base for a real-time tracking with connection to the energy predictions in NSOE for Austria. And going back to the ramping events, so we have this, and this was developed jointly with the Destination Earth on-demand extremes digital twin and the energy project is the wind speed ramping, where we have fixed thresholds, but we use the IFS ensemble to also detect the probabilities. So how high is the probability that we have a ramping happening, a down ramping for the in front of the coast of France, or an up ramping in Austria. Plus, we're also looking into a solar potential ramping to detect thunderstorms, and we will combine this with the thunderstorm classification. But these are the two tools we really use already and are implemented into the on-demand extremes twin detection system, so that we can trigger hectometric forecasts with roughly 500 meter resolution for the detected region in Austria, and then we convert this via classical post-processing to power production. And another topic, and I think that was mentioned also already a bit today, is the dynamic line rating. So depending on what the atmospheric conditions are, how much can you send actually through the power lines, which will be more interesting if we have way more wind energy and solar energy in the east of Austria and the storage facilities in the west of Austria. So how much can we actually send through? How can we help the TSO and the DSO to use this and integrate with the capacity prediction tool? And they have plans to have an initial draft for dynamic line rating operational in 2027 for subsegments. And we use our detection tool to detect, first of all, which grid points are suitable or not suitable for dynamic line rating, and combine this with the information of where we have the power lines. And the one in red you see is actually already the one they are interested in from the TSO side in Tyrol. And that's a quite interesting one and a challenging one. So we will see how good we detect suitable or not suitable conditions there. And we will do that really along the line segments, the grid points that cover the lines, plus minus 1 or 2 next to the lines, and the 4 3D fields or block to cover all height layers. And from our operational model, we have 10 meters, 15, 30, 40, 50, and 80 meters below 100. So we can really go along the full level chain. And now I have for storm and gustiness, this is driven by a case in 2020, Storm Petra, that affected some power lines in Styria and Salzburg, which are just central Austria, and damaged some of the power lines. And for the initial draft, we're using Error 5. So we had to really adjust all our thresholds to be able to see actually high winds. And then we combined this, and we saw that it really fits nicely with the power lines that were affected. So on the left, you see the during the peak gust, the lines that were affected, and on the right, you see the power lines that were in total affected during the whole Storm Petra event. And that's the first iteration, and the next iteration we're working on currently is having a running window machine learning model that also considers causalities. So what is causal to this event that happened from the meteorological side, so that we can include all different causalities and aspects, including as well anomaly detection and a pattern miner. But that's still ongoing. And in the end, we want to include all our different power production infrastructure detection tools into one big library, so that we can apply this also to historical and scenario data, but also use it in forecasting. And another idea that might be upcoming is a nice paper on X-Archive on cause or trigger from philosophy to causal modeling that was applied to 4 hurricanes, I think. And we did already the first step in remodeling that into our forecasting needs for the power system. Yeah, and I have no sliders for you.
But
I'm sorry.
we did one for you.
That's one. Oh.
So we want to ask the same question as we had in Austria and see what comes out of this audience.
Very interesting. Or maybe count the severe convective thunderstorms to the thunderstorms.
Okay, thank you. And then, yeah, always open for questions. Irene? So, questions? Irene, about geospheres, green?
Thank you for your talk. You talked about air conditioning and the causes it might have on energy demand. Could it be that you can simply use the air conditioning during the day and then not use it at night? So use it when there is PV?
From my perspective, living in a flat that is southeast facing, no.
Okay.
No, we have, in summer, we have the sun inside the flat from sunrise, basically. You have no option of creating any type of ventilation, and that's true for most of the flats, and our flat is a new one. And I'm not living in the city center. And if you're in the city center of Vienna, you have a lot of those old buildings which are not yet foolproof for heat. And given how even churches heat up, despite them with the thick walls, you're not able to get rid of it, even if you use air conditioners throughout the day until, let's say, 10 p.m. So I don't think that.
Back at the flexibility.
Yeah.
Thank you for your talk. I was wondering about the extreme events plot and their relevance across horizons, the plot that you showed earlier. And I was wondering if you also looked at the precautionary measures that can be taken at different horizons. For example, Dunkelflaute, I saw that it was relevant across all horizons. However, the measures that one can take at different horizons might vary. Maybe at seasonal, there are no measures at all. Maybe if it's in the next days or so, you can do more things about it. And I was wondering if that also went into the consideration.
For that specific table, not. That was just a grouping of how the audience saw Dunkelflaute and other events across the timescales. I think we have some recommendations in the paper, but it really depends on where you are as well. So if you're in the east of Austria, in the Vienna Basin region, or even Linz along the Danube, such events can really last a long time, and then you just can't have any measures. One idea I heard to Christian showed this nice picture of the fog in the valleys. And one idea I heard was just placing floating PV on the artificial snow lakes in the mountains because they're most of the time not in the fog. But then you don't have that many artificial lakes to use that properly. So no, not yet.
Thank you. Yeah, thank you. And because of the time also, we'll continue with the next presentation. Max Pierzyna from TU Delft and also University of Albany. So we are going back from Europe now to the US, to New York. And he's presenting his PhD work together there with Mr. Kaspar, who's also directing the IEA task. Excited to hear what you're saying.
Yes, thanks for the introduction. So last talk before lunch, so it is going to be a little bit technical, but I will try to make it easy. So you can see a little primer already about what I will be talking here in the photo. So I will be talking about estimating and forecasting high-resolution wind gust fields from mesonet observations. So mesonet means observational networks where we only have a few locations where we have the observations. And for this particular project, actually, I would like to also acknowledge the team because the primary work here has been carried out by Harish Baki, who is a researcher at University at Albany in New York State. I was supporting him, so I'm also at U Albany and primarily TU Delft in the Netherlands. And then the PI in this work is Sukanta Basu, who was already mentioned. So it's just some words of acknowledgement. But I want to get into it, and I think I don't need to motivate too much. Why extreme events are relevant. Sorry, is this video playing? Yes. Unfortunately, only one of them. There was supposed to be another one. So if you would look at the radar and you would in parallel also look at observations of wind gusts, you would see that the storm on the left is moving through, and at the same time you also have gusts moving through the state. There is a strong link between thunderstorms and also wind gusts, which we actually observe. And we saw some news items already in the previous talks. So this particular storm I was just showing actually caused 100,000 power outages in New York State. And particularly because there was a lot of heavy wet snow on the power line. So we also just heard about that. And of course, the situation in the US is a bit unique because much of the power distribution towards the end consumer is actually still going on above ground. So that's why there is more of a threat. Wait, these slides are not advancing. The whole PowerPoint crashed.
No, yeah.
Maybe we need to close all the presentations that are in the background. Yeah.
Sorry.
Yeah, I will just try to close all of these and then we need lots of them.
What it doesn't.
Okay, there we go. Okay. Yes. Okay, yes, so this is what I was saying, sorry. So the case I was showing before was a thunderstorm which led to extreme heavy snow, which was going on the power line. So you see that as this March 2023 event. But actually you can say that there is at least one severe thunderstorm in New York State every year. Sometimes it's extreme wind, which knocks down power lines. Sometimes it's heavy snow on the power lines. And it's not only the distribution that is affected by extreme events, but also the generation. So we've heard that before, so I don't need to go into much detail here. Also in New York, there is wind energy and there is solar energy. And if you would look at the distribution, for example, of hail events here, then we get around 20 strong hailstorms per year. And also from the wind power side, we can have overspeed, which causes turbine or mass damage. We can have the cutoff, all of that. So the bottom line here, it really is that the extreme events in New York really affect the entire grid from generation to distribution. And we want to act quickly, which is why the goal we are currently having in our project is to develop a deep learning wind gust nowcasting tool. And when we talk about nowcasting, we are really talking here about 3 hours ahead. And we're talking also about deep learning, because if you want to make a forecast 3 hours into the future and you use a standard numerical weather prediction model where you first assimilate all your observations and then you still have to run the forecast, depending on how much CPU or computational resources you have, this 3 hour forecast is really not feasible. And from the societal perspective, we want to do this to give production operators of renewable energies short-term predictions of what they can expect with respect to wind gusts, but also to alert and pre-dispatch maintenance crews and early responders, because if they know where extreme storms are moving through, they can already prepare that power lines might need maintenance. And then, of course, we want to alert the population. So that is the big picture here. I will just briefly give you the pipeline of what I will be talking, and then I will focus on a few things. So for nowcasting, we really want to take observations at a certain time zero. And in New York State, we have this network, the so-called Mesonet, and we have observations here. And we want to somehow interpolate them to a physically consistent gridded field. And then the next step would be, once we have this gridded field, we can actually advance it in time until our 3 hour forecast. And then this is the product which we can deliver. So today I will mostly focus on this interpolation part, which we call deep interpolation, or also in brief S2G, because it's sparse observations to gridded fields. So it's basically the analysis part. And then I will also give a quick outlook into our forecasting, deep learning forecasting approaches. So this S2G framework I will introduce actually has 2 phases. And you may be wondering, okay, we have now these sparse observations. How do we really get to this nice interpolated field that also accounts for terrain? So we've heard, for example, the terrain in this interpolation is important. Well, we do this by first starting actually with a gridded reference data set, or we also call it proxy data set. So what I'm presenting here is New York State, but it works everywhere, because this gridded data set really only needs to contain your variable of interest. So in our case, it's the 10-meter gust. The data set we are using here is the real-time mesoscale analysis. It's a 2.5 by 2.5 kilometer gridded data set covering the continental United States, and it has a 1 hour time step. So it's pretty much standard NWP. And what we do is, with this reference data set, we sort of simulate our network. So we take from the gridded data at the locations where we know the stations are, we basically downsample the product, and then we upsample it in a very simple sort of low fidelity mode again, just by using nearest neighbor interpolation. So that gives you this patchy polygon field. And then we use a deep learning model which learns to reconstruct from this patchy polygon field back to the high fidelity gridded data output. So that is the full pipeline. So the deep learning model only comes in this refinement process. And then the idea is, if you do this, and of course we minimize the loss between the reference data set and our prediction. If we take this trained model and we now put it into production and we actually take our observation, we can run this pipeline again. So let's say we use these observations from the Mesonet I was just showing. In this case, we have 124 stations, and it's called the Mesonet because the average spacing is roughly 30 kilometers. So you can observe mesoscale patterns. And the interesting thing here is also we get these observations at 5-minute timestamps, not just at 1 hour like the numerical model. So we take these observations. Again, we use the nearest neighbor interpolation to generate this low fidelity field. And then using the pre-trained model, we actually obtain this interpolated high resolution, high fidelity fields, which have now the resolution of the reference data set we were using before. So we call this process deep interpolation. And I'm just showing here the entire pipeline again, because you can see that the blue part and the orange part, those are the 2 different data sets, so the gridded data set and the observations, and they are decoupled. And this decoupling has some very nice advantages because it means you can use archive data, for example. So if you have an NWP output laying around, you can use it to train the model and then still apply it live on your observations as they come in. And also, if you ever tried to match observations and numerical output, you are probably aware that there is often a spatio-temporal mismatch because the simulation does not place your storm exactly in the location where it was observed. But because of this decoupling, it's no issue for us. And we can deal with this different temporal resolutions. So 1 hour in the gridded data, 5 minutes in the actual observations. This decoupling allows for it. Of course, there is a key assumption, which is that the reference dynamics are representative of the real data. So of course, this gridded data set has to contain a physically reasonable representation of all the phenomena we will see. Otherwise, the interpolation doesn't work. And I want to benchmark this a little bit with you. So you can see, for example, the gridded data here, and a very popular approach from literature is the Barnes interpolation. There are other approaches like kriging, but we're focusing here really on a well-known strategy. And you can see already, if you would use Barnes interpolation on the observations, you get a field in the middle, which is not very much following the terrain, just because there is no terrain effects here. But we will use it as a baseline. So when we use our deep interpolation fields, we will report all these metrics as always as improvement above the traditional approach. And also, since we're dealing with two different data sets in the top left, top right, you can always see if I'm dealing with the proxy data or with the real observations, just to not confuse anyone. So we did a little bit of sensitivity study because some people are a bit skeptical about deep learning. So we want to make sure that we really make a good case here. So how much complexity is needed? Because there are relatively simple deep convolutional neural networks. There are more medium complexity networks, and then there are transformer-based networks for those of you who are a little bit into machine learning. So basically, we're checking 3 different types of complexities here. And then, of course, at the stations where we have the observations, we don't only have the 10-meter wind gust, so the G10. We also just measure the average wind speed and the 2-meter temperature or 2-meter humidity. So from all of these, we can go through the same pipeline. So we can create these low fidelity polygon inputs and then use them as auxiliary variables to still support to predict the high fidelity wind gust. And this benchmark is what we've been doing, and you see the results here. So the complexity in the models increases from left to right, and you can see the colors denoting the different variable configurations. And it is quite evident that this medium complexity network performs well. So it seems that the low complexity network does not have enough capacity to really capture the complex wind gusts. And then on the right, this SWIN to T2 transformer, the high complexity model, that one is probably already too complex. So it has too many degrees of freedom to fit this data set, which again leads to a lower performance. And we also see that actually just using all the inputs we can get, so the terrain, the temperature, the wind speed and wind gust, all as input to predict the gust is the most beneficial here. But then you may think, okay, from a practical perspective now, how much training data is needed? Because we have the advantage here, we're using a historical data set in the US, which has 10 years of record, but maybe you're not in this luxury position somewhere else in the world. So you may wonder, how much data do I need? How much gridded training data do I need before I can run this approach? So we're actually using 4 years, 3 years, 2 years, and only a single year of training data. And I forgot to say it before, so this is the root mean squared error reduction compared to Barnes. So we're seeing we have a 30%, we're outperforming Barnes interpolation here by 30%. And we really see that just 1 year of training data already gives you quite a good of performance. And remember, you can use archive data because of this decoupled approach. And then the next problem is, of course, instruments can not only fail, they will fail, especially in extreme conditions. So then the question is, if we have temporal data, what about the spatial diversity? How many missing stations, how many NaN values in your data set can we tolerate? And here again, we were looking at how much does it change? How much does the performance change if we really have 100% of our network available versus only 3/4 versus only half of it? And here we see 2 very interesting things. If you focus only on the blue bars first, that means we were using Barnes also, the Barnes interpolation as a reference also in these reduced data simulations. So because we would expect that also for Barnes interpolation, performance drops if you have fewer stations available. But then the orange case is really what happens if we use the best possible Barnes. So really Barnes interpolation sees all the stations and our approach only sees 75 or 50%. And we still see that that we still outperform the traditional approach with the deep learning to quite some degree. So that is quite nice. And we also found from a technical perspective that that is actually really crucial, that already during training of the network, we simulate these missing stations by randomly dropping stations, because that will make the deep learning model very robust against these missing stations later in production. So does it all work? I have another video for you, hopefully. Or not? Okay, so the video does not play, unfortunately. You would see that it is working. So we have the sparse observations on the left, and we can nicely interpolate them to a gridded field. But there is an asterisk attached to the yes. There is always an asterisk, especially with machine learning. Okay, I think the laptop just doesn't like my videos. So the asterisk here is, we were also looking really at the tails of the distribution. So if you imagine the wind gust as a histogram, basically, then the extreme events where we really get extreme gusts at like 20 meters, 30 meters per second, those are very, very rare. So they are in the 99.9th percentile. And for machine learning models, this is really problematic because machine learning models try to not fit the outliers. They try to fit the core of the distribution. And that's why the performance of our current approach is not so good there. What we intend to actually do as a solution, oops. Let's see if this comes back. So anyways, we try to use radar data as a solution. Okay, yes, so this is what I was showing. So the problem is the tails of the wind gust, if you plot it in log distribution, are really towards the end where we have the very high the very high and impactful events. So this entire distribution is pretty skewed. But an idea we are having is to use the radar data I was showing in the very beginning as another auxiliary input, because it's a very nice complementary data set, because whenever we have strong events, often there is a strong convective storm. So that means these tails would be supported by having the radar input. And that is how we actually hope to improve this. So I was talking a lot about this. So in the interest of time, I will only very briefly mention now our forecasting approaches. And this is another video, so let me try if I can skip it. Okay, yes, so I'm not showing the video now because it's also not super interesting, because the problem currently is that wind gust, especially at a 5-minute temporal resolution, is a very dynamic field. So you would see that the analysis field we are generating is really intermitting. It's like lots of blobs turning up, and you saw it a bit in the beginning also when I was showing the video of only the observations. So this is very challenging for machine learning, where usually like very smooth and nice curves are beneficial. So at the moment, the actual forecasting 3 hours ahead, 5-minute resolution is not working super well. But like I said already, we have ideas to improve this. So we want to go with additional inputs like, for example, using radar. And there are also different strategies for those of you who are familiar with machine learning. You can either make predictions 5 minutes into the future and then feed it back into the model. That's called an autoregressive rollout. Or you can also directly go 6 5-hour steps into the future, for example. So then it's called a K-ahead prediction. So the conclusion of this is that this analysis part already is working quite well. So we are robust to missing stations. We outperform the traditional interpolation, and we are decoupled from synthetic data. And I was showing it here for wind gust, but it works for other meteorological variables. And the future steps are to improve this, that it really also works for the tails of the distribution, and to also improve the nowcasting. And we assume that in both cases, really having radar data, because the radar data will also give you a sense of advection of patterns through the field, will really help here. So yeah, we have a preprint submitted. If you want to, you can scan the QR code here. And thanks for the slightly messy talk.
Yeah, the mess was not your problem, not your fault. So, and also that we are actually short of time is not your fault. So that we still take 2 or 3 questions before the lunch break. So.
And
slide. Oh, slide. Okay.
Is it already open?
Yes.
Okay. Yeah, so because we work on, we work from the academic perspective a lot on AI, and you hear that AI is a lot of a buzzword, but since there are also quite some applied people here, I'm really interested in what is needed for you to also adapt AI a bit more, in case you're even interested in doing that. So by training, is that data or compute resources? So maybe you can specify that, or is it knowledge that is needed? Is it literature? Time, yeah. Yeah, the less hype part, I actually also get. That's why we always try to always explain a little bit more in detail how we actually obtained the machine learning models, because there is a bit of hype around it, but it can also be very useful when you do it properly. Yeah, data quality is also a big issue. That's why we are also struggling with the 5-minute data at the moment, because real observations are quite noisy, especially at such a fine resolution. That's true. Okay, maybe let me go to the next one. Oh, it's okay.
Also started with.
Yeah, and this is yeah, it's okay. So this is about this, like the state of the art, how much AI or data-driven techniques, because we saw some clustering here, we saw some interpolation. So it does not have to be like really deep learning. How much are you actually using in production already? It was actually quite balanced. Oh, not anymore. Anyways. Okay, maybe with 35, I go to the next. I think, should I skip this for the last one with the like more content wise? Okay, it's already people. Okay, so yeah, how high do you even rank the potential? That would also interest us. Okay, so quite some interest in that. And then I think there should be one more knowledge question. Oh, no, okay, then. Yeah, and do you see any specific use cases where you can imagine AI to come up? Okay, now casting, that's very nice to hear. Yeah, so I see a lot of observations and yeah, data assimilation, forecasting. Yeah, that's nice. So we're doing our best, but it's also good to hear that there is a general interest in that. Thank you. As I said. Yeah.
And the horizontal grid spacing of your model, is it limited by the model analysis which comes from the Energinet, or do you have additional predictors which would allow you to go to higher resolution?
Yeah, so the horizontal resolution in that sense is limited by, if you remember the two phases I was showing, by the initial, by a reference data set basically. So I remember you were talking about 100 meters. So if you have some LES, for example, or gray zone model at that resolution and you have a year of it available, then this should work. But I cannot comment on the quality of the analysis fields yet. But technically, it's only whatever data you have.
Hi, thanks for fighting the hype. Giving very much detail about how you do things in machine learning and AI, deep learning, particular. About the yet poor performance in forecasting in 3 hours. I was wondering whether you've considered including a larger region around the state of New York, both when it comes to the METOSWISS observations and the weather radar.
I assume your motivation behind this is to sort of have boundary conditions of like, or like advection that is going on outside the state.
Yeah, it's a really long time when it comes to advection or initiation of deep connection.
Yeah, so that's where we really hope that the radar comes in more, because radar doesn't stop at the state boundaries, but our network unfortunately does. So yes, we could, like technically we can improve, we can extend the domain, but at the moment we only have observations within the state. So the further outside you go out of the state boundaries, the less accurate currently the analysis fields become. And actually that is also why we assume that this is not working well yet, because basically if you have wind from the west, then the stations, like the model doesn't know what is coming in. So we hope that the radar comes in handy, or cross-state networks. Thank
you. We have to stop here. Unfortunately, then there's lunch. Let's go with the yellow door. And there also, if you would take us there, it's here, as I said, if I remember right, in the green room. Picture. I think to take it later.
And so first, we just want to say thanks to Max for. And our radio agent has arrived. If you haven't seen him here in the back, and he has reminded us that we should take a photograph before we go to lunch, because otherwise we don't know when we come out of the room and so on. So now we are all together. So please go out of the room, and there is a nice poster of EWD where we can place ourselves with a nice background. Thank you.
I should probably check the animations for that.
Okay, we have a second session on extremes. And in the schedule, we have 3 speakers, but I just wanted to ask, is Serihun Desalegn from Ethiopia here? Okay, doesn't look like it. So then we have only 2 speakers, which means that we can take your time. We can discuss maybe some questions that you wanted to ask in the previous sessions that you didn't get to. We can take those in this session. I'll just let you take it away. Thank you.
Thank you. Okay, so today I'll talk about deep convective cold pools, the potential impacts on wind energy from observations and from numerical modeling. And I'll focus more on the numerical modeling aspect here today. I'd like to acknowledge my co-workers, Jeffrey Thayer, who's here with us, and Norman Vodman. Okay, so to set the scene, here we see the distribution of wind turbines and the convective cell frequency over Germany. These 2 plots are from relatively recent papers in 2023. And what we see here is that the convective cells basically, while they regularly occur throughout Germany, they often tend to be concentrated in regions where wind turbines are particularly densely concentrated. And not only are wind turbines densely concentrated, but they're also growing in number year on year. In fact, the wind energy contribution has increased in the German energy grid from about 1.7% in the year 2000 to just over just over 34% last year. So that means it's becoming increasingly important to gain a more complete understanding of meteorological phenomena that impact wind energy output. Better? Okay. Now, that's better. Yeah, okay. Now, larger scale events, for example, such as cold fronts or mesoscale storms or low-level jets are relatively easy to forecast in advance with modern numerical weather prediction models. And I say relatively because some people will fight me on that. But shorter scale events such as thunderstorms that occur on shorter timescales and smaller spatial scales are much harder to predict. And that's due to the intrinsically stochastic nature of deep convection. Now, thunderstorms involve lightning, abrupt darkening, heavy precipitation, and the cold pool gust fronts that they produce lead to rapid changes in wind speed and direction at both hub height and near the surface. And this plays an important role in producing minuscale fluctuations in wind energy output. So the goal of the current talk and the current work is to try to quantify the impacts in terms of both observations and in terms of numerical modeling. In terms of observations, we have our DLR-operated wind park Vivaldi. Vivaldi is located about 50 kilometers northwest of Hamburg. And at this site, it's about just along the River Elbe. At this site, we have 4 years of data. I'll give a brief overview of the wind park here. The wind park is oriented in a line with the mean winds, with the met mast over here measuring the inflow fields. And behind that, there's the first of 2 wind turbines that are operational, 2 Enercon E115, 4.2 megawatt turbines. And behind the first turbine then is a met mast array, and that measures the turbulent wake of the first turbine. And then behind that turbine, there's another, behind those met masts is another turbine. And then behind that is going to be eventually a custom-built smaller turbine that's not yet built and another met mast. And on top of that, we have a fairly dense observational network on site, including 2 LiDARs, a nacelle LiDAR and a ground-based LiDAR. We have a microwave radiometer on site, a micro rain radar. We have a ceilometer that's been recently installed, and we're getting an X-band radar in the next few months or so. And on top of that, we have ground stations and whatnot. And with that, over the last 4 years, with all the data that we have, Jeffrey and I have documented all of the cold pool passages that we could find over the wind park. And we've recently had a paper accepted on this topic, where we found over this 4 years at the wind park, depending on the instrument, up to 120 cases. Okay, so this paper has just been accepted. It's in preprint in Wind Energy Science. And I'm not going to spend too long. This is the only slide I have on the observations to hear today. But if you want to speak more to Jeffrey and I about the observations, please find us after the talk, or about the wind park. We can tell you more. Okay, so I'll briefly go over the main findings from this observational paper at the wind park. Here I'm showing in the blue the wind speed difference. In the light blue, the wind direction change. In the pink, the estimated power output change. And in the red, the virtual potential temperature change at hub height, and the changes from the background flow, so half an hour before the impact of the cold pools, where T0 is the time of impact. And we show in the darker curves, in the center, these are the median values, whereas the shaded regions show the 90th percentiles. And what we see is that the observed median hub height wind speeds typically increase by about 4 meters per second, with that increase in wind speeds typically lasting about half an hour as the cold pool passes through. And that's for the median case, but for the 90th percentile cases, that increase in wind speeds can be as high as 8 meters per second, just over 8 meters per second. And of course, with this increase in wind speeds, there's going to be an increase in power output. And for the median case, that's about 50% increase in power output compared to the background flow, lasting again about half an hour. But for the extreme cases, that can be between 100 and 150% power output, again lasting roughly about half an hour. In terms of wind direction change, the median case tends to come with a wind direction change of about 20 degrees. However, for extreme cases, that can be up to 60 degrees. And that, of course, would lead to some negative impacts on wind turbine operations in terms of the turbine not being able to yaw on time. In terms of temperature drop at hub height, from the met mast, the median drop is about 2 Kelvin, with extremes of 4 Kelvin recorded. However, those values are typically stronger near the surface. Okay, so this is the overview from the observations at our point source Vivaldi in northern Germany. And the question here is, can we see a similar, or do we see a similar impact convective cold pools throughout Germany. And here the sample size of 120 cases is a bit too small to make general statements. So to do that, we need to quantify cold pool characteristics, bulk characteristics. And in order to do that, the best way that we thought to do it would be to run numerical simulations. So we run the WRF model with the aim of answering the following 3 research questions. To what extent can WRF reproduce the bulk observed convective characteristics over Germany? Before we can make any statements about wind energy, we must first validate the model, and we do that against the Deutsche Wetterdienst's radar network output. The second question then is, how do convective cold pool characteristics relevant for wind energy evolve through a typical convective cell life cycle? At what point during a convective cell life cycle is the impact the largest? And the third is a bit more general. Are convective cold pools a significant factor for wind energy applications? If you're an operator of a wind park, do you even care that there's one coming towards a wind park? Should you care? We'll try to answer that. So we're using the WRF model, the Weather Research and Forecasting Model developed at NCAR. And our setup is as shown here. We have 2 nested domains. Domain 1 has 5 kilometer grid spacing. Domain 2 has 1 kilometer grid spacing and covers roughly the network of the Deutsche Wetterdienst operational radars. We make a direct comparison from the output in WRF to the observational network. And in order to do that, we also output WRF data every 5 minutes in order to get the exact same temporal resolution as the radar data. We run a simulation, a single month simulation for July 2023, the full month long with 5-minute output of 3D fields. It produces a rather large data set. And in order to compare the convective elements in both WRF and in the observations, we use this open source Python package called Tattoo, which allows us to detect, track, analyze the life cycles of convective systems, allows us to connect systems in time. It's quite similar to the DVD's Conrad system, if anybody knows that here. Okay, so to give a brief overview, the animation works, that's okay. To give a brief overview of what the simulation looks like, compare the observed and the simulated convection. Here I show an animation on the 3rd day of the simulation, so the 3rd of July, and just after midday. And we focus in on northern Germany over where our wind park will be located. And what we see is, so I'm picking a data that's particularly convectively active over this region, but I'm not cherry picking anything here. You can basically focus in any location at any time during the simulation, and the results are roughly similar. But what we see here is we don't find a one-to-one placement or simulation of the convective cells observed by the radar network, and we wouldn't expect to do that because, again, the stochastic nature of deep convection, that's pretty impossible to do. But what WRF is doing reasonably well is capturing the general location of the convection. It's capturing the background flow really well. It seems to be capturing the morphology and the strength of the convection reasonably well. So we can go one step further and try to quantify each of these convective objects and compare them to the simulated convective cells to the observations. And I show here for the entire month-long simulation, every convective cell that we've detected at every 5-minute output, so every snapshot of convection. I filter for cells that must have at least 1 grid point with 46 decibels. So I'm filtering for the stronger convection, the convection that likely produces lightning, that likely produces convective cold pools. And in both the observations and in WRF, we have roughly 90,000 cases, so it's relatively comparable. And I show on the top the mean reflectivity within a given convective element, and on the bottom in blue, I show the maximum rain rate. And what we find, is that WRF tends to produce slightly stronger mean reflectivity on average, but it does a reasonable job of capturing the observed distribution of convection. The mean and medians in the mean reflectivity is relatively good. However, WRF tends to do a slightly worse job when simulating the maximum rainfall, with the mean and median in WRF tending to be about 6 to 7 millimeters per hour stronger. And this is a known bias in WRF. It's been found in other studies. WRF tends to exhibit a positive bias in terms of very high rain rate. Okay. If I move on to convective cell life cycles, so here I'm looking at convective cells where I can connect in time for more than 3 time steps, so at least 15 minutes. I'm also filtering for stronger cells that must have at least 1 grid point with 46 decibels, and I remove any cases that undergo splitting or merging. So to keep the analysis as simple as possible, we're focusing on cells that are basically isolated convective cells. I split the analysis into two different parts. Shorter cells are shown with a solid curve, while longer cells are shown that live longer than 1 hour are shown with a dashed curve. And again, I'm showing here the mean reflectivity and the rain rate as before. So what we find in terms of life cycles is that, oh yeah, one more thing, the life cycles are normalized by cell lifetime here. So what I find here again is that the convective cells in WRF tend to peak earlier in intensity. From the very first detection, the cells are stronger in WRF, and they attain a slightly higher maximum intensity throughout the life cycles. The high rain rate bias is confirmed again in WRF. The convective cells are raining stronger in WRF throughout the entire life cycles. So that's just something we have to live with in WRF. In terms of convective area, the size of the convection, we find similar results to previous studies performed by people working at Deutsche Wetterdienst, Katrin Wapler, 2021, and Wilhelm et al. 2023. We find this upside down parabola archetype. So that basically means that the convective cells tend to peak in size about halfway through the life cycle. And we find similar results in both observations and in WRF. However, in WRF, the cells tend to be slightly smaller. So we get smaller, more strongly raining cells in WRF. In terms of convective shape, however, the results are remarkably consistent. In both WRF and in observations, the convective cells are not circular, they're far from circular as you find in idealized studies. Instead, they have an aspect or ellipse ratio or an aspect ratio of about 1.6. And that is remarkably consistent throughout the life cycle. Convective cells don't tend to change their shape with time, which is a bit surprising. Okay, so now that we've basically highlighted the biases in WRF and compared against the observations, now I'll go on to variables that I don't have observations to validate against, so we're going to have to trust WRF a little bit from here. Here I'm showing life cycles of the 2-meter virtual potential temperature difference on the top left, the 2-meter saturation deficit on the top right, the static stability over the rotor blades in the green, and then the 10-meter wind speed anomaly in pink. And what we find here is that in terms of strength, convective cells in terms of strength, both temperature drop or temperature difference and 10-meter wind speed perturbation, again, tend to peak about halfway through the convective cell life cycle, whereas saturation deficit tends to decrease with time. And that makes sense because the environment of a cell, the more that it rains out, the more evaporation that you have, the more the reduction in the saturation, the more the increase in saturation, the reduction in saturation deficit. And because you're evaporating, or the rain is evaporating as it falls out, there's also evaporative cooling occurring. So that means that the environment under the cell is stabilizing. And we can see that in the static stability. So the environment, so the pre-convective environment from the first detection is close to neutral for the median case, but the longer the cell lives, the more stabilized the environment becomes. Okay. In terms of wind energy related variables, here we're looking at the 100-meter wind speed in WRF following a cell and the estimated power output from a simple piecewise relationship. And what we find again here is that the wind speeds tend to peak about halfway to 2/3 through the convective cell life cycle, which also leads to peaks in estimated power output at the same time. And we can go one step further then, and we can try to isolate the effects of the convective cell alone, or for the gust front alone, compared to the background flow, to see what the increase in power output due to a convective cell or a median convective cell is. And when we do that, we find that there's an increase of power output, estimated power output, between about 35 to 60% for longer lived cells, 33 to 50% for shorter lived cells, with the largest increases occurring roughly halfway to 2/3 through convective cell life cycle. So that means that if you're standing at a wind park, if we're standing at Vivaldi and we see upstream a convective cell developing, if that cell is just newly forming or decaying, we should expect for the median case at least 33% or 30 to 33% increase in power output. If that cell is in its peak strength about halfway through its life cycle, the power output increase could be up to 50 to 60%. And that's for the median case, not for the extreme cases. I'll show briefly, since I have a bit of time, I'll show briefly what we're currently working on. So we went through this data set, this month-long simulation focused in on our wind park, and looked for the strongest convective cell that we could find, the strongest cold pool that we could find. And we've re-simulated with nested domains down to large eddy simulation mode in WRF, included a generalized actuator disk, so a turbine parameterization in WRF. And we've simulated this passage of this cold pool over a 2-hour period with 20-meter grid spacing. So this is really, really high resolution simulation. And this particular cold pool, we can see from the red curves in the top left there that the background flow for each of the 2 turbines is roughly between 8 to 10 meters per second until the cold pool comes through. There's a sudden increase over really about 2 or 3 minute period up to 22 meters per second. And then those increased wind speeds tend to hang around for a solid 5 to 10 minutes or maybe 15 minutes, and then drop down to the background flow slowly after. And then of course leads to associated increases in rather large increases in power output. And the idea what this current work is to try to quantify the effects of cold pool passage on wake structure. And this animation starts again, you'll see that the pre-environment before the cold pool comes through is rather convective. You get, I'll wait for a second. No. So the whole fields are quite convective. You get these streaks occurring that maybe come from terrain that are maybe in the outer domain. And then about half past, just as the cold pool begins to pass through, you get to see the turbulent structure of the leading edge of the cold pool. And the increase in wind speeds occurs really over a 2 to 3 minute period. And we get a feeling for the wake structure in the convective environment. And as the cold pool passes through, the signature is really quite lost completely. And then about 10 or 15 minutes later, the environment following the cloud is more stabilized. The wake length, the wake duration, the wake deficit is stronger. And it takes longer for the wake to recover until the environment recovers from the stabilization from the evaporation of cooling. And it does that towards the end. So there's a period maybe after a cold pool passes through, about an hour long, where there's increased stabilization. And that's more important if you have a wind park with many turbines, that you will have wake interactions lasting longer. Okay, and I'll skip the conclusions and go to Slido, or do we do that later?
No, forget it.
Oh, there. We have a few Slido questions. I'll let you.
Thank you. So we start off with a very general question. How relevant are convective gusts to wind energy? Do you feel that these are important? Should we put work into quantifying them more to? I'm glad we don't have any irrelevance. That's means we haven't been wasting our time.
We're missing some wind turbine manufacturers here.
Yeah. Well, I think the next question is literally for those wind turbine manufacturers. So, wind park operators and turbine manufacturers would be interested in improving thunderstorm wind gust nowcasts. I mean, for the stronger cases, very clearly, I think that would be interesting.
Would be or shall be?
What's right?
With the convective gust nowcasting, you're not getting a day ahead forecast or nowcast. You're getting really only a few hours notice. But if you're an operator at a wind park, does that help if you see a gust coming through and you know that the wind direction change is going to change by up to 60 degrees? Does that help you plan accordingly? If you've got many turbines in a wind park and then you have several shutting down because of safety features going awry, and you know that the gust is only going to be 15 minutes long, is that useful? Saves people going out on the weekend to restart turbines. Of course, it's not just increased wind speeds. We've also seen previous talks, hail being an issue, as you have stresses on the turbines, of course, too. Lightning comes through, and of course, there's abrupt darkening with convective deconvection, which would impact solar. So you'll get an increase in the wind power, but a reduction in the solar. So there are multiple aspects of pole pool passages or convective passages. And of course, the heavy precipitation too. We've seen some events in southern Germany where heavy precipitation plays a big role with flooding and whatnot. Of course, this is the answer that I want, so.
Okay, 32 seems to be the number that we're getting.
We have one more question. That's the quiz.
Okay. Oh, yeah, Mr. Vivaldi.
Yes, right there. If we have time.
Okay.
When you need to have to, okay.
So we showed in the slides of the observations for the wind park, the 90th percentile. But we looked through our 120 cases and tried to find the maximum wind gust. And the gust is the difference from the background flow. So not including the background flow, what is the... Yeah, yes, that's... If we name our pole pool.
Going to be part of it.
Oh, okay, okay.
There will be a winner, so whoever is taking part will be a winner or a loser.
I was expecting the numbers. Okay.
But that's coming when enough people have signed up.
Okay. So the question is, yeah, what is the maximum gust that we found, or we detected at our wind park from a cold pool passage?
Percent?
You've already input the correct answer, have you? What did they win?
Where's the correct?
No, the correct.
No, activate.
Okay, you know the answer. You can't take part.
15 seconds. It feels like there's a timer, so quick.
Do we know the winner? Do we know who it is?
Yes,
Do we know
yes. So
what it is?
this is the correct answer. The 14.5 meters per second. That is the strongest gust we've recorded. And so that increased with the background flow was something like 8 to 10 meters per second. So the total winds would have been close to 25 meters per second with the gust coming through. Okay.
Okay, are there any questions for Tara?
Very quick,
Yeah.
otherwise we run out of time.
No? Well, I guess then we can move on.
Okay, thank you.
Thank you. Speaker and last speaker of the session is Gregor.
Jetzt gerade im Bildschirm. Pauli macht ein Studio gerade mit dir aus.
Nein,
Also bin ich mal nicht sehen. Und doch nicht. Was ist? Ah. Ne, und dann. Aber vorhin schon mal so. Wo sind die auch? Leider. Jetzt haben wir das weg. Das kann man gleich nehmen. Das war gerade eben. Also wie das ist. Das ist ein Zweck. Wo waren jetzt eins? Aber ist du das da eins meinst? Ah, ja. Mal in vollen Modus gehen. Menü. Ja, das sieht man ein Problem bevor. Why don't we see them? Green.
Ist das ein zweiter Bildschirm? Ach, sie teilen, ja.
Ah, jetzt kommt's.
Ah. Wir haben das gemacht.
Okay, now we can start. Thank you. And welcome everybody to my talk about a rather specialized product which has been developed in cooperation from DWD with the German TSOs. And the question was, can we define weather conditions that pose a risk to power lines? And yeah, there are, of course, lots of weather situations that can pose a risk to power lines. And some figures I always show in these talks are the most extreme impacts on power lines or even the towers themselves of weather conditions. So 2005, there was a huge winter storm over the western part of Germany, and many towers collapsed because there was ice on the power lines. They were very heavy, and then some wind just made them collapse. And on the right-hand side, there was no ice, but only strong winds, which led to the collapse of some towers. And yeah, as you can imagine, these conditions have, of course, lots of impact on the grid operation. And they are called ECs, like exceptional contingencies. They, of course, affect the power grid operation, and they are attributed to critical weather conditions because the TSOs say if they find some contingencies in the network in the grid, and they do not find any technical reasons for this, yeah, then there must be some other reason, which then is most likely the weather and these conditions I showed before. In the user dialogue with these TSOs, we defined over the past few years criteria for critical weather conditions, for example, freezing rain or only strong winds. And yeah, these criteria are evaluated and further developed over time. And at the moment, we are working on include also in-cloud icing. A few more details on this will follow later. And what happens under these weather conditions? We get often galloping power lines. So if we have only the power lines or even ice on the power lines, they are more affected by winds, and we can get these horizontal oscillations. And another problem is if the power lines are iced and the ice falls off, suddenly we can get vertical oscillations, and these oscillations can cause problems with the power lines, and the TSOs want to get warnings when weather conditions might lead to these situations. And before I go to the details of our method, what we do, I want to give a few words on the model we use, which is the DWD's operational numerical weather prediction model, the ICON. ICON for icosahedral non-hydrostatic model, which is a global to regional numerical weather prediction modeling framework. And for these warnings, we use two regional configurations. The one is the ICON EU EPS, the top picture here, which covers all of Europe and a bit more. And the other regional configuration is the ICON D2 EPS, D for Deutschland, Germany, with a 2-kilometer grid spacing, which covers Germany and neighboring countries. So both configurations are the EPS, the ensemble prediction systems. So we produce probabilistic forecasts with them. The big differences are listed here between the two. We have 13-kilometer grid spacing in the larger domain and provide 4 forecasts a day, initialized at 0, 6, 12, and 18 UTC. And with this configuration, we have a forecast horizon of up to 5 days. And we have 40 ensemble members. In the ICON D2, we have a much finer grid resolution of 2 kilometers. Therefore, we have 8 forecasts a day, every 3 hours initialized. But therefore, the forecast horizon is only 2 days, 48 hours, and we have only 20 ensemble members. And what can we do with these with the model output? So at the moment, the current implementation is that we follow an empirical approach that the TSOs over the last years have a list of events that occurred where they observed ECs, exceptional contingencies, and then we look at the weather situations during these situations and define common weather conditions in these situations. And for instance, we now see that we had lots of precipitation and the temperature, 2-meter temperature within a range of -3 to +1 degrees Celsius. So more than 15 millimeters in 6 hours precipitation. And if we now see these conditions in the weather model, we can calculate from the ensemble prediction system a probability for these events to occur. A second criterion is the icing and wind. So again, we need precipitation, not so much, but 5 millimeters in 6 hours, and the temperature again in this range. And if we then have wind about a certain threshold, 10 meters per second in the wind gusts, this can also lead to critical situations. And then the wind alone criterion is that the maximum 10-meter wind gust exceed higher thresholds of 29, 33, or 36 meters per second, and then we give out warnings on different warning levels, 1, 2, and 3. And from our probabilistic forecasts with the ensemble prediction systems, as I said, we predict probabilities for these events to occur, and then we can determine warn levels, so that we say if we have very low probabilities of maybe 5 or 10%, the model says there potentially can something critical occur, but the probability is rather low. And we can, of course, increase these probability values and say if the model produces with 80, 90, or even 100% such situations, you can be very sure that something critical will occur. So, and these warnings we give out to the TSOs, but from the models themselves, we get, of course, these maps over Europe or over Germany. And for the TSOs, we developed a specialized product where we map these gridded fields down to the assets of the TSOs. So we get coordinates from the TSOs where they want to get these warnings for. So the black line is one example for an EC line, how we call it, so an asset which shall be warned. And we see all the dots that are the model grid points for the ICON EU with a distance of 13 kilometers and the ICON D2 with a distance of 2 kilometers on the right. And then we can say we want to include all grid points within a certain radius or the nearest neighbor grid points to these power lines. And then we check all the grid points that are within, for example, this blue polygon here, and then search for the maximum probability within these regions. And if the maximum value of all these grid points exceeds the threshold we define, then we get a warning for this EC line. And an example here for a line in the southern part of Germany, which reaches to to the far south and to Austria, especially here, to higher altitudes where the Alps are, and we see that at few grid points here, we have very high values for the wet snow freezing precipitation criterion with a high probability threshold. And we always look, of course, for the highest values. And we see for the freezing precipitation wet snow criterion, we would get the 1 level 3. For the wet snow freezing precipitation with wind criterion, we get only 1 level 1, but in the end, of course, we are interested for any of those. So this would be a 1 level 3 for this asset. Yeah, so as I said, the criteria as they are implemented at the moment are based on these empirical approaches, and a bit of an outlook, but we are quite far with this, is that we want to change these empirical definitions of the criteria to literature definitions of icing rates. And there are different processes that occur. So this is, they are pretty different in what happens. So the freezing precipitation, we see a nice picture here. We have like 6 centimeters radius ice built around a power line. So you can imagine this can have some effect on the power lines and how they behave. So the conditions in literature say we need, of course, for freezing precipitation and the wet bulb temperature below 0 degrees Celsius. So wet bulb temperature is a combination of relative humidity and temperature, no details here, but there are ranges given that we can calculate. And then we get the icing rate in kilograms per square meter in second. According to the formula here, we just need the precipitation rate and the wind speed. The same we can do for wet snow accretion. Again, we have a nice picture, which is on the same order of magnitude, I would say, where ice was, or wet snow accumulated around a power line. Again, we need precipitation, the temperature within a certain range, and the absolute air temperature below 2 degrees Celsius. Then we have, again, a formula for the icing rate, where we need to put in the precipitation rate, the wind speed again, and also the fall velocity of snow, where most of the time a mean value is taken, which is like 1.7 meters per second that snowfalls on average, that snowflakes on average fall with. So we have these two formulas where we could calculate the two criteria that we have already, wet snow and freezing precipitation. And as I said, we also want to include the in-cloud icing. In-cloud icing is a bit different. Again, a nice picture here from a study in 2009. So there, for this type of icing, no precipitation is needed, but we need high relative humidity and pretty cold temperatures. So this is usually conditions where we have fog, and if there's fog, there is no precipitation at the moment, but very high relative humidity. And then if it's cold enough, we get rime ice on the power lines. And then if the conditions are fulfilled, we have a factor and multiply it with the wind speed and get again an icing rate. And for the warnings in the end, we do not need to distinguish which process led to the icing, but we just can sum up we can calculate all the three types and then build the sum of the icing rates, multiply with the time we are interested in and the diameter of the power line, and get then an ice mass per meter power line. For these ice masses per meter power line, we can define critical thresholds where the TSOs again can say, okay, the power line has no problem with, I don't know, 100 grams per meter or so, but if we exceed a certain threshold, it becomes critical. So then we can calculate this from the model and calculate again the probabilities from the ensemble, define probability thresholds where we want to give out the warning levels again, and then have this product on a new basis, on a more literature-based basis. And yeah, I have put three figures here next to each other that you see that all the processes produce very different types of icing, so it's important to have all the three of them included in our warning product. Yeah, with this, I have a few take-home messages on this slide and a few nice produced pictures of the processes here, maybe. So icing of power lines, of course, endangers the safe grid operations. Our product, the EC Warnings, is a user-specific product for the German TSOs. But what I've not said so far, the probability data sets, so the gridded data for these probabilities, are available via our geoserver maps.dvd.de. So if anybody's interested, please contact me later or go to this website, and yeah, I'm happy to answer some questions now.
Maybe we'll do some slide first.
Yeah.
I'll just let you.
Yeah, yeah. So just which are already taken into the into account in the EC warnings. The three, yeah. Who was right? It's part of the summary, let's say.
Can only choose one.
One? Ah, okay. That's too bad. I thought it was multiple choice. Okay.
I just changed it.
Huh?
No. Maybe it doesn't work after.
Unfortunately, the one on the top we've not yet included. We're working on that, but very nice, seems to be very important. So yeah, and the other three.
Oh, now it's working.
Okay.
Yeah.
But yeah, to shorten this, I mean, yeah, that's the one that comes with the next version of the tool.
Now the in-cloud icing is going back. But you can see it's
very good.
Important.
Yeah. Yeah, and the strong winds alone are also included in the current implementation. Next question. Bit details. How often do we update the warnings based on the Icon D2 EPS? And maybe some know about the model and 25. Oh yeah, that goes into the right direction. Yes. So every 3 hours, Icon D2 is initialized. Very good. And yeah, more a question of interest from my side. What other weather phenomena might be interesting for TSOs or DSOs that might affect safe grid operation? Yeah, I saw this in one of the previous talks, and I'm very interested in this. Yeah. Thunderstorms, yeah. Thunderstorms, yeah, we are working on this, let's see. Right, maybe. Flooding and flash floods, yeah, that's what's on my mind as well. Yeah, we are in preparation of a product that includes also lightning. So if we have flashes that strike the towers, depending on the surface they are standing on, that can cause problems as well. Yeah, so that's another type. And the high temperatures, I'm happy to discuss later, maybe with those who answered this. Yeah. With this, I think we're done. Thank you.
And any questions?
Yeah.
Yeah, thank you. So it's easy to imagine that this is important for TSOs, but if you give them a warning, what do they do?
Maybe we can ask the TSOs.
So in our normal calculation, in our normal security calculation, we always calculate one failure of one network element. And these exception contingencies, when we activate these, we calculate multiple outages based on one cause. So every line which goes over the tower, which is warned by DVD, will be then calculated as an outage. And therefore we see how the situation, or how would be the situation afterwards, and also the dispatch for that.
Is there any other?
I guess like 99% it would be the same. So in this event where there would happen one of these very large critical failures, the possibility of actually saving one of these electricity masts is basically non-existent. But yeah, the preparation and the insurance of having the right resources at the right positions to mitigate the worst parts of the incident is like was just said in the security calculations in it as well.
Yeah, I think the aim is to keep the regional extent of an outage as small as possible in the end.
Yeah.
Did you also take into account in your calculation of the icing that the power lines itself is when there's no load, they will have ambient temperature, and when there's a load, the temperature is higher. And did you any do verification so far of your model?
So first, we do not take into account the heating of the line itself, because we do not have the data how much warmth will be generated by electricity there. So that's on the side of the TSOs. If they know this line is fully captured at the moment, then there might be the risk very low for the icing. And verification, it's a rare event, let's say. So we have some data from the TSO where they said there were these and these lines and coordinates that were affected. And we can then say and check the model if we got warnings for these lines in these cases. Yeah, so we do this kind of verification at the moment. But as it's rare events, the product is designed in a way that we get many more warnings than events. So over warning, we call it. Yeah, so normally these events are captured.
Thank you. Perhaps a little bit a stupid question. How do you deliver the data? What kind of data transfer? What kind of data format? And how are they processed? Let's say TSOs. That's a question what came always into my mind. Obviously, yes, very critical events, but also transferring the information in any kind of action. I guess that's also a pretty important question here.
Yeah, the first part I can answer. So this is a specialized product for one of our key customers from DWD. So we push these information in tables, CSV tables to the customers, and they get this information updated every 3 hours from us. Internally, how are they?
To an SFTP server, and then we shift it to another server where we also host some services also for other TSOs, for example, for security analysis, and then they will be included in the processing.
So I assume there is a certain line section involved when the warning is getting active, and the line has a special ID, and then you match the ID.
Yeah, we have also. Correct. Yeah. The warnings are based on ID, and in our system we see what line are connected to that ID and can calculate that.
Maybe that question is I would like to take it one step further, because now you have implemented it, and I know a couple of other TSOs that have implemented it. But it's a very complicated process, because generating a warning is one thing, but how have you been finding out what should be warned and when should it be warned? Because one of the things is if I warn about something at a certain time, the next forecast will be different. It can be
stronger or less strong, and it can also vary. And how, just if you can elaborate on that, because I think this is a very important question that is often overlooked, that we need to understand what and how often. If I want too often, an operator will just ignore it. And if I want too little, the operator will not be prepared. So how did you find this threshold?
Well, that's a tricky topic. But as Leo also mentioned, there's two sides we can narrow it down. So on one side is our asset, which there are norms for it. Which wind speed they have to withstand. So on that side, we have values. We can see, okay, these forecasting values are really critical because our asset is not suitable for that. So it's over the limits of the assets directly. And the other part is empirical, where we see certain events, and then we look at the weather data on that timing and see what weather really occurred and what will cause the outage. And the other side is the system operation guideline, which clearly say if we have increasing probabilities of these kind of outages, we have also taken these into account. And that is a rule, and therefore our operators also acted and try to heal these situations as best as possible.
So that's a very important point, and you get one more question to that, because it is a long process to find this. If something has to go into an operator guideline, we know that this is a long process, even if this should be changed, I guess.
It's only not a question, but the second part of the answer about the jumpiness of the weather forecast, which may change the warning levels from one forecast to the next. And this is something I'm really happy about, is our collaboration with the TSOs include analyses from their side as well. So they analyzed the temporal evolution of our warnings from one forecast to the next, and we identified very few examples where the warning levels were jumping too much. So this was actually reassuring for us that our weather model is pretty consistent, which doesn't mean that it's right, because I think sometimes it needs to be inconsistent because the weather situation has changed, and therefore the knowledge about the weather situation has changed, and therefore the forecasts need to change. The second thing is that you said it already, we overwarn, so we release more warnings than have been actually observed, which is another problem, the observations. But the thing is that we have probabilities, so it is intrinsic that we warn more than has been observed. So I think the mindset need to be changed in order to understand probabilistic forecast information, and this is something I think we had quite a success. And I'm very thankful that we had this chance to work together closely.
In the end, I mean, you can calculate a cost-loss ratio for things like this. So how often would you do something that is cheap in relation to, if you do nothing, you have one event that you miss, and then you have a disaster also. So therefore we overwarn. And the jumpiness, just one point, we very much improved this behavior with the introduction of the ICON D2 EPS with the 3-hour update cycle, which was introduced about 1 year ago. And before, these warnings were based only on the ICON EU, where we very often had jumps from one level 3, then one level 1, the next initialization again, one level 3. And this very much improved with the ICON D2. Yeah. And we easily filled the gap of the missing talk now with the shared talk.
Thank you, Gregor.
We'll move right into the panel discussion.
And we get some, I think it's probably easier if we get some chairs.
How many chairs do we need?
How do you mean? Ist ja abbrechen, oder? Ah ja, ist vom
Quickly speaking, the break was only in an hour. But
Ich meine, wenn sich die Panelisten mal hinsetzen würden.
ja, versuchen wir die.
Hi, Irene. Nice to meet you. Yeah, definitely. Put a face to the name. How was it?
This morning, not so sure.
Yeah, I woke up at 5. I completely fixed up the date yesterday before going to bed. I thought that the workshop is supposed to start tomorrow. So I got a panic attack when I woke up. And I had the opportunity to switch my flight to this morning at 8:30.
Yeah.
So, yeah. Yeah, 1 hour. I was lucky to have found the plane was completely empty. Yeah. Surprisingly.
Almost.
No, not. Was okay. We should have let's see. We were.
Kommt da gar nicht rein,
I have no. I don't think that's going to be a manager.
I know it's very difficult to concentrate, but the plan was actually to have the coffee break, the next coffee break after the 10 minutes. But I can see that it's getting more and more difficult. So, but I want to give you another break before we go into the last session, so you last for until the end. And we
I also want to include you if there are any questions that you have while the panelists answer the questions I have been preparing, then just raise your hand and we get you in. So the reason why I wanted to have a panel with, again, the three pillars of our community, the system operation or the system, the power system, the market, and the input, the meteorology part, is that we start having these dialogues and get to use to talk to each other with certain topics in our mind. And so that's why you have placed yourself quite randomly, and that's also fine. So I have invited Irene and from Geosphere in Austria and Vanessa, and Irene has, everybody knows last year there was a real extreme event in Austria, and so it's quite it's quite vivid in the memory still. So so that's why I thought she's a good person, and then she's involved in the energy meteorology part, as well as Vanessa from DWD, who has been telling us a little bit about what she's working on earlier. And then I have invited Mohamed Diallo, and you will hear from him tomorrow. He's coming from the trading side and from Engie, and he knows everything about, well, everything about the extremes, as Detlef also told us this morning about how the market gets nervous and how the market reacts when it comes to extremes. And extremes are, as we have learned this morning, also prices. If the price forecasting shows that there are extremely negative prices, then this is an extreme event for a trader, I guess. And so we have different extremes. Then I have invited Hamid Bastani. He has been in the energy meteorology group at WMO for many years and has left now and is still working in projects, but as a consultant. And he has a lot of insight into the WMO, the World Meteorological Organization, and all the data and all that processing of how we actually get to the forecasting and how we process these observations and what is needed and how it's needed and about the quality of data and all these things. So that's why I have invited him. And then, of course, Martin from the CSO side, from the system operation. And now I have told something about you from my perspective as the moderator, but I would also like to maybe let you tell in one or two sentences about what you are most concerned about in your organization and why you have been motivated to come here, and for Vanessa maybe to host us here to discuss extremes. And I don't know whether I start with Irene.
Yeah. I think we are more concerned with all the extremes that happened in the past, let's say, 5 years, the intensity of extremes, how they change with the changing climate and what the impact is, not only on the power grid, but in general, and how we can actually tackle this and see this, because also we don't have the data for proper verification for the extremes or enough data. Also, again, independently of the power system or metrology. And the reanalysis data set don't capture that. So I see the critical point in extremes and verification of those extremes.
Thanks. So to answer this question, I will answer based on the perspective of my former role and my current role. So in my former role, I was focused on the extreme, which is related to the pre-feasibility of wind asset, meaning what would be the wind speed that has statistically the probability of being overpassed once within 50 years. So if you select your wind turbine, this wind speed will determine the class of wind turbine that you will have, and it will have an impact on the financials of the project. So now that I've switched into the trading market, here the impact of the extreme, for instance, if we continue with wind, will be if we go above the cutoff wind speed, then it will have a high impact on the day-ahead or intraday market. So it's nice to have this both duality, this both vision.
I think I would place your question a bit different, because the concerns they form into the needs we need to discuss here, and I would like to stress this, that we are in an interdisciplinary group where we share very different knowledge and expertise, and perhaps data. This goes into the direction of verification, because it is a very, we need a lot of different knowledge to bring together and to tackle these these questions about how to deal with extremes. And I think what I'm concerned about is that we not often talk about this together, not often enough, in order to understand each other and to find a common language, and then to identify the things we need to do, and to find solutions for the problems ahead.
Yeah, I think just to break in, I think this is something that we just saw in the last session, that a warning system can be part of an operator's guideline is something that you need to know if you start thinking about how this can be implemented. Because if I know that I have to go through an entire set of standardization, then this is a quite different thing than if I just have to change an IT solution. So just knowing about all the regulations is something that we often underestimate, that if you don't know about it, you think, why don't they do this? And it's these discussions here that are really important to understand each other's requirements, needs, but also restrictions.
Thank you so much for your invitation, and I think you mentioned correctly my role at the WMO, but just to emphasize that I'm not representing the Meteorological organization, but sharing the information that, the knowledge that I got during the past 5 years within the organization. I think what is interesting for me personally is the evolving change of the extremes in the changing climate, and the fact that the intensity, duration, frequency, the shift in the onset of the extremes, all are changing under the climate change. All the reports of the IPCC International Panel on Climate Change and also WMO confirms that. And obviously it has a great impact on the grid reliability and in general on energy systems. This is one aspect that I'm really interested about the workshop, but also about data sharing, as it was mentioned, specifically among energy and meteorology communities. And I will elaborate more on that later.
Yeah, I think one thing I have learned this morning that I found very interesting is that, now I have forgotten who said it, but that the turbine data above 100 meters, this is known because of the aviation security. And then I get this question in my head: why is the power system not equally important than the aviation area? And
we have some people from the aviation area here in the audience, and maybe they can also tell us or think about how can we get that knowledge, and the way this is totally normally shared in the aviation area. That kind of information is very difficult to be shared in the energy or in the power system, and between the actors of that. So I'll leave this for now and let Martin also tell his motivation.
Thank you. So, considering the biggest challenge of these extreme events and the grid operation, I think my answer from a TSO and from an Energinet perspective is quite close to some of the things that have been said already, that the playing field of these extreme events and the probability, the frequency of these extreme events happening to an extent we haven't seen before, really puts pressure on our core exercise at Energinet, which is to deliver security of supply for an affordable price. Like, how do we make that distinction between, should we start procuring reserves for some very edge case? We might have to, because we see that these situations just keep evolving and they become more frequent, they become more intense. But then again, to expand on these reserves really takes some political power, and who in politics wants to pay for something you're not sure you're going to need? So it's really a balance between those that are on my mind.
Yeah, so that was a very good point, and I may want to give this back to the trading and the market perspective, because we can see everything the point is the money. So a trader wants to earn money. Really, we all need to earn money to feed ourselves. But the market doesn't always react system conform. So the system operators also are often in trouble by the way the market acts. So when it comes to extremes, and let's take a weather extreme, because that's maybe the easiest to start with. If we take a weather extreme, then we often see that all traders or many traders act in the same way, and that generates also negative prices. So maybe you can enlighten us a little bit. Why is this kind of, I do what everybody else is doing?
Maybe before coming to that, I would like to come back to what you said earlier about having some reserve for an event that we are not sure will happen. If we focus on the economics of it, in the balance market, I've seen some price of 7,000 euro a megawatt per hour. So if the price is high enough, then the finance will make sense enough to build this reserve. So yeah, but I think the problem arises if the finance does not make sense to build this reserve, and that the utility do not have enough money to compensate for having this reserve. And to come
but just to jump in here, does that not also mean that the market really has to function? And does it always function? Maybe that was also what you wanted.
Okay, let's go down this path. So yeah, 7,000 euros per megawatt hour. It could be higher. I think we have 15,000 earlier this day. It is possible. It does happen. Honestly, it's not. I would still call it an extreme event, but it's not exceptional in the way that it's a once in 10 year. It does happen. But we just see that incentive, that you could potentially get that payment for a few minutes, maybe a few hours throughout the year, is not enough to incentivize the the investment in this technology. Unfortunately, that's what we see, that there are some traders, actors on the market that are hoping for these spikes at times, but not enough that they want to invest new products to do this. Yeah.
And to come back to your second question, why are we all doing the same thing? I would say maybe because we use the same data. So if you have all the same information and that we do the trading based on the same information, you are more likely to have the same strategy. Except if you have data that others do not have, except then you would have a competitive advantage, for instance, by developing your own model that is more accurate. But I don't think that's the case for all utilities.
No, that's correct. So, but that's something that let's say service providers to trading organizations always wonder about. Why is there a structure that supports that everybody's doing the same kind of using the same data? Because one of the things that we know for many years is that let's say an average best forecast is not always the most effective forecast, and a market should normally, if it works, it especially work on diversity in a way.
Maybe I could give a sneak peek on my presentation tomorrow.
Okay. So we'll go back to that one tomorrow. Yeah, so then I want to go a little bit into the definitions of the extremes, and there I would like to ask Irene and Hamid about thresholds in meteorology, maybe also Vanessa. How do we find and how do we define thresholds in meteorology to areas that are maybe not only meteorological, but maybe starting in meteorology? How do you find in meteorology thresholds on warnings, like indices that are kind of red, orange, green, or so? Maybe you can elaborate on that.
What we did in this destinational framework, and that's mostly done by the colleagues, they use the extremes compared to the model climatology. So of the current ensemble forecast, they look into the model reforecast and climatology of the past 20-something years, and just look into how much it deviates and what the difference is. What we did for wind ramping, because we said that for us it maybe makes no sense for wind speed-based ramping, a really simple approximation of wind speed times 3 is more or less power. And based on that, we said, okay, we take these thresholds and everything above 10 meters per second within 3 hours, because we just don't have it higher resolved currently, is an extreme event for us, up and down. For solar, you really have to consider as well the day, sunrise, sunset times. But yeah, that's basically how we did it to start with. And then also looking into norms, standard survival, wind speed of wind turbines, what the temperature or the feel-good temperature for PV panels is, more or less. Yeah, so that's the approach we took, looking into a lot of paperwork, historical. And then just trying to find also historical cases we know of.
And are you then also including end users into that? Or?
Yes. So we did reach out to end users, but more on a one-on-one base, not in a huge room, and just whenever we met someone, writing in emails, talking to former meteorologist colleagues who work now for the industry, which is in quite easy. You just go to Verbund, for instance, where a lot of meteorologists stand up, and you just ask your study colleagues and ask for feedback, and also other from context from projects, just asking and talking to the industry. But nothing really like official questionnaire, but we have one if you want to. But yeah, that was the easiest way for us to go.
And then maybe Hamid, from your knowledge and about how the WMO is working, you can maybe elaborate a little bit how difficult that process is, because now we're coming from the national center to the global, and then we have very different data sets available, very different regulations in the various areas of the world. And how can you tell us a little bit on how does the WMO bring people together and talk about data, and if we can see there is a need or something?
Sure, thanks for the question. Before going to the data, if you allow me on definition of the extremes, I would like to refer to the slides that we saw from EPRI's presentation today, which provided a very comprehensive list on extremes definition. I would like to highlight two of those items. One of them is that we compare the parameter that we observe today with the climatological standard, as it was said. Based on WMO standards, is 30 years of climate data. So WMO has standards for all of these observations, definition of the extremes. And the second point, which is very important, is that extremes are local based and they differ from location to location. The WMO standard number 1310 on definition and characterization of extreme events, like climate events, gives a very interesting example that hundreds of people in northern part of India in 2011-12 were died, fortunately, during a cold wave in temperatures that is considered to be a normal temperature in autumn and in spring in northern part of Europe, in Scandinavian countries. So you clearly see that the difference, the context of the location context of the extreme event. In addition to these guidelines that I mentioned, WMO has also another guideline on how to calculate the extremes in a changing climate for decision makers. That's number 1500 that was published in 2009. And that was used by the Atomic Energy Agency to develop a very comprehensive standard for the nuclear power plants. I was part of that report from the WMO side. And basically, they issued a very high-level standard for all types of extreme events with the definition, with the threshold, and then it will be officially distributed to all the countries and from the governments down to the nuclear operators. I see it as a very good example to be replicated in other industries, like aviation is quite advanced, as you mentioned, also in WMO. But during these years, I really felt the gap in having such a standard specifically for wind power plants and other types of power plants.
Yeah, because what the IEA presented in a report end of last year was that they started to look into different phases of wind and solar or renewables integration. And they realized that if they have set 6 phases, and they realized that when countries are in phase 1, 2, and 3, it's kind of this startup where there is a lot of things that have to happen. Regulations have to change and all that. But when countries then move to the phase 4 and 5, where we at the moment have Denmark, Ireland, Spain and Germany are about to move into these phases, then everything changes. Then extremes become more dangerous. Forecasting and other tools become necessary. High-speed shutdowns can be suddenly a threat to the system. And that's why I think we actually have that gap. And I hope that we can learn from WMO how to make such guidelines across the energy and across the globe.
On data, just quickly on data, there are also guidelines on data. There is also a world weather and climate extreme dashboard that collects all the extremes, all the validated extremes from 2007 onward. And there is an associated also guidelines on how to evaluate the extremes, which is quite useful for the countries. But something very important here I would like to mention is that the WMO members are national meteorological and hydrological services like DWD, MeteoSwiss. In each country we have those national met services. And those met services are the authoritative voice and should always be kept at the center of any type of service development, both from the user side and also from the NMHS side. And this is something we've been advocating for during our regional projects, always putting in contact the user and stakeholder with the national met service in order to ensure the co-design, co-development and co-implementation process, the co approach.
Yeah, and we can see that data is a huge problem. We have data sharing, but also data quality. That's coming back to our Eveline and WFIP projects, where good data could well be assimilated also in the models, but bad data is doing worse to the assimilation and the model than not having data. And we notice on all levels. We notice also in the power space, if we use power data to update our models and the data is bad, we do worse than if we wouldn't have the data. And that's why quality control is something that I always thought that this is what we have to learn from meteorology. So I hope that we can continue, and as Vanessa said, we can have these discussions a little bit more. So then, if there are any questions from the audience, just lift your hands. Otherwise, I will go a little bit into the forecasting capabilities and the gaps. So we have heard.
That's one question.
Okay.
Just to the last comments that basically the dialogue should be channeled through the national net services. I mean, do you have experience from other countries? I think Germany is a prime example where we have the user forum and there is really the energy meteorology community discussing through the national net service, but how is it in other countries? You have a Danish example or others. I mean, I know in Switzerland we are trying to do that, but it's currently not set up in that stage. Difficult to get in touch actually with the players.
So as you mentioned, some of the net services like DWD, EMC, the net service in Chile, also CMA, Chinese Meteorology Administration, they are quite advanced in this area. The mechanism for WMO is basically advocating this approach through regional projects. And this is what I'm doing now on the project that I'm involved in Southern America and on this project. Chile, Colombia, Peru, Argentina, Ecuador, Bolivia are part of the project. And during the meetings that we have to develop demonstration projects for energy sector, we make sure that both sides are included. This is something that through the regional projects that WMO can do. But the capacity and the capacity of the team is really limited. It's a very small team in WMO. So we encourage net services all the time to establish this type of agreements with their users. There are sectors like agriculture, disaster, like health sector, they are quite advanced in developing such mechanism with their sectors. But others like energy, it's still at the beginning. I would like to take this chance to invite all the audience who are interested to participate or involved in the upcoming WMO Regional and Climate Workshop, which I'm organizing end of November in South America. It will be in Asunción, Paraguay, especially from Met Services. We will be happy to host you if you would like to be there as an observer, and from Met Services as a speaker, distinguished speakers. Yeah, basically to share the knowledge that the advancement services are.
Yeah, so I can send that on to the participants here.
Yes, of course, I will share it with you, but the participation is only for Met Services in the region. But if there is someone interested to attend as an observer, yes, it's possible.
Just because the GWG is now in the spotlight as a positive example, I just want to remember that it took a lot of time to establish this and to be patient and I don't know, to take chances, to talk to people, to build coalitions or like project consortia to get in touch. This is a lot of work, and we had the chance, and we've been lucky that there was funding that actually brought us to the point where we are today. And I just wanted to stress that it takes a lot of time, and I think many of us are on our way, and it is the right path, and just to encourage to stick to the goal.
Thanks. I want to stay with one more question at the data level, and this is if we look upon climate data and we look upon infrastructure planning, asset planning in a changed climate, where we see cold waves in Texas that cause blackouts. We hear about India, strong cold spells where people die because there was just nothing, no clothing and no heating and so on. And then on the other hand, we observe heat waves. How often does the climate data nowadays, do you think, have to be updated? Because we have also been working with system operators where they were used to have 30 years of data to make a projection. But if we go 30 years back, this is not going to give us a good projection for the next 10 years, because we have a changing climate. So maybe anybody that wants to take that on, how do we deal with that? And is there already a kind of a consideration of that type, how we deal with that? Because we have been starting to say, let's better make an uncertainty quantification from the last 10 years looking forward than going 30 years back with 1 or 2 models.
I think, and we're still not there, but I think the destination of climate DT with the storylines is quite a good way to go. So what you do in the storylines is, and they have, I think, 3 months now, the climate as is, then a changed climate, and climate like 50 years ago. They freeze the state of the climate and run storylines for roughly 10 years, I think, of climate simulations with a resolution of 9 kilometers globally. And for the other part of the climate DT, they run 4.4 kilometers, I think, for the RCP scenarios with IFS coupled with two ocean models and the ICAN coupled with ocean models. And I think the idea, but I'm not in the climate DT, but I think the idea is to continuously run those models and keep them updated.
Kind of with data, with more recent data.
Yeah, I think that's one of the ideas, but maybe you know more.
That's right, yeah.
Because if we then go to my next topic, the mitigation and adaptation strategies, this is something that the system operators are very much concerned about. And do you want to?
Yeah, I wanted to react to your previous question.
Okay.
I might have a non-popular opinion, but I think we have the data to the climate projection. I think the issue is to know how to use the data that we have, know the uncertainty, and know what we can conclude from the data that we have. For me, I don't think that's an issue of data. It's using properly the data that we already have.
So you think this is more political question?
Or scientific?
It could be scientific, because recently there is more and more paper to, for instance, we have the climate model data. We go through a process of downscaling, statistical or physical, and there are a set of publications that want to attribute, okay, what are the uncertainty related to the phenomena, and distinguish it to the process that we need to do to have data at local scale. So that's, for me, we have the data. It's just knowing how to use it accurately and to not use the data to say something that the data cannot say.
Okay, yeah, I can see, but what is hindering this? Is this that we don't have the right people, or we don't have this multidisciplinary team where you have the knowledge from the meteorology in the system operation or system planning?
That's what I think, yeah.
Okay.
So
maybe, yeah.
How to deal with these uncertainties that are pretty large in the climatological projections or forecasts and seasonal and decadal forecasts. I think it is, I don't know, it establishes at the moment, I think, to use uncertainty information for a weather forecast. So I think this is actually, we see many different action or activities to use this information to make something, say, the decision based on an uncertain data set. And I think the uncertainty in those longer forecasts are more difficult to deal with than with weather forecasts. And I think this is one thing we miss still, that we can draw some conclusions or even say, okay, we don't know. And this is something that, perhaps.
Yeah, so here comes the climate.
Yes, was part of Vanessa's talk, so maybe I can also add to this panel on behalf of DWD. So I mean, when I heard the last few statements, so the specific examples from Germany came to my mind, because you were, for example, saying, well, we have all the data, but the problem in practice is that, for example, our partners in the government that are responsible for the security of the electricity system, so they want to run scenarios of the future. They are aware that there are these climate models, but they tell us that their models are rather complex. They consume more time than our weather models. So they want to, in the past, they typically use just a representative weather year. So they just use 2012 and we're running all the simulations with this 1 year.
So then we were going to that community and telling them, well, you should consider climate change. You should also consider the uncertainty in our simulations. You should use a multi-model ensemble. You should run it for 30 years. And then they were telling us, well, that's completely impossible. And the weather is not the most important point in our activities. So that's on the one side. But then we were also looking into the quality of these climate simulations. So when you just talk about, I would like to have feeling for the average wind or the average solar radiation in the future, then that's fine. But we also, this morning I talked about the weather patterns. For example, this over Mitteleuropa, which is causing these Dunkelflaute events. So we also checked the historic climate simulation. If they produce the right frequency of the critical weather patterns, and that's just not the case. That's wrong. So if the models don't have it at the right frequency in the past, then you should have some concerns what you can do for the future. So there is still this gap in the quality of the climate simulations in getting the weather patterns right. And for that, we have to discuss what do we really want to see in the future. Is it just enough to look at the average wind conditions, or do we really need the extreme events? And I'm not convinced that we have the quality of the data that we need.
Well, let's say we have to deal with the uncertainties.
Yeah, I don't think really it's a question of complexity of the models and simulation computational time and representative dates. And here it's a matter of cost, actually. To give an example, you can have a river with infrastructure for hydro, and then you have to invest in this infrastructure, and you consider what is the security you take for the investment. Do you take events that happen once in a decade, once every 50 years, or one every 100 years? And then you decide on the risk actually, and you invest. If you develop an infrastructure that is taking over an event that happens once every century, of course the cost is very high. Today, the planning models of the TSOs, etc., are not really designed for events that happens one every 10 years or so. So, and this is actually a research question, and there is research going on to adapt the planning models, the classical that exist today, to take into account the climate change. In this means to design the investments for the grid, for the network, as a function of events that can happen in very, very low probability, and this, of course, involves higher cost. I mean, you can take in a model a representative day or a year where you have an extreme that happens once a century, but and then before that, you have taken the decision to invest for this type of event and this very high cost. So it's a question of cost and also yeah, how the planning was done so far. But it's an open research question, and I know that there are projects that are dealing with that. Actually, there is on the system and to adapt the planning model so that they can plan investments with rational costs that can hedge against these kind of events.
Yeah, just to follow up, because I think both of you have some really solid points that there has been at least a history of very conservative ways to look at these forecasts. And looking at mean wind speed, looking at these not very representative weather data for extreme events. But at the same time, it's a consideration of investment costs. But I can assure you that these days, these years, the mindset of the TSOs and SOE as a whole, because it's a bunch of different European countries that have to collaborate on the way of performing these forecasts. It's a huge collaboration with very tough, or at least very different minded people regarding risk. So work is slow, change is very slow. But as we've seen in Denmark, moving on towards more probabilistic reserve dimensioning, we see also across all of Europe more and more agreement with we need some kind of probabilistic view on these risks instead of just going for the static old school way, which worked fine, honestly, 40, 30 years ago when everything was very static. You could place a huge nuclear plant here, build some power lines, and then that would work for the next 30 years. That's not what we're seeing anymore. Decentralized production, among smaller consumption everywhere, really pushes TSOs and the collaboration to the edge. But change is happening.
Yeah, thanks a lot for that, because I think this again tells us we need first movers. We need those that burn their fingers. We also need those that push hard, and that those that make themselves maybe sometimes unpopular among the larger groups that do not want to move that easily. And then, of course, we have different cultures, and not from a human perspective, but also different countries have different challenges. Different climates have different challenges. So there are so many challenges that sometimes you don't really know where to start. And that's why we need those dedicated people that just try to push this. But we have only 5 minutes left, and I have a question to each of you. But before we go to that last question, there is something that I really want to ask, and whoever wants to answer. We have a lot of extremes these days. We talk a lot about extremes. But in our last workshop 2 years ago, we also found something that was not so much considered. And this is if we have a weather extreme that correlates with another extreme. That could be a cyber attack. This is very much circling around these days here, and I think it's maybe appropriate to ask this question: how do we deal? Are we prepared for extremes or things that happen where somebody could use an extreme in weather, for example, to add something on top to make the system vulnerable?
I think if you have the malicious intent, that would be the way to go. Because the TSOs, they do dimension for, it's called N-1. Most of you probably know that we dimension for the largest possible incident. We do not dimension for the two largest incidents. So by stacking those, that would definitely cause difficulties. And just to circle back to some of the things that I've said before, that the technology and forecasting harmonization across the board really pushes the N-1 way of thinking as well. Because if you have 50% of your production mix coming from wind in the North Sea, suddenly everything is centered around the same thing. If you have an extreme event there, you really are pushing your N-1 to a degree that's not considered right now. So that's another aspect of these weather dependent and geographically small extreme events.
Anybody else? If not, I will go to my last question, and this is some years ago. Charlie Smith at ESIG once asked in a panel if I was king or queen for a day, then I would do what? And I would like to give that question to you too. Now in Denmark we have a king and a queen, and they may not have so much power, but we just imagine now you have all the power in your country or in the world. What would you
recommend, or what would you put on the agenda on the very top?
Yeah, so it's probably going to sound very populistic, but from what I've heard here today and what I've heard earlier as well at these IEA wind talks, if I could decide, I would make sure that the data that we have available at Energinet, because we do have a bunch of all this data that you guys are wanting for, but we're not able to share it. We would be able to share it, and then I would change the mindset of the probabilistic way of thinking. So I'd take the best probable research and then actually use it as well.
I vote you.
Yeah.
Vote you as king.
Excellent.
Yeah, actually, my answer is quite similar to what you mentioned, exchanging data between the energy and meteorology community. Within the World Meteorological Organization, we have an observational network of all types of parameters, and those who accomplish this sort of type of standard are available online through OSCAR platform. There are about 12,000, 13,000 stations. But I once did research in ChatGPT. I give all the credit to ChatGPT on that. And I found that about the same number, 12,000, 13,000 net services are installed within the power plants, all types of power plants, nuclear, etc. And unfortunately, this data, because of commercial interest, is not shared with the meteorology community. And it's kind of mutual benefit, because by having the by sending the data to Met Service, you will get a more accurate forecasting based on bias adjustment. And from the other side, the data can be used for better modeling for benefit across the countries and in the regions. So I would go definitely for sharing data between the two communities.
I was struggling to find another. But probably because I'm, representing the meteorology part of this endeavor, I'm not quite in a position to say I know how it works, but I have the impression that a more European view of the entire system, although I know that there are interconnections and the exchange of energy across borders, but I think in particular, with respect to the wind and solar resources that are distributed over larger region than one nation, that I think perhaps we could actually profit from a broader perspective and a system that is, for example, Europe or Europe plus the North African region, so that we can stabilize even more or profit from regional differences between resources and actually available production, so that we can do or stabilize the system even more. And then we would invest into storage as queen.
King Mohammed I. So when you asked this question, the first thing that came to my mind was data assimilation. So imagine, okay, on the top of your mind, you have a rough idea of what are the sounding measurements that we have available. Now, picture all the wind turbines that are located worldwide. Imagine them as met station, where you can have temperature, wind speed, and even the weight. And imagine that all the energy utilities communicate with the weather forecast center, and that they can provide this data, clean, of course.
Quality.
And that can be used into a data assimilation framework. What would be the impact in the accuracy of the forecasts? Yeah. If I was the queen, then it would be the thing that I would have commanded.
So I think we have a lot of data already in estimation, but I would invest in education. Knowledge is power, and we need to educate ourselves in between the different groups more. Maybe invest in some sort of joint educational program. You never stop learning, and I think there's still a lot to learn from both sides or all sides that helps us making everything else better and improve the rest. So I would invest in education and computational power.
Thank you. And if I had been clever, I would have made a slide of which who would be your queen or king. But I leave this to the coffee break discussion. So thank you very much to the panel. It was really second coffee break, and we'll start here again at
16:20.
16:20. Thanks again.
Yeah. So let's get back to the last session of today, and we have to be pretty much on time because afterwards we have an appointment at 7 sharp in the restaurant, and that's by all practical purposes nearly an hour from here. At least with the timelines of everyone getting into the tram and getting tickets and getting out of the room and all of that. So we try to.
The tram runs 18 minutes, but I mean, and it's 200 meters away. So, but it takes 200 or 300 meters away from here.
The station.
No, the tram is 300 meters.
And also from the station in Frankfurt, it's another 100 meters.
But we have to organize the tickets. So we need to make groups of 5, and except those that have already tickets, the many Germans would have.
Group of 5. That's another hour. So let's please get going. Yvonne from DLR, everyone.
Yeah, I also work at DLR as one of my speakers before me, and I am an energy system modeler. And after that almost devastating critique of Frank Kaspar about energy system modelers and their models, and saying that they say they are impossible to be solved in ensembles, and many of them, I'm a little bit ashamed to say it, and I was wondering how I can defend my community. And I wanted to say our models are complex, but weather models obviously are complex too. So I think maybe the differences are, it's optimization that we do. So we don't only model the operation of a power system, but can also be, we model the capacity expansion, for example, and each kind of capacity expansion, be it PV or wind or storage or whatever, has multiple interlinkages with everything else. So it makes it really complex and long lasting. And the second thing is it's also about money, which also makes it complicated. So I want to show you 3 case studies that my colleague Madhura Yeligeti and I did in the last 2 to 3 years about Dunkelflaute and long-term electric energy shortage events in Europe. And I would like to start with, now it's working, yeah, okay. Some definitions. So in one of the studies, we used residual load, and we defined this as the load minus PV and wind power generation. No hydro involved, it's only the load minus the variable renewable generation. So what's left is what has to be satisfied with dispatchable, with conventional power plants or with storage or transport. Then a shortage is a residual load anomaly. And that means that the residual load is actually above, it's written wrong here, it's above its long-term mean.
And a Dunkelflaute is an event of that kind that may last 1 day or maybe up to 30 days. Then we would say a seasonal electric energy shortage is an event of 1 to several months duration. And a long-term electric energy shortage is an event of 1 to several years duration. And I brought 3 case studies. One is mainly about this residual load analysis and looking at the anomalies and the distribution of these anomalies. And the case studies 2 and 3 are about a resilience assessment in the energy system. So this applies such an optimization model where the costs are minimized and a system is designed that can satisfy the demand at the least cost. And
screen is not shared.
Oh,
Somehow we have to.
the screen is not shared, I heard.
Yeah.
Okay. Yeah.
When is it? Yeah, it's there.
Okay. So. Okay, so about this residual load analysis, we did it especially to find periods of time that are especially challenging for the energy system. And then we can put those periods in time into an energy system model because the model is too complex to solve it for many of such occasions. So we try to find those beforehand. And we did do this by fixing a scenario of capacities of renewables and of other assets in the energy system from the 10-year network development plan from the distributed energy scenario. Then we put into this fixed capacity set 30 years of ERA 5 reanalysis data, and we calculate rolling averages of different duration length of residual load anomaly. We find that in this scenario, the mean load is 410 gigawatts and the mean residual load after PV and wind generation is still 48 gigawatts, which means we have about 80% of renewables, of variable renewables, and about 20% of non-variable renewables. And when we look at this, it looks like this. This shows the 1 day, 180 day, and 365 day rolling average. And the 1 day is in blue, and it obviously it oscillates a lot. And the maximum can be around 350% above the mean residual load. And on the 180 days rolling average, you can see that there is a strong seasonal pattern. It has winter peaks. So this is a rather wind-dominated scenario. And if you look at the green line, which is the 1 day, 1 year rolling average, then you can see that there are times where there are several years in a row where this average is above, where the rolling average is above the long-term mean. So it means that it could be that if you plan a system with a specific year, that and you plan for storages, that maybe you are not able to fill the storages even in the next year or in the year after that. So that led us to thinking maybe we should look into this more and have a look at the distributions of more different durations. And here you can see the durations of the rolling average window, or that would be the Dunkelflaute or shortage event duration on the x-axis, and on the y-axis the anomaly. The distribution of the anomalies across those 30 years. And of course, it gets smaller the longer the rolling average window, so the duration of an event is. And when you look at around 15 days, or that would be around 14 days or so, 2 weeks, that would be an anomaly that could still be 250% above the mean residual load. And if you do less than 4 years averaging, it can be still elevated 10% above the mean. So it might be worth looking into longer timeframes. Even a 10-year anomaly can still be 5% above the long-term mean of the residual load. Now we thought, what does this mean in terms of energy? So we looked only at the maxima, so all the maximum values you can see there. We put that into another diagram. It's the green dots and line. That's the maximum residual load anomaly in gigawatts. And then we multiplied it with the time that this would last. And so we get the amount of energy that can be missing in a certain time. And we can see that in a 10-year period, this can amount to around 400 terawatt hours. So this is across Europe. And in a 20-year period, it could still be 3% above average, around 480 terawatt hours. So normally that is something that could be imported, but maybe there can be geopolitical constellations where import is not so easy. Then this should be considered, this has to be a strategic reserve or something that has to be taken into account. Yeah, it must be either balanced with imports, as I said, or storage or additional generators. And but what we also, as I said in the beginning, can do with this is identify critical time periods. So maybe 1 day or 14 days that are really critical for the system. And that's what my colleague Madura Yeligeti did. She did a resilience assessment with such an optimization model. It was slightly differing from what I showed so far. So it's a really total carbon neutral system. It's looking at 2050 with hourly time steps. It has more than 70 technologies. It looks at the electricity, natural gas, and hydrogen sectors. And it has a lot of flexibility from battery electric vehicles, demand-side management, heat sector demand, but only within Germany. And as you can see, also the spatial resolution is increased in Germany. So this is the focus, and we have the surrounding countries to account for imports and exports at least a bit. And there were 11 scenarios that vary in terms of cooperation in Europe, grid expansion, extent of electrification in heating, and hydrogen-driven applications and more. We will look now at 2 of those 11 scenarios that were investigated then with the remix optimization model. And how was this done? So first, as I said, we identified a 15-day period, which was the highest 15-day Dunkelflaute in Europe between 1919 and 2020, given this scenario that was taken into account here. And then we made it optional whether we can introduce this into a predefined period or not. And this predefined period was there in that project because there was a snowstorm that was to be investigated. So it was clear it should be in January and beginning of February. And so the Dunkelflaute that we had identified was introduced into this time period. So it's sort of a synthetic introduction weather here. And then we could switch on and off whether to use the original time series or whether to use this introduced Dunkelflaute. And just to make it, to illustrate this a little bit, so the green bars would be the original case and the blue bars would be the Dunkelflaute event, where all this production is reduced by the amount you can see here. And now let's look at the first scenario. On the left-hand side is the original case with no event. And this was used the whole year with this kind of time series was used to design the system. So to set the amount of PV capacity, the amount of wind capacity, and of all other assets. And then the Dunkelflaute event was introduced, and you can see that on the right-hand side. Below zero, so this is the zero line. Below there are the different types of demands, and above are the different types of generation. And the yellow and blue ones are the PV and wind generation. And you can see that on the right-hand side, it is reduced because it's the Dunkelflaute event. And you can also see that the reddish bars are largely bigger. And these are the gas turbines in this case, which now operate at their full capacity. And nevertheless, the bright red parts that you can see on top are unserved energy. So the system that was designed originally wasn't able to deal with this Dunkelflaute event at that time. And there is a second scenario that has a similar case, but it is different in that it relies more on imports. So a little less on, it also has a lot of renewables, but it relies more on imports. And it has hydrogen turbines, so gas turbines that can use hydrogen. They are the turquoise ones, these here. And basically it's the same again. Left-hand side is where the system was designed. Right-hand side is with the introduced Dunkelflaute. And again, the demand is a bit lower and the production is a bit lower. So everything that can be shed or shifted is shed and shifted. And you can see that the gas turbines, so again, the pale red, and the turquoise hydrogen turbines are running at full capacity throughout this whole time, but still they cannot prevent this unserved energy. And you can compare with the case beforehand that it is even a little bit more. So imports cannot per se compensate this lack if the capacity was designed for another case. So the capacity was designed without the Dunkelflaute, and in this case, the Dunkelflaute cannot be, the demand cannot be served. And very briefly about the third case study, it's basically the same setup, but the question was, is it important when a Dunkelflaute event occurs in the year? So it was fixed to a 2-week event again, and the intensity was varied. So at first, the event wasn't introduced, then the amount of renewables were lowered by 20%, by 30, 40, 50, 60%. So that's a variation of intensity of the Dunkelflaute. And the starting times were distributed across the year. And for each starting time, an individual model run was performed. So overall, there were 360 test model runs. And this is the result. It's a bit hard to interpret. So these are the different time steps. And on the y-axis, you can see the residual load on what happens to it. It's not to be read as a time series. It's not a time series. And the lines are only there to make it easier for you to connect the dots. So it's not a time series. But you can see that the lowermost is the original case, and the residual load varies between -10 and -4 terawatt hours, let's say, in the time span of the Dunkelflaute. And when you reduce the variable renewable infeed, then the residual load goes up because less is served by PV and wind. But from this, you cannot yet see whether there will be unserved energy in any case or not. So you can see that from the next plot. And these are, again, those different time steps. And you can see that in hardly any events, there is unserved energy. It's only in those 3 events that you can see on the left-hand side. And the different intensities of Dunkelflaute increase the amount of unserved energy. But it's actually really only in those cases. And why is that? It's simply in those cases, the system is already under some sort of stress. So introducing a Dunkelflaute here is too much stress, and there is unserved energy. And in those other cases, there is enough flexibility in the system to cope with a Dunkelflaute event. Now, some takeaways. Critical time periods to be further investigated can be identified using residual load analysis. And residual load, and with it energy demand, can be elevated by up to 250% compared to the mean residual demand in a 14-day period, by up to 30% in 1 year, and even 5% still in 5 years, in 10 years. And if a system is optimally designed, it can still be inadequate for energy security in cases of short extremes like Dunkelflaute, or, as I showed in the beginning, if there cannot be imports, also in cases of long-term shortages. The resilience or system response can vary drastically based on the system configuration, depending on what flexibility options are available. And storages, demand-side management, like load shedding, load shifting, electric vehicle flexibility, they have limited benefit for Dunkelflaute that lasts for many days. And the timing of the events is also a significant aspect in testing for energy security. So that's all. I brought many questions. Not sure I have a Slido. I do. Mache ich irgendwas?
Yeah, no. So yeah, we have Final questions, you can moderate.
Okay, so I'm interested in what indicators of extreme events do you use or know of? So do you use yourself, like the residual load I showed, or like only wind thresholds or whatever? What do you know? What do you use? Forecast error anomaly. High price. So I might go to Mohammed and ask which percentiles and how do you choose them? Okay. Again, percentiles, yeah. Okay. 2 participants still typing. I think uncertainties. Yeah, okay, again, thresholds. Yeah, thank you. I think we can. So, yeah, so we looked at Europe, at Central Europe, and what do you think? What is the geographical extent of extreme events that is most relevant for power supply? So maybe you can, I guess, rate this from 1 to 10, each of them.
1 to
1 to 5.
1 is very local and 5 is the entire globe.
Okay. Yeah.
So the normal C would be 2.
Yeah, I would say so. So a region smaller than national.
Depends on the size of the nation.
Yes. You're right.
As you can.
Yeah. Okay, yeah. So it seems like regional, so size of a small nation also. Yeah. Yeah, and as I said, shortages can extend to several years. But is this really relevant? So would you say, no, there will always be the opportunity to import enough energy carriers? Or would you say, yes, there can be geopolitical situations of regional rivalry or so? Or would you say, maybe? Oh.
That's interesting.
Yes. I would have thought maybe there would be more optimism about international trade, but okay. Yeah, but I see very similar. Okay. One more. Yeah. So I guess we heard a lot today, so this is maybe also a question that checks how well you listened. What are potential hazards to the supply system associated with extreme events? So this doesn't have to be Dunkelflaute. It could be the icing. It could be whatever. So whatever comes to your mind, and we will have a nice word cloud, I think. Wow. Will we have pictures of this? Mm-hmm. So this could give a direction to future research, maybe, because I didn't think that thunderstorms would be rated so much higher than Dunkelflaute, for example. But that's interesting. Yeah. Hitzeflaute. Mm-hmm. Yeah. So, thank you very much.
Yes, thank you.
I think timing wise, we need to continue. We still have 3 talks, right? So the next one.
The next one is slide up. We start with this slide.
Yes. Okay.
Yeah, please. Sorry.
Are you also happy?
The jumping. Yeah, actually, I wanted to break the ice a little bit with the Slido question. And because the events of November 2024 and the Dunkelflaute events of 2024 were already presented several times in the morning with Frank and Kaspar and in many other talks. I wanted to just to break the ice and see if you could answer what was the change in production in megawatts from November 2023 to the November 2024. So the year over year change. So I just put the Slido question at first, and then at the end we won't have any other Slido questions. But you were doing better at the beginning. I don't know who started to answer the question, but it ruined up totally.
This is for Germany, for Europe?
This is exactly, this is for Europe. Thanks for the, I had it in the presentation, I don't see it now, but this is for the whole European region, all the countries of the European region. And it was just a question to start the discussion with this event.
And comparing to November.
Say again?
Comparing the
Yeah.
climatological November over the years.
Well, compared to the November of the previous year. So just a change from one year to the other. And it's a monthly value, so it's not for those 5 to 6 days, but the whole month. Well, yeah, I think I can just start. So you were doing perfect at the beginning. It was a 9%. So close. I changed now to the presentation.
I found it.
No. That. Yes. And then I have to share, no?
Yeah.
No.
You have to share now. Yeah, this one?
Yeah, I guess. No. This one. Yeah. Just full screen and that's it.
No.
Yeah, fantastic.
Is it still sharing?
No, because we don't see the red frame, no? Maybe
It's not shared.
we can share it on the,
No, I see it.
Okay. Okay.
so, yes.
No,
It's not a presentation mode, it's the other screen.
It's so which one? Oh, now for you share the screen and no here.
Yes.
Yeah, thank you. So, yes, basically that was the idea, just to introduce a little bit the talk, because I will be using this November case that has been already discussed in this workshop as a case study to open up the discussion about seasonal forecasting of these events. Yeah, the right answer was a 9%. I wanted to bring the average values for November because in our group, what we do at TDP in our company in the climate services, we do seasonal forecast of all the energy relevant variables, and we usually deliver monthly values for the different departments and different groups that work with it. So
it's also important for us to aggregate those anomalies and work with those tendencies if we get more or less wind than an average or the mean average values for a specific month. So yeah, this is basically just a snapshot of the wind resource here in the left. You can see the wind speed anomaly at 100 meters, and you can see some regions that really were affected, almost reaching those 75% in an anomaly, compared in this case to the climatology. And here in the right is the irradiance, so you don't see such a huge difference, and as has been already said before, and it was published in recent papers. In this type of episode, this is the wind, the one that really determines the strength and the intensity of such episodes. Some things that have already been said. So for those days, there was a very little share of solar and wind. Actually, in wind, you can see that was a 0.5%, so close to nothing. And the peak price was increasing, and it rose up to 800 euros per megawatt hour. This is another graph that gives us a hint of what types of sources were entering the energetic mix for that day. You can see in the highlight for the 6th of November, just for that day, you can see that the share of coal, brown coal and hard coal was reaching that 60%, and then the orange one is the natural gas. So really a huge share of fossil fuels. This is why I wanted to bring that value. Actually, there was a peak in emissions for that month, and it rose up to 270 grams per kilowatt in an hour. No? So that's a strong peak emission. And actually, in EDP, we are interested in seasonally trying to forecast at the seasonal scale this type of events, because our share in Europe of solar and wind installations is large. Actually, 54% of our solar and wind capacity is installed within the European continent. And this is why I wanted to be at this workshop. I wanted just to say a few sentences about the EDP group. So we are the 5th largest company in terms of installed capacity. And we have installations and headquarters in these 4 main regions, these continents and subcontinents that you can see here. With regards to Europe, we are present, we have solar and wind power plants in all the countries that you can see there. This is a total of 11 countries. And we are a big company, so we are, well, these numbers are a bit outdated. I think they are from 2024, but back when we were 13 employees, we delivered a total amount of 56 terawatts per hour, and we had a total installed capacity of 29 gigawatts. I think now we are close to the 30 point something. So just to present a little bit the group for those who know that that are not familiar with it. And yeah. And here just a quick slide to talk a bit about our aim and our goal, our reason to be here. So this is a project we are just starting at the moment. We're interested in having a seasonal forecast of Dunkelflaute episodes, and it's something that this is just starting, and also because confidentiality reasons, I'm not able to show many of our own internal results. So instead of showing our own results, I just wanted to open up the discussion and announce that we would be very open to participate and collaborate with scientific groups or other players in the industry, like climate consultancies, for example, to try and investigate and advance a little bit the seasonal forecasting of these episodes. No? So, yeah, like I say here in the slide, do not hesitate to reach out and ask if you want to know a little bit more. Maybe also a final remark on this slide. We are interested in, for us, what we call seasonal forecasting. We develop monthly values for the month, the current month, the month ahead, and also lead months 2 and 3. So, for example, now if we are in September, we would deliver a forecast for September, for October and November. We know this is a very challenging topic, correctly forecasting a Dunkelflaute episode. So for now, we would like to just have an investigation on how it would be like to forecast the lead month 2. So we are interested in surpassing the threshold of the subseasonal forecast, trying to make it farther from that day 42, and maybe get a hint or a trend of what could be like. No? Like, for example, now we would like to know what's going to happen in October or even November. Okay. So now going a little bit to the core of the talk, I just prepared a few slides. So the first one is on why do we think it's important to get an earlier forecast of Dunkelflaute episodes, so they have a huge impact on the renewables business. I just gathered here these four main topics for discussion. The first one is the most direct one and the most obvious. So for us, for EDP and also for other players in the sector, we get a large part of our profit coming from the output, from the production we make from solar and wind plants. And as I said before, for us, it's a 54% of installation in Europe. And also that second point, maybe an aspect we didn't discuss yet, but if we would be able to know if it's going to be a Dunkelflaute episode, we could use that time as well to do some maintenance work. If we know it's going to be, we will have our turbines completely stopped, then we could also plan some maintenance. This will help us to save some costs, some operational costs. The second aspect I wanted to mention is the grid safety. We just had a very nice talk before me and also in the panel discussion. This was briefly mentioned. In the November episode, all the backup plans entered correctly into the system. There was no problems, but it was well forecasted well in advance. But I just wanted to bring a couple of pictures of the Iberian blackout. We had this last April, probably you got it on the media, and it's a very disruptive event. No? So obviously, I think the earlier we get these forecasts, the better we are prepared for trying to avoid those types of events. And as you can see, it was a total chaos at night, no? In the city of Madrid. It was a very fast recovery from the system, but still, many people couldn't catch the train. Obviously, problems at the job places. So a very disruptive event. No? Okay, another aspect in which this may be relevant is for energy trading, which is usually done at a shorter time scale, but also in our company, our colleagues, they want to know about the main trends for the coming months. And like this, they can anticipate themselves and plan a better strategy. They can position as well a bit better in the forward and futures market. And this is why trying to reach that seasonal scale would be a nice advantage. And then finally, more like a mitigation strategy, it has already been pointed out here. So using the batteries and energy storage systems, this would be a way to try to cope with these Dunkelflaute episodes, but also trying to reduce the CO2 emissions. We don't need any fossil fuels in this case. And I wanted to share with you this paper. It's a recent one by Mittel et al., where they quantified the amount of capacity that we should have in order to cope with the most extreme Dunkelflaute episode as they identified them. So you can maybe just go and check that paper. It's a good one. Another aspect in which the seasonal forecasting of Dunkelflaute is going to be relevant is for hybrid plants. I don't know if you are aware of this type of installation, but basically it's combining both wind and solar together. This is done basically because it's very efficient and we save a lot of costs. Usually we have already an installation for wind or solar, and then we take profit of that point of interconnection, that granted point of interconnection, and we combine it with either wind or solar. In addition, sometimes we even share as well the same substation. So as you can imagine, the advantages are huge, no? From the point of view of CapEx and OpEx. Also, another aspect that is very relevant to this type of installations is the fact that wind and solar, they are complementing each other. This is a daily time scale. You can see in red is the solar curve and in blue the wind one. And as you can see, there are deficits at the same time where the solar provides the most output. And this is why this is a good investment as well for a company like EDP. Okay. And then finally, just a few pictures on projects that where we have developed such a hybrid approach. These are just two in Iberia, the one in Spain, Cruz del Hierro, with 15 megawatts installed capacity of wind and a peak, and 13.8 megawatts peak for the solar, no? And another one in Portugal. just as an example. Okay, and I wanted to also bring a very short slide on the challenges of seasonal forecast. I think this is something we are all very aware of, but I just wanted to bring it because we suffer it every month. Every month we go to the forecasts, ensemble simulations, and we try to see what the tendencies will be like. And sure, there's a moment where we start to see a loss of sharpness and a lower reliability on our forecasts. Typically after the second week of the forecast, we start to see all these white colors. So there's little agreement between the ensemble members or the model members, and sometimes we don't know what decision to take. So this is really hampering our decision making. And this is an issue that we will also see, obviously, if we want to develop a Dunkelflaute forecast. But it's important to keep it in mind. And then, well, Christian already introduced the topic of the weather regimes, but we believe it's a very promising approach. And as he presented in the morning, it has already been showing very good results for the subseasonal forecasts. And there are a few very nice papers where they apply this methodology to energy relevant variables. So we have those 7 main regimes. And actually, the Dunkelflaute, as it was already said before, could profit from these persistent synoptic situations. So they, as we have already said, they are related to the blocking conditions, and also any type of situation that's persistent, like the polar vortex anomalies we also see as well in the stratosphere, could also bring a little bit of predictability. I wanted to bring this example that was done for the episode in 2022 for the Christmas in 2022. And well, this is just a news extract, but it shows very well that this weather regimes approach is able to capture the main patterns that will happen. I believe this was up to day 20, if I'm not wrong. So already getting close to that third week of predictability. Probably this is just a very specific case, but I think the prospects are good. And then the question remains if we could apply that approach to a further forecast. So this is something that maybe we would like to try as well. We're just starting with this idea, but that would be the main question. Can we get some predictability beyond day 42? So without trying to be too ambitious, we would like to leave it to lead month 2. And well, the prospects indicate that this is worth trying at least for a back test. Okay, and finally, something that we touched very briefly upon, but maybe it's good that we can emphasize it now, is the development of a Dunkelflaute index. Actually, there has been many work done. This is a very nice paper by Vival et al. From last year. And he was, I don't know, the author, so they were trying to analyze different methods to detect the Dunkelflaute episodes, most of them based on a statistical approach, so getting those time series and finding them, and also based on processes. But yeah, there has been a lot of efforts trying to get these Dunkelflaute indices. I just wanted to bring an example here from Lee et al., which is a very interesting one, combining convolutional neural networks as well with a clustering with the k-means. And well, they were able to detect well those periods of very low wind and solar together. And then the question would be if we could use something like that for seasonal forecasting. And if we could, can we couple it with other types of approaches of forecast? Could we combine it with the weather regimes idea, or maybe try to derive it and calculate it from ensemble simulations? Or also, how does it relate to other climate indices? When we have indices that provide a lot of predictability, like El Niño, for instance, could we combine it together, or maybe more related to the northern latitudes, the NAO, and any type of climate indices? So this could be a nice development for collaboration. As I said, we're open to collaborate with scientific partners or any other partners in the industry. And I just wanted to finish the talk, so trying to wrapping up and being a bit optimistic about the November 2024. So if we have had a Dunkelflaute seasonal forecast, so our hope is that we would have had a better renewables management. we would have positioned better our company in terms of energy trading, and we would have anticipated that lower revenue, which is important for our financial development. We could also have planned a bit of maintenance works while the turbines are shut down. And this is what I wanted to present. So just wrapping up, Dunkelflaute episodes deeply impact the renewables business, and its seasonal forecasting definitely poses relevant challenges. However, these subseasonal studies and the state-of-art methods have shown promising prospects, and this is why we would like to foster the collaboration between the industry, the research groups, and the climate consultancies to try and help develop a preliminary Dunkelflaute seasonal forecast product. So thank you very much. Yeah.
Thank you. I think we.
Thank you. Do we have time for questions, or
yeah,
we're sure?
I think we have time for a couple of questions.
Was also one or two more slides.
I didn't prepare any more questions from Slido.
Oh, sorry. Yeah. That's good. Sorry.
We have questions here.
Yeah.
It's all right. I was wondering if you want to look at lead month 2 or 3, do you think you'll look at weekly averages or monthly averages or daily forecasts?
So typically we delivered monthly averages, and that's a very nice question. I didn't have the time to talk about it in the talk, but that would be a nice question. No? A Dunkelflaute episode lasts between 5 and 7 days. So it could be as well that those events are masked somehow in the monthly averages. But yeah, we typically deliver monthly data, but we are open to any type of development. Also, weekly data could be useful. Our philosophy is more like any type of information is good for us. Even if it's just a tendency and no numbers, that's useful. If it's a week, that's useful. If it's a month, that's useful. So any type of development that gives us a hint on the tendency and the direction that it will take is useful for the company.
Thank you, Albert, for the talk. I was wondering if you already have concrete strategies as to how you would use to put out a forecast. Say you were given probabilistic forecasts and were told for the next month the probability is 0.3, let's say. And I was wondering if you already have pipelines established in your decision-making process where you use those probabilities, or you're flexible in that regard.
No, we are just starting the project, so we don't have anything now in the operational system. The starting point for us would be working with the climate regimes at first and trying to see if we could couple that Dunkelflaute index with the weather regimes, and then if we get some predictability on the weather regimes, then we can transport it somehow to the Dunkelflaute episodes. No? And also another approach that we will have is using those ensemble predictions we get from the different national weather services and try to detect the Dunkelflaute episodes in them. We get the information for the lead month 2 and 3. So I think what's needed now basically is a back test. We need to do that for the past forecasts and see if there was some predictability. With a little bit of predictability, then we are happy. Any step we take is good for us.
Yeah, I was wondering if the third and fourth top wrap-up point here, anticipating a low revenue and maintenance work, could it not also be a case where you use like reserves to save that for these times? Like when you have maybe also power plants with a battery storage or something like that. So the prices will be pretty high and every megawatt you can squeeze out would be paid like tenfold in that time. So maybe also don't plan maintenance work there. It could also be a business case or not.
Definitely. I didn't hear very well at the beginning of the question, but you were asking about using those Dunkelflaute episodes to sell energy, no? Maybe using what has been stored maybe in a battery system, for instance. Definitely, and this is coming underway. There's important developments regarding storage, not only for Dunkelflaute, but for many other applications. And yeah, this is the goal of the industry, trying to sell when the resources are low and then the prices are up.
Good. Thanks. Then we get to the next speaker, Abhinav Tyagi from Fraunhofer IEA.
Yes, that's the second one. Yes.
Oh, there it's already. Okay. Oh. But here we don't see it.
I see it.
I think that's it's that red frame.
It's okay. It's okay. I'll manage. Thank you.
Thank you, Albert. That was a very nice segue, I think, to my talk. Today, I wish to present to you my recent analysis of sub-seasonal and seasonal Dunkelflaute forecasting. Well, I'll be focusing on Flaute forecasting for this talk. And since often this is the question, when we get a forecast, we don't really know how we can use that in decision making. So I wish to make here also a simple cost model to show if it is going to bring some profit in the operational context. Okay, well, let's start. Christian earlier mentioned the definition of Dunkelflaute, and I took the same definition from the paper where it is defined as a rolling window over 48 hours where the energy is below a certain threshold. Since we already know a lot about the definitions now, I won't focus too much here. And essentially, we know now from the talks today that we can expect the Dunkelflaute events mostly to happen during winter, and it is the time where where solar capacity is already quite low, and the fluctuations in the wind capacity cause then these events. But this is to serve the background. Now the question is, can we predict these Flaute events at sub-seasonal and seasonal level? We discussed already that the sub-seasonal and seasonal forecast, the average tendencies are usually what can be predicted at very coarse temporal and spatial resolutions. However, the frequency of the extreme events is usually not very well modeled by the sub-seasonal and seasonal models. And that is precisely the question here, because these extreme events are high frequency events or happen at a very high resolution, a temporal resolution, over which sub-seasonal and seasonal forecasts usually do not have skills. So to go about it systematically, I want to show here the average skills that we see in sub-seasonal forecasts. So to see if we can even forecast the average tendencies. So the way I have tried to present here is first the sub-seasonal results from the ECMWF model for the past 20 years, where we calculate the simulated power and simulated energy forecasts, and we evaluate the skill in energy anomalies for weekly means over Germany for different TSOs in Germany. And we calibrate these forecasts. And here I have shown you just one skill that we calculated, which is the anomaly correlation coefficient. And we see the way I have tried to present it here is in the plot B, you see the dependence of the skill with respect to lead time for sub-seasonal forecasts. And you can see the expected result that for the first and second week, the skill is quite high and it declines rather strictly after that. But I've also tried to average across different lead weeks to see if there is any systematic skill with respect to the target season or the target month that you're trying to predict. And we see that in winter, we expect some slightly higher skills than the transition periods, that is in April and October, November. And then there's a slight peak in the skills in peak summer as well. Similarly, we have results from seasonal power forecasting where we use the GCFS model from DWD. My colleague Jan Vandel would be elaborating on it tomorrow in more detail about the skills here as well. Here we used an approach called subsampling where we select the best ensemble members based on a statistical forecasts of teleconnection indices. And you can see here in the target season plot particularly that this process of subsampling increases the skill significantly. As you can see, I have already only plotted it for Germany, and you can see the line, unsampled line for Germany, which is the dashed line, is quite below, significantly below the black solid line for Germany, especially in the peak winter and peak summer seasons. And the error bounds that you see are also are obtained by bootstrapping to test if the skills obtained here are significant or not. You might be wondering why I would average across lead months or lead weeks in the first place, and this becomes quite clear in this plot. For seasonal forecasts, if I were to average across all seasons for each lead month, for 1 to 3, 2 to 4, 3 to 5, and 4 to 6 month forecast, you see that there is not quite a tendency or trend here for the skills with respect to the lead time for seasonal forecasts. However, you see that if I average across all lead months and just plot the skills for each individual seasons, we see significant skills for extended summer and extended winter, which tells us, which is likely because the skills for seasonal forecasts is largely due to large-scale circulations, which change very slowly over a monthly period and therefore do not have a very strong lead month dependency. However, this is all about the average tendency of the forecast because the anomaly, the skill scores are evaluated on the ensemble mean. Now, the question is if we are capable of predicting these extreme events which occur at smaller time frames than these. So, which is, and as I said, I focus on Flouter forecasting. So the problem is that if you see this is a plot from time frame from ERA 5 dataset, and you can see that given an event on a 48 hours rolling window on the top plot, if you were to average it over 7 days, the signal decreases significantly. And if you average it over 3 months, which is the time frame for our seasonal forecast, the signal goes away entirely. And this is expected because these are high resolution events. So no surprise there. The question is, we evaluate those skills that I showed you earlier at these averages. So we can't just expect that we can use the high resolution forecast and directly empirically estimate the Dunkelflaute episodes from there. And that indeed doesn't work since the frequency of those events does not correspond to the actual observed frequency from the model. So what I tried to do is I tried to develop a post-processing model and see if I can squeeze some skill out of those forecasts. What I do there is instead of taking the ensemble means over the time windows, I try to consider the entire distribution of the given a window. So sub-seasonal is weekly windows and seasonal is 3 months windows. And I take the forecast. Here are the example of probabilistic forecast, the black line being the mean and the shaded and the lighter lines are the ensemble members, individual ensemble members. And I take these windows, respective windows, and I calculate statistical features out of these windows, which are, for example, mean standard deviation, skew, kurtosis, the 4 statistical moments. And since these are probabilistic forecasts, I can also calculate probabilities at different thresholds within the distribution that I would obtain otherwise with a simple empirical analysis. And what I then do is I train a machine learning classifier and help me predict if there is going to be a yes/no Flouter event, but also importantly, if there is, what is the Flouter intensity? So how long it's going to last? We'll see that that is going to play a significant role in the classifier. All right, so here are the results. I have plotted here on the y-axis the area under the ROC curve for the classifier, and the 0.5 is the baseline. That is, it tells me the skill that a random classifier would have. And I see that for subseasonal forecasts, as you would expect, the skill declines significantly after the second lead week, but still remains slightly positive, around 0.55 after the third week, and then declines further towards the last weeks. Something that I mentioned in the previous slide was about the flouter intensity. So what I found in the analysis was that if I train a machine learning classifier with all sorts of events, let's say on a 48 rolling hour window, only for 1 hour, the produced capacity went below the threshold, then that would be marked as a Dunkelflaute event. But if I were to mark all such events, it makes too much noise for the classifier. And so the classifier is not able to predict these events that are very short lasting. So I found that for this machine learning classifier to have any significant skill at all, the significance of the skills is again determined by bootstrapping, which is the intervals, the standard deviation for all of them. The bootstrapping samples are plotted here as shaded regions as well. So I found out that on subseasonal scale, an event has to be at least 12 hours for a subseasonal forecast to have any skill at all. Below that, it doesn't quite work. It's worse than a random classifier after 2 weeks. This is the subseasonal result. Let's look at the seasonal result. Here, I find that no classifier works if I take events less than 4 days. And if their event lasts less than 4 days, the classifier just takes it as too much noise and is not able to learn anything. So here I see that for any significant skill, again, the significance is denoted by the bootstrapping intervals here. To have any significant skill, the event has to be at least 4 days. And here you might be wondering again why I haven't plotted the lead time dependency. I told earlier that the seasonal forecasts do not have a very strong lead time dependency. And if I were to split them for each lead time for each TSO, I'll have too few samples and you will see too much noise and no skill at all. So I averaged it for extended winter for different TSOs. And you can see that for Germany, the skill is significant. However, for individual TSOs, these are smaller regions and have more noise because, well, for Germany, you average over a larger region. This does not seem to impact the weekly forecast too much. And I assume that's because the amount of training data I have for weekly forecast is much larger than I have for seasonal forecasts. And I think that might be the reason why this extra noise introduced at smaller regions with these TSOs is causing a problem. So far, so good. We understand that there is some sort of skill here that might be present, but again, the question remains, is it significant enough for me to implement it in operational context and extract any use out of it? So for that, I have here, before I go there, so this is an overview of how a forecast might look like in operational context. So I would say for week 1, week 2, week 3, I have the subseasonal forecast, and I would say, look, there is a probability, and above a certain threshold, we have a Dunkelflaute, and then we will go seamlessly into the seasonal overview, and we will tell if there is a flouter that is supposed to happen that has an intensity of more than 4 days. And now I come back to this question, if this has an operational value, if the skills shown here have any operational value, have any value in the operational context. For that, I use a very simple cost model. We do not need to go into the details of this. If you're interested, I'm happy to talk with you in detail about this later. But the simple assumptions here are that assume that a Dunkelflaute costs some value C, which is in this analysis 1. And let's say the preventive cost for, if you were to take any measures against the Dunkelflaute, is some fraction K of this value C, then, and hopefully it's less than 1. So otherwise it doesn't make sense. So based on the value C and KC, and since I get probabilities from the classifier, I can define the threshold over which I were to consider the true positives and false positives. And then I can make a simple cost model which is dependent on the threshold. And what I can then do is try to maximize my profit to see which threshold would be optimal in the operational context. And here I have compared the profit for the model, the trained classifier that I have trained and showed you the results of earlier. And then, of course, we want to see how much profit I would get if I had climatology, if I were to just take the average over the 20 and 30 years timeline over which I had the model to see if I'm doing any better than climatology. Obviously, doing nothing, which is the second part, is the most costly. So either you act based on climatology or you take the classifier. So the real comparison is between those two then. Let's look at the results for subseasonal forecasts. Here you see, I want to point out that earlier we saw for week 4 and week 5 and 6 that there was some skill present after the third week as well. However, if I were to put all this analysis in the cost model, I see that that skill is not sufficient in operational context. And after my third week, I stopped getting any value out of the machine learning classifier. And here you see the difference for different TSOs as well, which was not reflected in the ROC value alone. And this is because the threshold for TSOs in Germany is same, and TSOs are smaller regions. They have larger number of these episodes simply because you average over a smaller sample, and the number of episodes, events on TSO level is much higher. Therefore, the classifier used for those events also gives much higher returns compared to Germany. So you see that just looking at the ROC does not provide you a full picture, and the simple cost analysis is able to give us more insight. Another thing to note here is that the K value here is 0.1. So I have chosen that so that I could show something to sort of understand what's going on, to sort of intuitively see what's happening. But if you change the K value, of course, the profit would change. If the K value was much smaller, let's say 0.01, which means your preventive action is extremely cheap, then you can take the preventive action every time, and there's no use for the classifier. On the other hand, if your preventive action costs very much, so it's comparable to the C, so it's close to 1, then the cost of preventive action is just too high, and you actually can't trust the classifier either. So this is something that also needs to go into the consideration when we develop the Dunkelflaute model. What are the preventive costs? And here, of course, it's a very simplistic model. The real model in true operational context is obviously much more complex and nuanced, but at least it helps us understand how we could address it. The same thing for seasonal forecasts. Here, the results are quite comparable to the ROC value that we saw earlier. We see that for individual TSOs value. One thing that I forgot to mention, the dotted line is the climatology model. And you can see that after the third week, the profit goes compared to or below the climatology line. So that's how we decide that after a certain lead time, it's not useful anymore. Here also we have the same results. Climatology is the yellow column, and the blue column is the teal column is the our model itself. And we see that the fluctuations here are high. It's just because the seasonal model has too few training data points for the machine learning classifier to work. However, we see that there is some hope for Germany for if I were to make Dunkelflaute forecast for whole of the country. Exactly. So with this, I want to go into the future steps. We saw today in the many presentations that there's potential by including weather regimes and teleconnection indices as for such a forecasting system. And the kind of network, the architecture that I have for the classifier, it's very simple to add extra features, which could be weather regimes or teleconnection indices, and see if that improves the forecasting accuracy. So far, I have not integrated PV production, which I plan to do soon, but I don't expect the results to change much because we saw earlier that the real culprit behind the Dunkelflaute episodes is typically wind in winter. I want to create a seamless picture over the shortest horizon. So for the next 14 days, going to seasonal level and see to create a seamless picture of Dunkelflaute forecast. So the investigation at shorter horizons remain, but I expect the skills there would be much higher compared to what I showed here. So, and as I mentioned earlier, the model I have is very simplistic, and a nuanced cost model would be very helpful. And that is where we could work together with the TSOs to understand how exactly or what the preventive actions can be for such episodes. With that, thank you very much for your attention. And I do apologize. I have a lot of questions, but it's supposed to, the main idea of the questions is that I want to understand a bit better what are the applications of subseasonal and seasonal forecasts and how you may want to use them. So you do not necessarily have to answer all of them, but if you have an idea or you work with them, you're welcome to give input. And so what are the applications of Dunkelflaute forecast at subseasonal scale? Hedging, many applications were also mentioned by Albert. I instantly took a photo of that slide. Preparedness, storage management. Price forecast. In the next question, I would also write, I would also like to ask what are the applications in seasonal scale. So perhaps if you're thinking about it, you could, if you can, perhaps you could also separate the horizons if you are already at it. Okay, I think we could move to the next one. So at seasonal scale, what could be the applications of such Dunkelflaute forecasts? Trading was something that Albert mentioned. Security of supply, capacity planning, maintenance. Perhaps I'll come back to Gregor and ask if maintenance is more relevant at subseasonal scale or seasonal scales, or maybe it's not, it can't, maybe we can't separate them so much, but maybe we can talk about it.
I wanted to put it in before, but it wasn't fast enough.
Ah, okay. I'll put it myself. Thank you. Okay. Thank you very much. So as I mentioned, the cost model is right now very simple, and it surely doesn't include all sorts of different preventive actions one could take. And surely the preventive actions also depend on the intensity of the Dunkelflaute and the horizon of the Dunkelflaute. So perhaps some things that come on top of your mind about what sort of things should be better modeled in the cost model for the Dunkelflaute, so that it's more useful in the operational context. An energy system model. Weather regimes, day ahead and intraday price. I wonder if that also plays a role at subseasonal and seasonal level. Potential reserve power prices, actual demand during. Actual demand during Dunkelflaute, that's an important point. This is something that I would also want to include in my model to see if there is what is the demand parallel to the production. Flexibility options. Thank you. So I also wanted to get an overview of which forecast products are most of you using right now. I imagine intraday and day ahead are gonna win by a landslide, but maybe let's see what's the percentage.
So this is independent from the budget?
Yes, so in general, so now the Dunkelflaute section is over, so I wanted to go a bit more generally into the applications of sub-seasonal and seasonal forecast. So this is where I wish to ask in general which forecast products you use. So sub-seasonal is at 20%, huh? Didn't expect that.
Only choose one, is that correct?
Sorry?
Only choose one.
Oh,
We can do several.
It seems some people are saying they can choose multiple. But okay. Well, medium range forecasts seem to be winning. It's rather interesting. Okay, thank you. Maybe I move to the. So here I want to just have a general overview of applications beyond day ahead.
Yeah, we were thinking we could do this maybe tomorrow so that we
Sure.
can the door.
Sure.
Okay.
That sounds great. Thank you.
Thanks. And he'll be here for the dinner, I hope.
Yes, I think so.
And that means we can ask him, but we can't with Jim Wilczak, who's retired from NOAA and is only available online. So he has a really hard time joining for dinner.
And we also take the questions after Jim, so
Yeah.
we see how much time we have.
So how do we get him here?
We can see him.
How do we hear him?
Can you see my slides now?
Yes.
Yes.
Okay, great, thanks. Okay, yeah, I'm Jim.
I can see them, but
Just wait a minute.
Sie haben noch
Okay.
gesehen.
Yes. And then can you take the participants away?
Yes, and you can. There, no, then of each other. Where's the mouse? Yeah. So I think.
Can you not show Jim as the speaker so we can see him?
Maybe, but.
Maybe go
on layout, maybe.
Yeah.
Where's,
Layout.
where's my mouse? Here. And where's layout? Okay.
Yeah.
What does it make? No difference?
You just moved it up. Yeah, so leave it.
I think that's fine.
Yeah.
Okay.
So we can see Jim also.
Jim, please go ahead.
Okay, great, thanks again. Yes, I'm Jim Wilczak, formerly from NOAA and now trying to enjoy retirement, but I'm still working on some science on the side. And here's my new personal work logo that reflects my current job status as well as my state of mind, I guess. So first question is, why study wind and solar droughts? And I'll also be referring to these as WSDs and Dunkelflaute. And as you've already seen in the presentations in this session, that to be reliable, a wind and solar-based energy system has to function during the times of greatest system stress, which are just these net energy droughts, which are wind and solar droughts in conjunction with large loads. And if an energy system can handle these worst energy droughts, then it's also going to function well during more generation and loads. So it's not going forward. Okay, here we go. The presentation is based on these three papers that are shown here. The last of these is a perspective article that provides an overview of some of the impacts of wind and solar droughts. And I'm indebted to my various co-authors shown on these papers for the much of the material that I'll be presenting today. So the outline of the talk is very briefly, I'll just comment a little bit about definitions and describe some metrics. And then I'm going to go into more detail on these 10 topical areas where I and my colleagues in that third overview paper decided or thought that these were research areas in which it would be most fruitful to look more carefully at wind and solar energy droughts. So in terms of definitions, wind and solar droughts are complicated because of their multi-dimensional character. Four main attributes are their intensity, duration, spatial extent, and how often they occur. Occasionally, you might see that seasonal variations are taken out, which then only leaves short-term weather and climate trend components. But of course, it makes a lot more sense to include the seasonal components in, because that's what the energy system has to respond to, is the total shortage. So in terms of metrics, droughts are often defined using some ad hoc thresholds of duration or amplitude, but those thresholds really don't have any clear relation to the energy system itself. And ideally, what you would like to do is have drought metrics that would depend only on energy system attributes. And my preferred metric is using intensity, duration, frequency diagrams that do not use any thresholds of amplitude or duration. And those two examples are shown here for the Southeast United States on the left and for the Quebec interconnect in Canada on the right. And these were constructed using 64 years of bias-corrected ERA 5 daily capacity factor values. And the first step is to normalize the capacity factors by their long-term mean capacity factors for each region, and then show those as a percent. And it then applies continuous moving averages to the normalized power time series, where the longest running mean length corresponds to the maximum duration that one is interested in. And so here these go out to 90 days. And then the next step is that minimum and maximum values are then found and plotted for each duration. And those are shown here as the blue curves for wind, and solar is in the red curves. And a 50-50 mix of wind and solar generation is shown in the green dash curves. And when you do it this way, the power produced during drought events is then going to range from 0 to 100%, where 0, of course, is the very worst possible drought, while the power produced during floods will be any value greater than 100%. And it's clear that in the Southeast US on the left, that wind droughts at every duration have much greater amplitudes than solar. And the opposite of that is true for Quebec, where solar droughts are more intense than wind. Also, droughts for the 50-50 mix of wind and solar are always less intense than either wind or solar alone. And so the next step is to calculate recurrence intervals from the IDF curves. And for each duration value, the most extreme event is removed, and then you find the second most, and you do that recursively, the third, fourth, fifth events, etc. And then empirical recurrence intervals can be then readily found from that family of ranked extreme events. And those are shown here on the bottom left for New York State, and on the bottom right for a hypothetical conus-wide balancing area that would span the entire contiguous United States. And in these plots, the solid green curve is the recurrence interval for once every 65 years, the dashed line every 16 years, and the dotted line once every 4 years. And you can see that in New York State, the droughts are considerably larger than they are for the CONUS region, and that just shows the additional benefit that you get from having a much larger balancing area. The kind of horizontal blacked dash curves are the contributions of the mean seasonal cycle on the drought and flood events, and the departure of the green drought curves from the black seasonal curves just gives the contribution of the short-term weather variability to the droughts. So there are various mitigation options for wind and solar droughts in highly renewable systems. These will be overbuilding of generation, transmission, energy storage, dispatchable generation that can come from a variety of sources, and demand response. And finding the optimal mix of these mitigation approaches is typically studied using capacity expansion models, using some assumed future levels of energy demand. And that takes us to our first research need, which is linking wind and solar droughts to capacity expansion models. Some of the shortcomings of capacity expansion models is, first, relatively few have been published, and most often they use unverified meteorological data sets, which it's not really clear what impact biases might have. Also, too short of time periods have historically been used, typically only 1 to 7 years of data. Related to that is that drought recurrence intervals usually aren't analyzed. And then finally, very few capacity expansion model studies take a deep dive to investigate in detail how the energy system responds to wind and solar droughts. I was so happy to see Yvonne's presentation that she gave, a wonderful presentation, because she did exactly this, starting to look in detail, how does an energy system respond to wind and solar droughts? And you can ask some interesting questions. For example, does the capacity expansion model mitigate droughts of similar amplitude that might occur in different years, the same way? And across different capacity expansion models, do they mitigate droughts in similar or very different ways? The second research need is looking at the meteorological conditions producing wind and solar droughts. I guess this was discussed earlier in the meeting, so I won't go into detail on that here. But I think the main point is that because wind and solar droughts have such extreme regional variability to them, that it's really necessary to do this kind of meteorological analysis of droughts on a regional basis to be able to understand how you might be able to use that information to forecast them. The third research need is related to this, and that's snow and ice, wildfires, and dust storms. And there was an earlier presentation on the snow and ice. That was great. Of course, ice accumulation when turbine blades can result in significant power reductions. And snow and ice, obviously, on solar panels will have a huge impact. And that's especially true in parts of the United States and Canada. And historically, there's been almost no mention of how snow and ice are treated in capacity expansion model studies, if it's treated at all. Fourth research need is better data sets. We really need, I believe, multi-decadal, high resolution, 3 kilometers or better, bias-corrected reanalyses that provide consistent wind and solar fields. Reanalysis data sets such as MERA or ERA5 are very often used for Dunkelflaute types of analyses. Because they assimilate observations, they're often considered to represent the true state of wind and solar energy generation. But because they're dependent on an NWP model, they too are going to have errors. And I found that during extreme wind and solar droughts, these errors can be quite large. So for example, the ERA5 solar derived solar power produced during the most extreme 10-day droughts in parts of the US was 60% greater than that was derived at the same time using direct solar irradiance observations. And I also found that the most extreme wind droughts at some sites, even in flat terrain, using the ERA5 was only half of that observed. Another issue with reanalysis data sets is the coarse resolution, which may overestimate wind drought amplitudes in complex terrain. For solar droughts, oftentimes products, the NSRDB and SERA products are used for those, and these are based on radiative transfer models that are driven only with satellite cloud observations. To date, I'm not aware of any studies that investigate the accuracy of NSRDB or SERA for solar droughts. You would expect that it would be better than, say, the ERA 5, but I think this has yet to be shown. Sixth research need is evaluation of the impacts of wind and solar floods on flood events on system design and market design. Floods present, of course, opportunities for charging storage. They also could present opportunities for developing new industries that may not need continuous power, for example, perhaps water desalination. But floods also present challenges, and challenges to the grid include transmission congestion and potentially massive curtailment of generation. And I found that the largest one-day flood events for a mix of wind and solar for different regions across the United States can exceed 300% of the long-term mean generation. And trying to make use of that large amount of energy that occurs really episodically and may be used very rarely would be very difficult. And so I think it's unlikely that it would ever all be used. There's also, flood events also provide challenges to market design. Are markets robust to long periods of negative prices that may occur during protracted flood events? The seventh research need is quantify the limits of predictability for wind and solar droughts. And the last two talks in this session touched on this topic, and were really great to see. Of course, in the simplest energy system model, it simply will use storage whenever generation is less than load and storage is not empty. But if you have some dispatchable generation that's available, the question is, can forecasts be used to develop more complex rules for discharging storage in order that you can keep some available during the most severe droughts? And in order to be able to answer that question, you really need to understand the limits of predictability of wind and solar droughts and load extremes and the compound events combining all three. And I think an interesting question going forward in the future is, will AI model limits of predictability be any different than those from NWP models? Research need number 8 is wind and solar drought implications for demand response programs. So wind and solar drought statistics will influence the design of these demand response programs, but wind and solar drought predictability can also impact those programs. Forecasting power outages many days in advance makes those demand response programs much more attractive to companies than if they were to occur with little or no warning. The ninth research need has to do with climate sensitivity, and there have been multiple studies that have shown wind and solar mean generation is sensitive to various modes of climate variability. And an important question is whether or not wind and solar droughts will also be sensitive to these climate modes of variability, and how robust are these sensitivities across different geographical regions, and how robust are the sensitivities across different meteorological data sets, perhaps reanalysis data sets. And related to this has to do with climate change, and that is, how will the statistics of wind and solar droughts and loads change under different climate change scenarios? And to date, I would say that various studies I've seen haven't really found consistent results against various climate models. And that takes us to the final research need, which is developing countries. And climate change, of course, is a global issue. And if you want to solve it, you have to solve it globally. Population and energy demand is growing rapidly in developing countries. And that's very likely to continue. And so characterizing wind and solar droughts in those countries is going to be important to design new renewable-based grids there. And I believe that it is likely that new observational networks are going to be needed to validate and correct these model-based data sets. So concluding remarks are that as electric grids become more renewables-based, I think we've already seen that they become increasingly vulnerable to renewable energy droughts, and specific mitigation solutions are going to depend on these drought characteristics, their intensity, duration, spatial extent, and recurrence intervals. And it's so great to see all of this work being done on Dunkelflaute, because I think it's really needed as we go forward. And yeah, I wish that there was this much work going on in the US on this as well. So thank you very much, and I'll stop there.
Thank you, Jim. We're just putting on the Slido questions. I hope you can see them too. Can research need topics for wind and solar energy droughts? Please rate which you think are the most important.
Gregor, I can't really see your screen. Is it possible that you can start sharing that again?
Yeah, Jim, we are making a new research program for the next 10 years. And Helmut is trying to get this online.
Where do we have it now?
Yeah, we wish it was US time here and we were all fresh, but we are we are in our last
No, wait a minute, I think
minutes of today. So everybody's looking forward to the dinner, I think. So you have to bear with us.
Some fresh air.
Oh.
Yes. Now you should be able to see it.
Yes. Great.
Yeah. Now we cannot see it anymore.
Different screen. Yeah, so
No, it's coming.
Oh, no, it's going away from here.
yeah. I don't know who made it set up suddenly two screens. Usually.
I think we have our mobile phone. Yeah, I think we have
a winner.
We have a winner. We have two very close and 3 over 4.21 over 4 votes. So that looks good.
Right. Well, it doesn't surprise me, I guess, that these top two are in the top two. It's interesting that they are almost exactly the same. Yeah, I think that this issue of predictability is really going to be important going forward in order to be able to manage storage in the future. And there really it's just this tremendous need, and it's been there for such a long time for better data sets to be able to evaluate renewable energy in general, but wind and solar droughts in particular. So and it's a lot of work to create those kind of data sets. It's not easy to just go out and anybody can do it. So it takes a very concerted effort from large institutions to be able to do that.
Okay. Go to the next one. That's the only one. Okay, so and the question is whether you still have some
Questions?
some very last questions for Jim, because as mentioned, he's not going to be at the dinner. Shouldn't have mentioned dinner. That's giving him far too much incentive for not thinking about work. No questions here. Brilliant. Then I would like to thank my speakers again for this Dunkelflaute, very specific. One of the extreme events that we have are looking at, and we can see that we are not running out of work as per Jim's talk. And Helmut is going to tell us where we need to go.
Yeah, this is just a short web map where we are. We are here at EWD up here. We go through the main entrance, and then to the right, it's at about 200 meters across the main road. And here is the tram station. It will be line 15, goes every 10 minutes, and then will go in, goes to Frankfurt. 18 minutes should it take. And in Frankfurt, we pass Frankfurt South main station. This is Main, Frankfurt Main, that's the name of the river. So it's not the main station, it's Frankfurt South. When I wrote it in German, I had no problem. Now talking English, I noticed the problem. So it's, but it's important, it's also the S trains go from there, for example, if you want to go back. So the tram goes here, and then after we pass here, Schwanthaler Straße, and from there we just go, I think 100 meters back, and there are Wagner, Apfelwein, Wagner, Schweizer Straße, Street 71, that's the address. That's where, so we just go 18 minutes. As I said, it's the, I think it's the first station after the Frankfurt South. How many people do already have a ticket? I mean, quite a few of the Germans, they have so-called Deutschland tickets. So, although actually, so that we need, so how many people need a ticket? Please raise your hand. 1, 2.
13, 14. Just 14.
Yeah, also, so we need.
That means we need 3.
Because there are, you can buy tickets, group tickets for 5 persons. And also important.
Per person. So it's easier, so we can, those that do not have a ticket can use it to get there and to get back to.
Yeah, important here. Frankfurt starts here. So this is just a ticket for Frankfurt. So because we walk to Frankfurt, but then in Frankfurt we have to take the tram. So.
But the groups also have to get back together.
Yeah, the 5 people then should go back together. That's right.
Find a ticket with a different group.
Would you recommend buying tickets on an app or something? Would you recommend buying a ticket on an app? Maybe.
You can buy pay also with
buy own tickets.
No, I mean.
No.
You have to download the app.
Yeah, but it just, yesterday I was just waiting forever behind the, at the station behind someone trying to figure out how to do it.
We hope.
So it's like, I had to wait like 12, 13 minutes.
I hope we do it.
That's why I'm thinking,
so much to
Do you use an app? I downloaded this, but I will need to skip the. I downloaded it.